Okay, good morning, bom dia. We are ready to go on Friday for lecture 20, and today we are dealing with the Phanerozoic rock sequences in southern Africa, the rocks of Gondwana, and we will start with the Paleozoic Cape supergroup and the Cape or Samfrau orogeny. So, let me start with the Cape supergroup, which is the first Phanerozoic sequence that we see in the geological record in South Africa, and is most famously exposed around this famous Table Mountain in Cape Town in South Africa. So we are dealing with a time period from about 500 million years to about 300 million years during which these rocks were laid down. So following the assembly of Gondwana during the Pan-African orogeny, you ended up with the configuration of the continents somewhat in this fashion, and so we had a large supercontinent. And the area that we are going to deal with is the southern part of the supercontinent, which is a rather complicated mosaic of different pieces which have to be put together in a very tight configuration if you want to have a tight fit of the pieces that make up Gondwana. So we have the African plate over here, but then the South American plate has to wrap completely around the African plate, because the Falkland Islands, or also known as the Malvinas, were actually situated paleogeographically right adjacent to South Africa and rotated about 90 or 180 degrees, because the rocks in the Falkland Islands match exactly the rocks that you see in South Africa, the Cape supergroup rocks, and even the Saldanian belt rocks, the Pan-African rocks that we see. They form the local basement in the Falkland Islands, and then overlain by the Cape and the Karoo supergroup rocks, and they are all those have been found in the Falkland Islands. It's been known about for a long time, and in fact, more recently, geologists like Bob Thomas, who used to be with the South African Geological Survey, who had mapped the regions in the Namakwa-Natal belt in South Africa, in this region here, he actually went to the Falkland Islands and mapped the Cape Meredith complex, which is the Neoporozoic and rocks that you find in the Falkland Islands as well. So there is a very good match, but there is still other pieces that have to be fitted in properly, and they have to be rotated and moved in order to have a tight fit of Gondwana. This is one of the big puzzles about trying to look at how Gondwana had fitted together and broken up. Later on, if you have a chance, I will show you a video, if it works, of the breakup of Gondwana that's from Colin Reeves, but it's not exactly part of this presentation. So what we're talking about now, the Cape supergroup, was formed sort of after the formation of Gondwana. And what you have to bear in mind always in this reconstruction, and even in the previous one, is that when Gondwana was formed, there was an active continental margin to the south of Gondwana, which has remained. Today, it would be the Andean, the subduction zone on the western side of South America, extending down into the Antarctic Peninsula through the island arc chains, the Scotia Arc, and so on. But this continental margin has been active since the formation of Gondwana, and is still active up to today. But the events I'm going to talk about are taking place here on the southern coast of Africa. So you have to think that there is a subduction zone and a magmatic arc which is still present in South America and extending through the Antarctic Peninsula. And so what happens in South Africa is actually happening in a back arc environment. And at some point in the early Paleozoic, there was a rifting event in this region here, which you could regard as a kind of a back arc rift opening up, which is what happened here. So you can see this as a little rift opening up, and in this little rift, you then open up a passive margin on the African continent side. So, but we always have to remember there was still an active arc to the south of that and a subduction zone, which was basically this one down here from South America into Antarctica. So, in this rift then was deposited a whole series of sedimentary rocks dominated by quartzites and shales. In fact, there are no volcanic rocks here at all. So this is a completely non-volcanic passive margin, and it's got rocks that were deposited only in the Cape region in South Africa, and extending towards the province of KwaZulu-Natal on the east, where there was also rifting, but the sources of sediments here were quite different from the sources of sediment in the south here. So prior to the development of this rift, we had a Pan-African belt in the southern part of South Africa, and it is manifested by grey-wacky type sedimentation, deep water sediments, which are intruded by the Cape granites. And the Cape granites are exposed in that whole region around Cape Town, and they form the base upon which these rocks of the Cape supergroup were deposited. So here is a famous beach just near Cape Town called Boulders, where you have you can be swimming here among all these penguins. So, but the granites around here are about 540 million years, and they are part of this Saldanian orogenic belt, which forms the basement to the Cape supergroup. When you go south of Cape Town towards the Cape Point, there is a very famous road called Chapman's Peak Drive, and it is one of the most famous geological exposures in South Africa because the road itself is built exactly on the unconformity between the Cape supergroup above and the granites, the Cape granites below. So the Cape granites, 540 million year granites, and they were uplifted quite rapidly, and by 500 million years you had deposition of these shales and sandstones of the Cape supergroup. And here is a famous view of Cape Town from one of the northern suburbs of Cape Town, and in the foreground you see metamorphic rocks of the Malmesbury group, which are part of this Saldanian Pan-African age orogenic belt, grey wackies, which are intruded by the Cape granites. And the Cape granites and these grey wackies, they form the bottom 1/3 of Table Mountain. So, and then it's overlain by the Cape supergroup sandstones. So in the bottom slide here, what we can see is basically a cross section through this kind of a magmatic arc. This is most likely there was an active margin here rather than just ocean floor. So this would be the Falklands Plateau or something like that. This was the southern margin of Gondwana land, and you form this extension. And on this portion here, on the southern part of the African continent, you had deposition of the Cape supergroup. Subsequent to the deposition of the Cape supergroup, about 300 million years ago, 320 million years ago, you had very active compression starting with subduction zone, and there was compression and closure of these sediments to form an orogenic belt called the Cape Fold Belt or the Cape Fold Mountains. So the Cape supergroup rocks were all deformed, and in a foreland basin behind this was deposited the Karoo supergroup. So this will be the subject of our next lecture. But first I'm going to concentrate now on this passive margin succession, which is the Cape supergroup. So here we see a simplified geological map of South Africa, and it's dominated by this huge sedimentary basin, which you see in green colors, which is the Karoo Basin. That's the one that succeeds the Cape. And down here in this bright blue color is the Cape supergroup, and it also has equivalent rocks which are exposed in KwaZulu-Natal. Now, when we look at the basement upon which these sedimentary rocks are deposited, we see here the Kafar Craton to the north, and this is the Craton boundary over here like this. It is exposed. Here is a major strike slip fault zone separating the cratonic rocks and the sedimentary cover on this side from the active magmatic arc terrains, which are gneisses of the Namakwa-Natal belt, which are 1,000 million years old to 1,200 million years. So this is a belt of Mesoproterozoic rocks which was accreted to the southern end of the Kafar Craton during the formation of Rodinia. Then when Rodinia broke up and then reconstituted itself as part of Gondwana, there were Gondwanan or Pan-African aged orogenic belts which were part of the larger network of cratons that collided to form Gondwana, which I started this lecture with. And in South Africa, we can see this on our coastline here, the Garib belt, which is a counterpart of some of the rocks that we see in South America, in Uruguay, for example. This is the counterpart of that, Dom Feliciano belt and so on. And if you come to the south of South Africa, we see a Pan-African orogenic belt, the Saldanhan belt. And the Saldanhan belt is consisting of these grey wackies and the intrusive Cape granites, and then it is overlain by the Cape supergroup, which you see in blue. And the Saldanhan belt is best exposed in the area north of Cape Town, near the town of Saldanha Bay, which gives its name to the belt. And there are also smaller exposures in inliers within the Cape fold belt. So let's get to the corner of Africa where Cape Town is situated, on the southwestern corner of South Africa. And we see this peninsula over here, which is the Cape Peninsula. The city of Cape Town is situated here, and the Table Mountain, the famous Table Mountain, is here, and there is this peninsula going up right down to a point called Cape Point. So let's look at that in more detail. Here is an aerial view of the mountains. This is Table Mountain and its surrounding rocks, going up towards Cape Point, and that's Table Mountain there actually, and these are some of the southern suburbs of Cape Town. So here's another view of Cape Town again, with the Saldanhan rocks in the foreground, and another aerial view like this taken from a book which shows the extent of the shales and granites that make up the bottom 1/3 of Cape Town, and the top 2/3 of the Cape of Table Mountain is made up of the Cape supergroup rocks. So if you look at the appearance at a place called Sea Point, a very famous beach exposure in the city of Cape Town itself, we see a very famous exposure where we see the Malmesbury group rocks, which are the Pan-African part, the Saldanhan belt rocks, dated between 560 and 540 million years, which are then intruded by the Cape granites. And here is the exposure, and the exposure was one of the first outcrops to be described in South African geology back in the early 19th century. And if you look at the sedimentary rocks are turbidites. They are graded sequences of turbidites in the Malmesbury group, and they are intruded by the Cape granites. And this outcrop was actually described by Charles Darwin when he went on his voyage around the world, when he came through here in 1836. But he wasn't the first one to describe these outcrops. They were actually written about and described already by about 1813. So, if we look at the setting of this whole region, of this particular arc, this magmatic arc, the Saldanian belt, was formed during the formation of Gondwana by a collision between South America and Africa. So there was some kind of an active magmatic arc, and in this, associated with this, was either a fore arc or a back arc, in which this turbidite sedimentation took place. And then there was a collision. This is during the Pan-African orogeny, the Saldanian orogeny, and there was intrusion by the Cape granites at 540 million years. So, and following this event, there was further extension and then rifting, in which a passive margin was created, and the Cape supergroup rocks were then deposited on there. So, from that previous outcrop where we saw the contact between the Greywackies and the granite, we can turn around to look at this mountain, which is Lion's Head in Cape Town, and see three rock types that are exposed on this. The Malmesbury schists or sediments, which are on this side, intruded by the Cape granites, which have a nice sort of outcrop pattern. And then there is a big unconformity over that, and it's overlain by the Table Mountain sandstone at the base of the Cape supergroup. If you climb up onto Table Mountain, you can see very nicely an angular unconformity between the Saldanian rocks exposed, dipping vertically, and then covered by the sandstones of the Cape supergroup. And I've shown you this drive, this Chaplin's Peak drive, which is built along that unconformity. Now, if we take a closer look at this whole this whole scenario, we have the Malmesbury group rocks, which are the Greywackies, and we find that the youngest detrital zircon in these is 560 million years. So these rocks have to be younger than 560, and they are intruded by the Cape granite, which is dated at 540. So just 20 million years after the deposition of these sedimentary rocks, they were intruded by the Cape granites. And following that intrusion, and the people have looked at the metamorphic petrology of the contact zone between the granite and the Malmesbury sediments, and worked out the PT conditions under which this intrusion occurred. So it must have occurred at some depth, a few kilometers down, at a certain temperature, and it was rapidly uplifted. After this orogenic belt, the entire system was uplifted to sea level very rapidly, because then it was eroded flat, and there was deposition of the Table Mountain group at the base of the Cape supergroup, and the youngest detrital zircons in there are roughly around 510 million years. So within about 40 million years of the intrusion of the Cape granites, they were being uplifted and eroded. So the rocks of the Cape supergroup were then deposited in this passive margin, and these rocks have been divided into three major groups. The Table Mountain group, which is the one that you see on Table Mountain, made up mainly of quartzites with some shales, and it's then overlain by the Bockerveld group, in which we have a series of alternating shales and quartzites, which are formed in some kind of a deltaic environment, and then the overlying Witteberg group, shown in black here, which are again dominated by quartzites. So this is a mainly siliciclastic succession. There are no carbonate rocks and no volcanic rocks in this succession. When you go to KwaZulu-Natal, you can see that there are some similar rocks on this side, on the eastern side of the depository, and here we find rocks that are equivalent to the Table Mountain group, which are called the Natal group, but they are made up mainly of arcosic sandstones rather than quartzites like we see in the Cape supergroup. So here is, in summary, the stratigraphy then of the Cape supergroup. We have the older basement, and then the Table Mountain group dominated by quartzites, minor conglomerates. And what I didn't mention is that there is also a diamictite, which represents a glaciation in the late Ordovician, and it is found at the very top of Table Mountain. And the equivalent rocks to this in the KwaZulu-Natal are arcosic sandstones. So I can just show you them quickly. These are the sandstones, the red arcosic sandstones that you find only in KwaZulu-Natal, but in terms of age, they are the same as the quartzites that you find on Table Mountain. Then there is the alternating shales and quartzites of the Bokkerveld and more quartzites of the Witteberg. So it's a sequence that is completely dominated by quartz-rich sandstones and shales, and it was deposited basically in a kind of a passive margin overlying the eroded and uplifted Saldanian orogenic belt, which has the deformed Malmesbury group turbidites intruded by Cape granites. So we can actually see the very nice exposure between the Cape granite on the bottom and the quartzites of the Table Mountain group, together with shales, and it's exposed along that unconformity road at Chapman's Peak Drive, and we can see a group of red shales over here which have been mud cracked and filled in with more sandstone and lenses of sandstone interbedded with shales, and they're forming in a kind of a tidal flat environment. We can see these mud cracks which have been filled in, so indicating the exposure and during deposition, and the ripple marks as well, telling us that you are dealing with a kind of a tidal flat environment like we see today, where you find these kinds of exposed ripples and mud cracks. Overlying these basal tidal flat sediments with shales, you find the rest of the Table Mountain group is dominated by pure orthoquartzites, no shales whatsoever, and it makes up the rest of Table Mountain. And this is there is a fault over here, a place called Platteklip Gorge, which is the most popular hiking route to the top of Table Mountain. It's the shortest route, although it's also the steepest route, but it can take you about 4 hours, and it's a very nice climb on a nice day, because it's a kilometer high, right from the sea level right up to the top. It's a very spectacular mountain. So the quartzites that make up Table Mountain are very clean orthoquartzites characterized by a planar cross bedding, and we can recognize that in terms of what we see in the rocks. We interpret what we see in the rocks, and then we can interpret it in terms of processes and so on. Now, some of these diagrams I'm showing you here are taken from a book by John Compton, who is a professor at the University of Cape Town, and it's aimed at the general public for people to understand more about geology, and I will show you more about that book later on. So the rocks of the Table Mountain sandstones were interpreted to have been deposited in this kind of a setting, a barrier island adjacent to a continent. So there's a continent, this is a lagoon, here is a barrier island, and here is a flood tidal delta, and this is the kind of high energy environment in these barrier islands here. So this is a model that was published by Tankard et al. In 1982 or so, in which they suggest that you had this kind of a continent with conglomerates and river systems building out, and there is a high energy barrier island system with these very clean orthoquartzites forming here, and then these occasional flood tidal deltas and lagoons bringing in some finer material. So the rocks in the Cape supergroup illustrate the whole rock cycle. You can see the intrusive granites, you can see them being uplifted and eroded, and the sedimentation occurring, and you also saw deep burial of these Malmesbury turbidites which were melted to form the granite. So it's a very good area to illustrate this the rock cycle. So we have looked at this bottom part of the stratigraphic column. We looked at the Malmesbury group intruded by the Cape granites, and then the unconformity of the Cape supergroup with shales in a tidal flat environment at the bottom, and then these peninsular formation quartzites that make up the whole of Table Mountain. Now at the top of Table Mountain, at the very, very highest point of Table Mountain, about 100 years ago, in fact in 1905, our most famous paleontologist, Dr. Robert Broom, climbed up Table Mountain and walked to the highest point and discovered striated pebbles in a conglomerate, a quartz sandstone-rich conglomerate in which he found faceted and striated pebbles and announced the discovery of glacial rocks. So even back then there were skeptics, and one of the skeptics was a famous geologist, A.L. Dutoit. And Dutoit, the following week, climbed Table Mountain himself and went to the top and confirmed the discovery of these glacial rocks. Subsequently, a lot of exposures were found in the mainland, in the main Cape Fold Belt, of very thick glacial deposits, and it turns out that these are known elsewhere in the world, especially in North Africa and in places like Bolivia in South America. This is an Ordovician glaciation. It's the Hernantian glaciation in the late Ordovician. So there are glacial rocks here at the top in the Puck-Hayes Formation, and then we can see a reconstruction in this diagram of the ice sheets that would have been present based on the occurrence of these glacial rocks elsewhere within the Cape supergroup, and the reconstruction of a lobe of this late Ordovician ice sheet during this glacial event. Now the Table Mountain group is then overlain by the shales and quartzites of the Bockerveld group, and within the Bockerveld group we find the first macroscopic fossils in South African geological history. So we prior to that we had only Precambrian rocks with stromatolites. There were some soft-bodied animals that you find in the latest Ediacaran fauna in the late Neoproterozoic, but the first hard shelly fossils like these brachiopods that you see here, these are found in the Table Mountain group, and following that you can see here the Cederberg Formation. Let me just show you here. Just overlying those glacial rocks in this formation, which is still part of the Table Mountain group, we find these fossils, these brachiopods, and here are photographs of them. This is also well known in places like the Falkland Islands, the Malvinas, and in other places. And so this kind of fauna has got the name Malvino-Caffric fauna. It's named after the fact that it occurs in the region of eastern of South Africa called Caffraria and the Malvinas. And so we have trilobites as well that have been found in these fossils assemblages. And here is a reconstruction of the kind of ecology of these animals on the sea floor at that time in the late Ordovician to Silurian. So here are some well-known examples of these fossils. In fact, the first trilobite that was found in South Africa was found in the 1830s and sent by Sir William Herschel, who was the astronomer royal at the Cape, and it was sent to the president of the Geological Society in London, who was none other than Murchison, and Murchison announced the discovery of Paleozoic rocks in the Cape supergroup already by the 1830s. So it's well known just from the biostratigraphy that these rocks are Paleozoic in age. We also have wonderful fossils like these starfish that also occur within the Cape supergroup. So overlying the Table Mountain group, we have the Bokkeveld group and the Witteberg, in which all these fossils occur. Now, interestingly, at the end of the sedimentation of the Cape supergroup, you had another big glaciation, which marks the beginning of the Karoo supergroup. And this is the famous Pan-Gondwana Dwika glaciation, which occurred throughout all the Gondwana continental fragments. But shortly after the deposition of these Dwika tellites and some of the Eka group rocks at the base of the Karoo supergroup, they started getting deformed. So there was the Cape orogeny that happened very shortly after this initial glaciation, and it folded the whole of the Cape supergroup into a series of spectacular folds, which forms this Cape fold belt. And here is a digital elevation model of the Southern Cape region, where you can see the topography due to the folding of this Cape supergroup, and the folds extend east to west for about 400 or 500 kilometers, and then make a sharp turn in this region and go more or less north-south in this area. So in Cape Town, the Table Mountain rocks appear flat and undeformed, but it's only because it happens to be the bottom of a regional fold, because you go just across the Cape Flats from here to there, and these rocks are dipping steeply to the east. So it's just a coincidence, fortunate one for Cape Town, that those rocks are sort of horizontal at that point. They are not undeformed. They are part of a big regional fold belt. And here we can see in the passes going through the Cape fold belt the deformed quartzites of the Table Mountain group, and vertically dipping or very steeply dipping rocks in the foreground, with more shallowly dipping rocks in the background that you can see over here. So it's a very spectacular fold belt. And of course, you have the equivalent of this particular set of rocks, the Cape supergroup, and the folding in South America, in Argentina, the Sierra de las Ventanas in Argentina, which are also Paleozoic quartzite, same kinds of fossils that are found in them, and the same kind of deformation. And I'll mention that later on, because the first person to link, well, not the first person, but actually the one who really highlighted the link between South America and Africa was Alex Tutoy. And Alex Tutoy was actually invited to spend several months in South America, and he came to Brazil and Argentina and I think Uruguay, where he spent several months looking at the geology, the Paraná, and so on, and compared that with South African geology and produced a geological map of that. And that's what led to his ideas in support of continental drift, and he was vindicated many years later. So here are some spectacularly folded Cape supergroup rocks in some of the very spectacular passes through the Cape fold belt, the Swartberg Pass being one of the most spectacular. And here we can see even overturned folds within these quartzites. Here is one over here. There's an overturned fold that you can see here, like that, in the Swartberg Pass. And here's some more beautifully folded rocks at a place called Meringspoort. So for some reason then, there was a folding of the Cape fold belt after it was deposited, and we don't know the exact reasons, because the other portions of this orogenic system then drifted away and are now sitting in South America. So we really need to have a project to really look in detail at all the dates, and it all depends on exactly how that configuration was, and we need to, in order to understand what was happening in the Cape fold belt. So, but the Cape Fold Belt and the very bottom part, the earliest deposited sediments of the Karoo Basin, which are the glacial rocks, were folded. And the Cape Fold Belt was then uplifted, and the erosional products were then deposited in the Karoo Basin, which was forming as a foreland basin adjacent to this developing Cape Fold Belt. So the famous South African geologist Alex du Toit, he was one of the first to recognize that the sort of continental drift hypothesis of Wegener could be tested by looking at the continuity of rocks from one continental fragment to another. And he was actually invited by the then director of the Carnegie Institution in Washington, D.C., to spend several months in South America, and that's what he did. And after having seen, because Alex du Toit was a field geologist first and foremost, he was probably the greatest field geologist that we have ever seen. He spent the first 15 years of his life mapping the entire Cape and the southern Karoo region, you know, back in the earliest decades of the 20th century. Before they had aerial photographs, he had to make his own topographic maps. Luckily, he had the skills to be a surveyor as well as a geologist, and he did a lot of his mapping on horseback, because he could only then cover huge areas, but he really knew those rocks very, very well because of his field experience. And having seen those rocks, he was the person who went up the next week after Broom's discovery of glacial rocks on Table Mountain, climbed up that mountain, which is a 4 or 5 hour hike, and just to confirm those things. So he was the best person to go to South America and look at rocks like the Sierra de las Ventanas and recognize that these are exactly the same rocks as he had mapped in the Cape Fold Belt with the same kinds of fossils and so on. So it was his field experience with the rocks that convinced him about the reality of continental drift, and the fact that the Cape Fold Belt rocks were folded, the Cape Supergroup rocks, and the Sierra de las Ventanas was folded and was overlain by the glacial rocks of the Karoo and the equivalent rocks in South America. That's what really convinced him about this interpretation. And he also knew that there were similar rocks in Australia, for example. He didn't know very much about Antarctica. The Antarctic rocks had not yet been described, but he, in terms of the fit of the continents, he was very prescient in producing this kind of a map, and he called this the Samfrau orogenic belt, because it stands for South America, and Africa and Australia. So Samfrau is the name that du Toit gave to this orogenic belt on the south of this postulated supercontinent called Gondwana. And remember, this was happening long before anybody else in the world had even accepted that there was such a thing as continental drift. And in North America, there was major opposition to the idea that there was any continental drift. So du Toit was almost alone in postulating this. But what is interesting about du Toit, he was a staunch supporter of Wegener, and in the University of Cape Town, in their library, which I visited last month, the geological library in the University of Cape Town is called the Alex du Toit Library. And in that library, they have a precious volume. They have du Toit, they have Wegener's Die Entstehung der Kontinenten, the origin of the continents by Wegener, in which he first came up with the continental drift idea. And that volume is inscribed personally by Wegener to du Toit. So du Toit certainly appreciated Wegener's ideas, and Wegener in turn appreciated the support that he got from du Toit. But there were people way ahead of their times, because it took another 50 years or so before the ideas were vindicated in the plate tectonics revolution. So I want to end by just showing you this cover of this book by Professor John Compton, from the University of Cape Town, and it is a popular book about the rocks and mountains of Cape Town. And I have to acknowledge that I got a lot of the diagrams for this presentation out of his book. It is still in press and can still be obtained probably through booksellers or through the Geological Society of South Africa. Okay, so we will continue in our next lecture about Gondwana. And just to finish the story about the evolution of the Cape Mountain of the Cape region from Professor Compton's book, following the Cape orogeny, which basically led to the, it was still part of Gondwana. Then eventually the continents broke up, and you had another passive margin, which is the present-day passive margin that was developed on top of this Saldanian belt and the deformed Cape fold belt and so on. So this would be the present-day continental margin of the Southern Cape region that you see today. And I'll stop there for now and take questions. Yeah, South America. The SAMFRAU stands for South America, Africa, Australia. It's an abbreviation, an acronym, if you like. But it's the orogenic belt that extends along there.
Okay, thank you very much, Shaddad. Yeah, we have a question here. Diana, nós temos uma pergunta aqui da audiência. A Diana está controlando as perguntas de fora.
A minha dúvida é sobre a ocorrência de pórfiro, copper gold deposits nesse cinturão, porque na Austrália tem, né? Na costa leste da Austrália você tem várias mineralizações de ouro e cobre associadas a essa deformação e entrada de pórfiros, né? Gostaria de saber se na África tem, ou na América do Sul também se continua a mineralização associada.
So he wants to know is that some porphyry copper in Australia, and which is related with this assembly. So is there any evidence for porphyry coppers in this place, and that would be of your knowledge?
So if you look at this reconstruction of Tutui, this would be the margin of Australia in which the porphyry copper deposits would be found. But as I pointed out in one of the earlier maps, South Africa is actually very far away from that actual margin of Gondwana, from the southern margin of Gondwana. So because it was more like a back arc basin, and on the edge of that back arc basin was and then whatever events were happening in that arc region that led to compression, led to the formation of the Cape. So in the Cape fold belt there are no intrusive rocks at all, even after the deformation. In the pre-Cape rocks, which are part of the Saldanian belt, which was on the active margin of Gondwana after it was formed, the Cape granites do have some mineralization associated with them, but it's tin mineralization. We have a number of prospects for tin, and in fact, in the late 19th century, there was also some gold that was found right on the slopes of Lion's Head in Cape Town itself. But and there was a small tin mine in the upper suburbs of Cape Town, within the Malmesbury schists, where they are intruded by the Cape granites. But we don't have any porphyry type copper mineralization.
Bom, a resposta é que não há mineralizações associadas a porphyry copper, porque na verdade nesse tempo a África do Sul estava relativamente distante dessa latitude, mais associada a um ambiente do tipo back arc. Existem algumas mineralizações associadas ao Cape Granite, que na verdade são anteriores a esse evento, mas são mineralizações de estanho e houve também alguma mineralização de ouro, mas não há mineralizações associadas a porphyry coppers nessa região. Tem alguma pergunta vindo de fora? Por enquanto não. Mais alguma pergunta aqui dos colegas? Ok, vamos esperar um pouquinho para ver que a gente ainda tem um tempo. São 10:14. What is the age of the fold belt, the Cape folded belt? What is the age of the formation and metamorphism? Estou perguntando qual é a idade, qual é a idade da deformação do cinturão dobrado do cabo.
The Cape fold belt is roughly around 300 million years. That's roughly the age of the Duiker glaciation, and the Duiker rocks were deposited first and then folded so shortly after the deposition of the Duiker group that these rocks were folded. So I will show you in the next lecture the folding of the Duiker rocks.
The deposition of the Peru sediments.
Yeah.
When they start the deposition, the very
Yeah. It's around 300 million years. That's the age of the Duiker glaciation. Yeah.
Também perguntei quando é que começou a deposição da bacia de Karoo, e ele falou que é em torno de 300 milhões de anos, que é mais ou menos a mesma idade da formação do cinturão dobrado do cabo. O que eu acho interessante é que, por exemplo, ao mesmo tempo, né, aqui no Brasil, a gente tinha uma situação bem diferente, né? A gente tinha uma situação de formação já das bacias, já, né, em estágio até avançado, da formação das bacias paleozoicas, no caso da bacia do Paraná, né? Começou a se formar no Ordoviciano, Câmara-Ordoviciano, né? Então, há 300 milhões de anos já existia uma deposição grande, uma história de deposição grande dentro dessas bacias, né, sem nenhum tipo de deformação, enquanto que lá no Cabo estava havendo ainda essa compressão que gerou o dobramento que ele mostrou, o sistema de dobramento do Cabo. At that stage, about 300 million years ago, we had no deformation in South America, I mean in Brazil. So the Paraná Basin sedimentation started about the Ordovician, and then we have this completely intercratonic setting with no deformation at all. As far as I know, the last evidence for some sort of deformation comes from the Dom Feliciano belt, which would be about 540. So it's a totally different story. But we had compression here, and a craton that was completely stable, and deposition of this huge amount of sediments in the Paraná Basin. I don't know if you want to comment this.
Well, I suppose it's more or less similar in South Africa as well, because the deformation really affects only the Cape supergroup rocks and the very, very southern part of the Karoo Basin. The rest of the Karoo Basin is undeformed. So it's only the Karoo Basin where the Karoo rocks lie directly on the Cape fold belt that have been deformed. So and it seems like the Karoo was deposited in a foreland basin related to the Cape fold belt, but then the rest of the Karoo Basin shallows, the deepest part, the 4 deep of the Karoo Basin is adjacent to the Cape fold belt, and then it shallows and just sits directly on the craton, and it's completely undeformed. Well, I'll show you in the next lecture.
Ele falou que na verdade a situação não é tão diferente assim, porque essa deformação está muito restrita a essa porção sul da bacia, que é onde está o sistema de dobramento do cabo, né? Mas a bacia mesmo, né, a bacia do Karoo está completamente livre de nessa mesma época ficou completamente livre de qualquer tipo de deformação, né? Eu não sei quanto aos planos da Diana com relação a coffee break. Ok, so I have a question coming from. A pergunta vem de Brasília. Ok. Okay. Is there any evidence of contact metamorphism involving the Cape granite and the overlying sedimentary rocks?
No, not at all. The Cape granites are intruded into the Malmesbury group, which is of the part of the Saldanian belt, and there that's the famous exposures you see in Cape Town, which are very well studied. They've got cordierite, hornfelsers, and so on. Very beautiful contact metamorphic exposures. But then it was uplifted and eroded before the Cape, and the Cape supergroup rocks are then completely, younger rocks, so they are not intruded by the Cape granites at all.
As evidências para metamorfismo de contato não estão na sequência clássica do Cape Group, mas na sequência que está diretamente sobreposta ao granito do cabo, né? Aí tem hornfels com cordierita e tal, mas as siliciclásticas do Cape Group não foram afetadas porque elas não chegaram a ser intrudidas pelo granito do cabo. Vamos. Hoje são 5 aulas, vamos para a última, então eu só estou preocupado com o horário do coffee break. Já está pronto? Porque a gente começou um pouquinho, mas se já está pronto, então vamos responder essa pergunta. Vamos para o coffee break rapidinho e volta para 21. Ok, vamos. Oi? São menores? Beleza, então. Ótimo. Então vamos responder Teresina. Quem é? Renato de Teresina. Das faixas do cabo. Então a faixa do cabo que deve estar... Como se deu a formação? Intracratônica. So the Serra de la Ventana sequence and the Cape folded system. Can they be related to some sort of intracratonic orogeny?
I'm not sure about, I don't know enough about South American geology to be able to comment on that. But I think if you look at the terrains to the south, those are all the terrains in Patagonia and so on, which have got a lot of intrusive granites of Paleozoic sort of age, which we do not find in the Cape at all. So it's all part of the orogenic belt that was to the south of Gondwana, and some of that history we do not record in the Cape fold belt. So, but there must be something happening in a back arc environment which is producing this Cape orogeny. Because when you reconstruct Gondwana, that is what you see. You see an arc to the south rather than a collision zone. So the deformation has to be in a retro-arc environment, some kind of a retro-arc compression relating to a subduction zone to the south of Gondwana, and that compression is also then producing this retro-arc foreland basin in which the Karoo supergroup is deposited.
Ele não conhece muito sobre a geologia da América do Sul, então não fica muito confortável em responder, mas de qualquer maneira, se a gente for mais para a geologia da África do Sul, o ambiente remete mais a uma zona de subducção com compressão, né, em ambiente de retroarco e formação de uma bacia do tipo foreland, onde o Karoo supergroup teria sido depositado. Então acho que a rigor, pelo meu entendimento, né, não existiria, pelo menos do lado africano, não existiria nenhuma evidência para uma orogenia do tipo intracratônica, né, já que toda a margem sul do Gondwana naquela época era associada a uma zona de subducção. Ok?
Explain that in this diagram, which is actually from the next lecture, but it does show this whole evolution I'm talking about. So initially we had, during the Pan-African, we had Africa and the collision with South America, producing this Pan-African belt over here, the Saldanian belt, if you like, intruded by the Cape Granites. That was followed by some back arc extension, and on that passive margin of the African continent is where the Cape supergroup was deposited, and I suppose the Serra de la Ventana would have been the same. And then something happened, still in a back arc environment, but compression that then deforms these Cape rocks and produces the foreland basin, but in this back arc or retro arc sort of setting. And that is what the best explanation that we can come up with for the Cape orogeny.
O professor retomou, na verdade ele apresentou um slide que os colegas, essa pergunta veio de Teresina, que você falou, né? O pessoal lá de Teresina deve estar vendo, na verdade esse slide é da próxima apresentação, mas ele mostra basicamente o modelo geodinâmico que ele apresenta para esse local que está associado à África do Sul e à Serra da Ventana lá na Argentina, no sul do Brasil, na América do Sul, desculpa. E segundo ele, a Serra da Ventana deve estar associado a essa compressão, né, que ele mostra ele como Pan-African Belt no slide, no segundo slide, acima para baixo, né, a Serra da Ventana deve estar associado a essa compressão associada ao fechamento daquele back arc basin ali onde está o Cape Sedimentation no slide. Então, de novo, né, só para demonstrar que não é nenhum tipo de modelo relacionado à orogenia intracratônica, né? Está associado realmente a uma zona de subducção e compressão num ambiente retroarco, ok? Bom, espero que as perguntas tenham sido respondidas a contento. Vamos fazer uma pausa de 15 a 20 minutinhos para o coffee break e a gente retorna para continuar até 1h da tarde. Tá legal, Diana, assim? Beleza? Ok. I'm going to make a break now for the coffee and then come back and go up to 1 o'clock, okay? Thank you, Sharad.
Okay, welcome back after the coffee break, and we will now go on to lecture 21, the rocks of Gondwana 2, the Karoo supergroup. So, in the last lecture we discussed the Cape supergroup, which was formed on the southern edge of the African continent due to a passive margin that was formed by some kind of extension behind the magmatic arc that was formed on the southern edge of Gondwana. Now we are concerned with what follows from that, the Karoo supergroup, which is deposited in a much larger part of South Africa. It covers about maybe 2/3 of the surface area of South Africa. And the Karoo basin is formed in a retro-arc foreland basin behind the Cape fold belt and the active margin to the south of that, which would now be the Falkland Plateau. So there was some kind of compression that folded the Cape Mountains, and the weight of this fold belt being thrust onto the sort of the older basement rocks actually depressed that basement and produced a sagging of the lithosphere, and that produced a foreland basin with the deepest part, the 4 deep, very close to the edge of the Cape Fold Mountains. But then the basin shallows as you go to the north, and especially when you get onto the Kapval Craton, which is an Archean craton with a very thick lithosphere, and it's very difficult to depress an Archean craton. Much easier to depress the lithosphere immediately to the north of the Cape Fold Belt, which is occupied by the Namakwa-Natal Belt, which is a Mesoporozoic orogenic belt, which itself was thrust onto the Kapval Craton. So the Cape supergroup, the Karoo supergroup, then follows on from the Cape supergroup, and I've shown you this diagram before in discussion of the last lecture, but we will just go through this again to summarize the development of the Cape and the Karoo basins. So in the Neoporozoic, we had collision between South America and Africa, and a creation of a Pan-African belt with the Saldanian sedimentary rocks and the Cape granites that were formed in this kind of an arc-related environment. But then in the early Paleozoic, we had extension in the back arc basin and formation of a passive margin on the southern edge of the African continent, where we had deposition of the Cape supergroup rocks, and the equivalent rocks in South America are the Sierra de las Ventanas. Then there was renewed compression, and we don't know the reasons why there was extension and then compression, but there was renewed compression, perhaps due to some event which we don't see in South Africa. It's all happening in this magmatic arc in the Falklands Plateau, and that produces the Cape Fold Belt, the Cape orogeny, and produces the Karoo foreland basin in a retroarc environment. And the final phase of the Karoo is at 180 million years ago, 183 million years, where we see the vast eruption of the volcanic rocks and associated intrusive dikes and soils that make up the Karoo large igneous province. And it has been related to, by at least some people, to a large mantle plume that then preceded and may have caused the breakup of Gondwana. And there were, of course, other plumes as well, like the Parana Etendeka plume, which is slightly younger at 140 million years. So this cartoon kind of summarizes that history from about 500 to about 180 million years. Okay, so let's look at the Cape, the Karoo Basin in relation to the Cape Fold Belt. So the Cape Fold Belt is shown in the blue colors here, and you can see that the Karoo rocks overlie this Cape Fold Belt, and in the southern part of the Karoo Basin down here, even the Karoo rocks have been affected by deformation in the Cape orogeny. So the Cape orogeny actually continues even after deposition of the Karoo rocks. The Karoo rocks, however, are thickest in the trough adjacent to this, so it's some kind of a foreland basin, but in this retroarc kind of environment. The Karoo Basin then thins along its strike going to the north until it pinches out when you're on the Kapval Craton itself. And then once you get onto the Craton, there are other Karoo rocks all over southern Africa and central Africa, which were all deposited in rift basins. So the Karoo has got the main Karoo Basin, which is the one we see in South Africa, was deposited in a big, let me just show you, this basin here is deposited in this foreland basin, deepest to the south and thinning out. But then you have other Karoo basins like this one on the border with Mozambique, this one here, the Springbok, and there are many others in Namibia, in Botswana, in Zimbabwe, extending all the way north towards Tanzania, we have rocks of the same age, the same kinds of fossils as well, which were deposited in specific rift basins. Okay, so the first thing that occurs in the Karoo Basin is this major glaciation that involves all the Gondwana continents. And in South Africa, we see the Cape Mountains here, which the Cape sort of mountain belt must have had a big extensive ice sheet here as well. And to the north, there was a highland region which has been termed the Cargonian Highlands, where there was certainly a big ice sheet, and that carried detritus to the south. So there are a lot of striated pavements beneath the Dwaika sediments of the Dwaika glacial sediments, which give us the directions of movement of the ice sheets. So this is in the Northern Cape region near Kimberley, for example. I've worked on these ones, and they certainly give this direction. In KwaZulu-Natal, we see almost north-south directions of the ice sheet going south like that. But interestingly, we can infer, although we don't see any striated pavements in the Cape fold belt down here because these Karoo rocks have been folded, we don't see the striations, but we infer from the clast composition that some of the Dwaika rocks were actually coming from the south as well. And this is very interesting because some of the components that we find in the Dwaika glacial rocks, I had a student a few years ago who studied the composition of the clasts here, and we found clasts that came from the Bushveld complex, from the Ventersdorp supergroup. We could match them geochemically, and they came from the north. That was not a problem. But in the same region where those clasts that were found that came from the north, other people found clasts, fossils that contain fossils, archaeocyathids. Now, an archaeocyatid is something that looks like a coral, but it's a creature that lived in the oceans and went extinct at the end of the Cambrian. So archaeocyathids are only found in the Cambrian. And in South Africa, we do not have any Cambrian rocks. And the nearest place where you will find archaeocyathids is in Antarctica. So if you do the Gondwana reconstruction, Antarctica would have been somewhere in here, and there are places, several places in Antarctica where the archaeocyathids have been found. So it would suggest that there was material coming from the south, brought in by these glaciers, mixing with material coming from the north. So this is quite an interesting story. And there are increasing studies of looking at detrital zircons as well in these. It's just beginning now. We don't have any results yet, but we will expect to find a lot of additional new information about that. So this would be one of the striated pavements. You can see here lots of glacial striations and this kind of smooth surface. This is the pavement in Nooitgedacht near Kimberley in the Northern Cape region. It's at the base of the Dwaika ice sheet. So we basically can infer that this is a major continental ice sheet which produced very spectacular landforms, roches-moutonnées and things like that, and left behind major moraines full of boulders and so on. And this debris, which makes up the tillites, can be very, very thick. It could be about 100 meters thick in some places where it is quarried as building stone. Durban on the east coast. So we had major continental ice sheets during this time, because now we know that if we read the paleogeography and the paleoposition of Gondwana, it was really moving over the south polar regions. So this would be a polar cap similar to what we see in Antarctica today, which is about 2 kilometers thick. Within this Dwaika, then at the base of the Karoo supergroup, we see these massive tillites with huge boulders Some of them could be meters in size, and a whole different size fraction going down to tiny grains. And when you look carefully at these clasts, you can see plenty of evidence for faceted and striated pebbles indicating a glacial origin. These tillites, in fact, were known since 1799. That was the first description of these tillites. And in the early half of the 19th century, people thought that this was some kind of a volcanic rock because it has these very strange textures. It looks like a pyroclastic rock with big bombs, and they just could not explain it in any other way. So, it was only in the late 19th century, by about the 1870s, when it was already recognized that similar rocks occur in the Tarsier beds and in Australia as well. That certain people who had worked in those other places realized that what they're looking at here is in fact a glacial of glacial origin. And then the spectacular striated pavements were discovered, and then there was no doubt about it at all. One of the people who worked a lot on these Dwika published a major paper, that was Alex Tutue. So this is what the Southern Cape region would have looked like during this Dwika glaciation, because we had major glaciers, and just north of the what became the Cape Fold Belt, it was already developing a deep trough. So we have evidence of glacial marine sedimentation. So the glaciers were basically breaking free from this continental ice cap and into a floating ice shelf, which was then melting with glaciers and producing drop stones and producing big boulders in a glacial marine sort of environment. So you can see things like this, big drop stones sitting within these proglacial sediments formed by melting icebergs. So a lot of work has been done on these glacial deposits by people like Visser and others in South Africa. We also can see proglacial turbidites that are forming in this proglacial environment due to the meltwaters coming from these glaciers and producing turbidites in a deep water kind of setting. Now the Dwika group, after the glaciation had ended, and it ended basically by the continents drifting away from the polar regions, so the climate was getting slightly warmer, and as the glaciers receded, you started to form the Cape Mountain Belt. So the mountains were rising up, and you started to form turbidity currents, and to the south of the Cape, then you started to raise this mountain belt due to those events going on in the Falklands Plateau to the south of South Africa. So you basically developed a deep water trough in the southern part of this Karoo ocean, or the Karoo Sea, but to the south there was land rising, and there were of course the continental highlands to the north. So for some reason my photograph didn't come out. What I did have here is a photograph showing folded turbidites within the Eka group that overlies the Dwika tillites. So that would be something like this portion of the diagram, where following the Dwika glaciation you still had folding, but the folding is confined entirely to the very southern part of the Karoo Basin. Only in this part here, the rest of the Karoo Basin is not folded, so the folding dies out as you go to the north, and then it's just flat-lying and undeformed. So here we see flat-lying turbidites close to Laingsburg, and Laingsburg is a place where you see the last of the Karoo deformation. So it's basically dies out over just a few kilometers, and then the rest of the Karoo is actually quite flat-lying. So this area here, where you have lots of deep water turbidites formed in the Eka group, is an area with a very beautifully exposed deep water setting. And so there's been a lot of interest in this area from oil companies, because oil companies want to know when you're looking in an offshore environment, deep water turbidites are a major habitat for oil, especially when you're looking at channeled sandstones. Within these, there are good oil traps. But usually, most of the information comes from 3D seismics on the continental shelves, where they don't have access to the rocks themselves. If you want to study the rocks, then you want to see one of these deep water offshore settings exposed on surface. The Karoo Basin is the most accessible deep water turbidite facies, the least deformed and most accessible one that you can see anywhere. And so a lot of work has been done on understanding the three-dimensional architecture of these deep water turbidite systems in the Karoo Basin in the southern Karoo near Laingsburg. Now, in the north of the Karoo Basin, what you had was the development of swamps on the edge of that Karoo Sea. You had little deltaic sedimentation happening, and lots of meandering rivers bringing in lots of muddy waters, and lots of vegetation which was deposited in swamps. And this gave rise to very extensive deposits of coal that we see developed as the major coal fields of South Africa. They are found in the Eka group in KwaZulu-Natal and in the Transvaal Highveld. So the coal fields of South Africa are our major resource. South Africa is one of the largest exporters of coal in the world, and it's also one of the largest producers for internal consumption. 80% of South Africa's energy requirements come from coal-fired thermal power stations. So coal is a very important part of our economy. We wish we had large rivers like you have in Brazil, where you could have big hydroelectric schemes. We don't have large rivers. South Africa is a very dry country, and coal provides most of the energy source. It is controversial now because of the environmental issues related to coal, things like the carbon footprint, the CO2 emissions, and so on. And when you have coal-fired power stations, and we have the largest carbon footprint in the whole of Africa. South Africa is the largest polluter, if you like, in terms of coal CO2 emissions. But we have no alternative until we can develop an alternative energy sector through renewable energy resources and nuclear energy. We do have one nuclear power station in South Africa, north of Cape Town, called Koeberg, and there are plans to build several more nuclear power stations along the coast in South Africa. But the nuclear option is also controversial for environmental reasons. The coal seams that you find in the Karoo Basin have a unique flora, which is only confined to the Gondwana continents. It is a southern Gondwana flora, which is very famous, the so-called Glossopteris flora, the Glossopteris flora. And the name itself, Glossopteris, which means a tongue, like your tongue in your mouth, the tongue wing. So it's shaped like a wing or a tongue, and that's what gave its rise to this particular form which you see here in this fossil photograph. Glossopteris, there's another one called Gangamopteris. This is Glossopteris, and that's Gangamopteris over there. So this flora is unique to the Gondwana continents, but it's also very characteristic. So you can find the same flora in India, in the coal fields, which are of Karoo age. You find it in Antarctica, you find it in Australia, and in South America. So the Glossopteris flora is very well known and characteristic of this time period in the Eka that's forming in the early Permian. The Eka group, which was deposited to the south in deep water turbidites, and to the north in these sort of deltaic swamp environments where the coal seams were formed, is then followed by the Beaufort group, which makes up about half of the sedimentary succession in the Karoo. It's a very extensive group where, in terms of paleogeography, most of the sedimentary sources were from the south, from the uplifted and eroding Cape Fold Mountains. So you had braided rivers coming from alluvial fans and so on in these mountain chains from the south, and even in South America in the west, and it gave rise to braided rivers, which eventually changed to more meandering rivers and feeding into a basin which started to shrink. So it went from a marine basin in Eka times, in Dwaika and Eka times, where you had open marine conditions. You find marine fish fossils in there as well, and it eventually became a continental basin with completely cut off from the sea, and it became a shallow lacustrine sedimentation, and this basin continued to shrink throughout the history of the Karoo Basin. So you're simply filling the available accommodation space that was created by the foreland basin due to the Cape orogeny. So this was basically a foreland basin that was filling up. And as it was filling up, it was shrinking in size. And we know very well the paleogeography of what was going on during sedimentation from the fauna that we see in the Cape supergroup. I will come to that in a minute, but the fauna are extremely interesting because we have some of the best terrestrial fossil record for this Mesozoic time period in Earth history. Nowhere else in the world is there such an abundance and such a wide variety and over such a large area of fossils. So the Karoo is a treasure house of evolutionary history in the Mesozoic time period on the continents. And we find in the Karoo the evidence for the oldest tortoises, some of the oldest amphibians. We see the earliest mammals, and even the earliest dinosaurs. They're all found in the Karoo Basin. So it is, because of the wide variety of different fossils, this is the first basin in which we can use biostratigraphy to subdivide the rock types, and because of the specific living habits of different animals. Like if you're an amphibian, you're living on the shoreline, and we can track where the shoreline was by looking at the distribution of the amphibians within the developing Beaufort group. So the Beaufort stratigraphy, the Beaufort group is just completely dominated by sandstones. And the depositional environments coming in from the mountains, you see braided rivers, and then it becomes meandering river systems with mainly sandstones and some mudstones in the overbank sort of areas. So it's a fairly simple kind of depositional system, but sourced in the south and moving towards the north. So the Beaufort group then leaves behind deposits of sandstones and mudstones, basically channelized sandstone deposits surrounded by floodplain deposits which were made up of the mudstones. And one thing that we do have in the Beaufort group is some mineralization, and the mineralization is in the form of sediment-hosted uranium deposits together with small amounts of molybdenite, and this is stratiform mineralization where you find sandstones with channels, and in the channels you have lots of organic matter that is trapped, and the uranium is trapped by the organic matter. So there were fluids moving through these sandstones that had picked up uranium and molybdenum, and they were migrating and being trapped in areas with high uranium contents. Now, in the 1970s, there was a boom in uranium exploration. This was before Chernobyl, before 3 Mile Island, which put a stop to uranium in the 1980s and 90s. But in the 70s, there was a big boom in uranium, and the first thing that the government did was radiometric surveys, where they found radiometric anomalies in the southern Karoo, which they followed up, and they discovered that it was due to this kind of mineralization in these channels. So this kind of uranium is somehow related to unconformity type. It's not quite in the unconformities, but it's related to sand uranium, like you find in the Colorado Plateau, the roll front kind of deposits I showed on Monday. And these things were a lot of work was done, exploration work and so on, by both the government and by private companies. But then the uranium, after Chernobyl, price fell down and the whole market disappeared for a couple of decades. But then the uranium price went up again in the 2000s, in the late 90s, because of the end of the Cold War. And what had happened at the end of the Cold War is America and Russia had reached an agreement for disarming the big nuclear stockpile that was in the Soviet Union. And when the Soviet Union broke up into different countries, Russia actually took all the stockpile of all the nuclear weapons that were in the other countries, Ukraine and Kazakhstan and all these other places, and they actually reached an agreement that they would disarm all those weapons and use the uranium for and make it available for use in nuclear power reactors. But that stockpile started to come to an end. There were predictions about what would happen when that Russian stockpile of uranium would finally end, and then there would be a huge shortage in the market, because countries like France are 80% dependent on nuclear power, the way that South Africa is dependent on coal. And so France is one of the major countries that's involved in exploration for uranium. And many companies realized that there was going to be a shortfall in uranium, and that spurred the current boom in uranium exploration that we have seen in the last decade or so, especially prior to 2008, and led to new discoveries, but also to rediscovering the old places like the Karoo Basin, where the uranium was known in the 70s. And today there is now a mine that has started, the first mine in the Karoo Basin, mining these Karoo sandstone hosted uranium deposits. What is interesting though is that I've looked at the hydrothermal geochemistry of molybdenum, because I'm interested in that. It occurs in the stratabound copper deposits and so on. And when you look at molybdenum chemistry, everything that we know about how the hydrothermal chemistry of molybdenum is that it is only soluble at high temperatures as various kinds of complexes, but whatever complex you want, its solubility is highest at about 350 degrees, and it falls to about 250 degrees, and that is why you get porphyry moly, copper moly deposits deposited out of hydrothermal solutions, magmatic hydrothermal solutions at high temperatures. And all the fluid inclusion studies in porphyry systems show the temperatures of deposition between 350 and 250 degrees centigrade. And from the experimental work done on molybdenum chemistry, it shows that there is very low solubility of molybdenum at low temperatures. Now there's been work done on the diagenesis of the Karoo sediments here. These are undeformed Karoo sediments. In the Cape Fold Belt even, the temperatures that were reached were just something like 150 degrees centigrade in the Fold Mountains, and to the north it's practically unmetamorphosed. So the question then is, what kind of fluids were involved in these sandstone-hosted uranium of molybdenum deposits? And I can only come up with one solution. The uranium and the molybdenum had to be transported as organometallic complexes. Now we know about organometallic complexes for lead, zinc, and many other metals. We don't know anything about molybdenum organometallic complexes, but I predict, this is my prediction, anybody who's a chemist here who wants to do this study can prove me wrong, but I predict that you will find that there are low temperature organometallic complexes of molybdenum, because I can't see any other way of transporting molybdenum in these low temperature fluids that are involved with this. There is a strong association with organic matter. So there is organic matter present, and perhaps there is some organic involvement. We know that things like oil, like black shales, have got a lot of molybdenum in them, and perhaps the molybdenum is actually migrating in oil or hydrocarbons, and then the uranium comes in separately, and just reacts with a molybdenum-bearing hydrocarbon. I don't know, but something of that sort. It has to be low temperature, but we don't know enough about molybdenum chemistry at low temperatures. It's just, I'm sorry I went off the topic completely, but this is the only thing that is of economic interest in these Beaufort group sandstones. So we have other sandstones within this Beaufort group, and what is interesting in the Beaufort group is that we see the Permian-Triassic boundary, and it is one of the few places in the world where you can see that PT boundary in continental sediments. So there's a lot of interest in this because, you know, in the marine record, it's very, very clear there is a major mass extinction that can be seen and very clearly. And there's still huge arguments about what caused the Permo-Triassic mass extinction. But here in South Africa, we find also evidence of big climate change. Coal disappears completely from the rock record after this KT boundary, the PT boundary. And there are also mass extinctions that can be recognized in the continental fossil record, but you don't see it as sharp as you see in the marine. And some paleontologists think that some of the animals started to die before you actually reach the PT boundary. But there are big problems with actually locating this boundary in the field, because there is no real marker horizon associated with the boundary. So one of the things, sorry, if I just go back here, one of the environmental things that we can see is that braided streams replace meandering stream deposits, and it's been argued that it's maybe the result of the dying out of vegetation, and that there is more erosion, and that's changing the style of the river sedimentation as a result of that mass extinction. But these are speculations. So I'll just show you some of the fantastic fossil fauna that we see in the Karoo supergroup. This is a dicynodont, and these kinds of fossils were first found in the 19th century, and they were sent originally to the British Museum because there were no real paleontologists in South Africa at that time. Now we have the finest collection of fossils in the entire southern hemisphere. That in my university there is the Bernard Price Institute of Paleontology, which has the largest fossil collection in the southern hemisphere. There is another very big one with the South African Museum in Cape Town, and the Geological Survey, or the Council for Geoscience, has its own paleontological collections as well. So we have an unrivaled collection of fossils from this time period, and researchers come from all over the world to study these and to compare them with what they have in their own countries. So, and there are also very nice museum displays of all of these fossils in some of the major museums in South Africa. The South African Museum in Cape Town has a wonderful display, an entire floor devoted to the fossil fauna and flora of South Africa, with nice reconstructions like you see over here. Here is another one. This one is in our own museum, this Gorgonopsian, and this is a very, very characteristic predator with this huge tooth, kind of a enlarged tooth, and this particular animal here is in our museum at Wits University, the reconstruction. And then there is another group of dinocephalians that you see here reconstructed, also in our museum, and this is what some of the fossils that have been prepared look like now. So it is on the basis of fossils like this. This was the person who actually prepared and actually found this particular fossil, and we have a fantastic museum. And the one thing that our government has recognized is that our fossil record is unique, and it's something that needs to be preserved, and they have put a lot of money into conservation and into museums and in actually preserving this fossil record. So as you go higher up in the Karoo stratigraphy, above the Beaufort group, we have the Molteno formation of the Stromberg group, and the basin is shrinking. And remember that it's a lacustrine basin; it's getting smaller and smaller all the time, and there is a change in the sort of depositional environment slowly, and it's getting drier slowly as well. And here we see evidence of deposition by braided rivers, and we do see some small coal seams here in the Molteno in localized swamp environments. And some of these coal fields were worked in the 19th century in the Eastern Cape region, and they're now being looked at again, and we're trying to resume some of the mining in these Upper Karoo coal fields of the Stormberg group. We also find red beds associated with these overlying. That is the Elliott Formation, and here you can see in situ in one of our national parks vertebra of possibly a big dinosaur that's still in situ in the rocks. And we also find in these some of the earliest dinosaurs, and we find we have found the oldest dinosaur eggs, including some that have a perfectly preserved embryo in there of Massospondylus. So there's a lot of very spectacular fossil fauna that we have in the Karoo Basin. And here is the final sedimentary unit in the Karoo Basin, which is called the Clarence Formation. This is again in the Golden Gate National Park, and this is the most famous outcrop there, this spectacular cliff of Aeolian sandstone. And so here we see what was happening. There was a progressive drying out, progressive filling up of the basin. It was getting, the lacustrine basins were getting smaller and smaller until eventually you probably reached a very flat environment, somewhat like the Kalahari Basin today, the Kalahari Desert, with a few pans, isolated pans like that, and lots of dunes. So there was desert dunes and dune sedimentation in the interior as this basin had become completely filled, and it had become progressively arid. And so eventually what you see is this basin then filling up, and the last event that you see in the Karoo Basin is a major outpouring of lava. So the basin had sort of become arid, and then suddenly there is an outpouring of lavas still while the dunes are still being deposited. So the very base of the Drakensberg lavas, which make up the final phase of the Karoo, the volcanic phase, the initial flood basalts are interbedded with Aeolian sediments. So that you have a lava flow, and then you have dunes moving over that, and then some more lava flows, and so on. And I know that in the Parana-Etendeka basin, we have similar things at the very base. In Namibia, in the Etendeka, you have the same thing. You have lava flows interbedded with Aeolian sediments, and it may be the same in the Parana, I'm not sure, the Bokutaku formation. So here we see a spectacular and well-known exposure, because it's right on the main road as you go from Johannesburg to Cape Town, to Durban rather. You pass this isolated sort of a mesa of Karoo rocks, the Upper Karoo Clarence Formation, and then you see at the very top of this hill this beautiful columnar jointed rock, and it was. We always thought it was a sill, and in a lot of the literature it's regarded as a sill, but the Geological Survey has mapped it as a lava flow. So this is the lowermost Karoo lavas directly sitting on these Aeolian sandstones and actually interbedded with it as well. And associated with this huge plume of Karoo rocks, there were lots of feeder dikes. The Karoo Basin is full of lavas, of dikes and sills that are cutting through at various angles. You can see one exposed nicely in the Golden Gate National Park, where you see a Karoo dolerite dike cutting through the Elliott Formation. And this is a geological map of, it's a detailed geological map, 1 in 250,000, of the southern part of the Karoo Basin, where you can see the outcrop pattern of all these red sills. and the sills are not just sub-horizontal, but some of them form circular features, which you can see over here. They are kind of lopoliths, or something like that, which are quite interesting. And there is a group from Norway which has been working a lot on the physics of volcanic processes, and they have been very interested in studying what's going on in terms of the intrusive processes resulting in these kinds of things, and the interaction between the volcanics and the sediments. They also have very interesting interactions, and so on. So this is an area with active study going on, with several groups who are working on this. It's a very well exposed and very easily accessible rocks that you see in the Karoo Basin. So the final part of the Karoo then is the huge outpouring of the Drakensberg flood basalts at 182 million years. It's part of the Karoo Large Igneous Province, and here we see them in the high Drakensberg Mountains, which are the highest part of South Africa. They are elevated at above 3,000 meters. The highest point in southern Africa is about 3,300 or so meters above sea level. So this uplift is fairly recent in origin. It was maybe in the last 30 million years ago that the whole of southern Africa was uplifted, and it's being eroded at a spectacular rate. So I will end there and say, well, the main reference for this section is the book McCarthy and Rubidge, from which most of the images that I used came from in this study. So this is the book that was put together by the Wits University Geology Department. Okay.
Thank you very much, Sharad. Nós temos uma pergunta vinda de fora. Peraí. Marcelo Januário de Souza. Marcelo é de Brasília. So we have a question from Brasília, and Marcelo wants to know if there is any sort of graphite mineralization associated with the coal field formations in Quasa. Is there any graphite associated with these coal fields? Yes, in Quasa. How do you call that? Yeah, that's right. Yeah.
No, there is no graphite there at all, because the metamorphic grades are too low. These are practically unmetamorphosed sedimentary rocks. So the only thing that you do find is that the Karoo dikes in the late Karoo, related to the Large Igneous Province, they cut through the coal fields as well. Lots of them, and they're a major nuisance because they then thermally alter the coal, and they burn the coal for about a meter or two away from the dike, and they have major effects in terms of mining and so on. But now they're using geophysics to predict the location of these dikes ahead of mining. They're using radar, borehole radar and things like that, so they can plan better where to expect to find these dikes in the coal fields. But there is no graphite at all.
Não existe, porque a temperatura nunca foi suficientemente alta para formar depósitos de grafita, né? Esses depósitos não estão, as rochas que contêm esses depósitos não estão metamorfizadas, então não se formou grafita. O que acontece é que em alguns casos os diques cortam os depósitos de carvão, e isso traz problemas para as companhias que mineram o carvão. Então o que eles estão fazendo ultimamente eles estão utilizando recursos da geofísica para localizar esses diques e assim poder planejar melhor a lavra, né, desses depósitos de carvão. Ok? A Diana saiu agora, eu estou sozinho, vamos ver aqui, mas eu não estou recebendo nenhuma pergunta de fora. Se tiver alguém, se alguém quiser fazer alguma pergunta aqui, o Cláudio, claro. Cláudio, a gente está fazendo o seguinte, a gente está fazendo a pergunta em português para os colegas entenderem. Se você quiser, você mesmo faz em inglês, tá bom? Mas primeiro sempre em português.
Tá bom. Então Então a minha pergunta é em relação a duas coisas. Uma, se aquelas mineralizações de urânio e molibdênio que você cita como possivelmente resultado de transporte em complexos orgânicos, se não teria, quer dizer, é interessante isso porque é diferente do urânio e vanádio, né, no típico roll front, né? E se teria outros elementos associados que pudessem justificar esse transporte por complexos orgânicos, por exemplo, ouro, né? Bom, a outra pergunta é assim.
So we have two questions here from Claudio Porto, and the first question is regarding the uranium molybdenium mineralization. Okay, so is there any evidence for they're a bit different from the mineralizations associated with vanadium, and he found it very interesting that you associated them with the organic some sort of organic transport or deposition. So he wants to know if there is any other sort of metal, maybe gold, associated with this uranium and molybdenium.
Yes, in fact there is, but there is some gold that is found, but not associated with the uranium and moly mineralization. A very small gold field in the Cape, within the Cape Fold Belt, and it was mined in the 1870s, a long time ago, 150 years ago, and it was a proclaimed gold field, but then very low grades, not very continuous, and then they discovered all the rich gold deposits in the interior, and everybody abandoned the gold field and they went to make money elsewhere. But I've actually done some work in those abandoned gold fields, and there's just quartz veins with sulfides in them, and they are found in the pre-Cape rocks, in the Cape supergroup, in the white quartzites, and also in the Karoo rocks. And there is in fact a study done on fluid inclusions in the Karoo rocks near Prince Albert, where they found temperatures again about not very high temperatures, 150 degrees, maybe something like that, which is consistent with an origin during the Cape folding. And that Cape orogeny produced some fluids which were migrated through the Cape rocks as just into the foreland basin, into the Karoo rocks. And so there's some minor gold mineralization there. And there was also some fluid inclusion studies done on the uranium deposits. Were also fairly low temperature, the same kinds of low temperature fluids. And there were studies done on the clay mineralogy within the Cape Fold Belts, which show that there weren't very high temperatures either. So we can see that there was probably low temperature fluids mobilized during the Cape folding, and not very high temperatures, not any magmatism at all involved in this. So it's just low temperature fluids, but they've picked up, some fluids have picked up gold, others with uranium and moly. The molybdenum may be related to a source. I mean, it would have to be something like black shales or whatever. We don't really have any black shales in the Cape. In the Cape supergroup, it's just quartzites. But perhaps in the turbidites of the Saldanhian belt, where we find gold-bearing veins, maybe some of that material could have been mobilized, could have mobilized uranium together with molybdenum in these low-temperature fluids. But again, we have to explain the hydrothermal geochemistry of low-temperature fluids to explain the molybdenum.
Bom, com relação ao depósito de urânio e molibdênio, não tem ouro associado, né? Existem pequenos depósitos de ouro associados, mas pequenos depósitos de ouro que foram explorados há mais de 150 anos atrás, mas esses depósitos de ouro estão associados aos processos de formação do cinturão dobrado do cabo, né? Então são veios que cortam as sequências siliciclásticas posteriores, como os quartzitos, por exemplo. O que ele comentou é que houve estudos de inclusões fluidas que mostraram que os fluidos associados à deposição desse ouro são também fluidos de baixa temperatura, né? Mas, de uma maneira geral, não há nenhum outro tipo de metal como o ouro, por exemplo, associado à formação do molibdênio. Uma coisa intrigante também é que ele esperaria que o molibdênio tivesse relacionado a folhelhos, por exemplo, né? E, no entanto, não há folhelhos nessa região. Vou passar para a segunda pergunta do Cláudio. Ele tinha duas perguntas para fazer. Se quiser fazer.
Uma outra pergunta é se a paleogeografia da Karoo Basin se liga com a bacia do Paraná de alguma maneira. Essa é a minha ignorância, assim, do ponto de vista da distribuição das bacias. Now I'm talking about the link between the Karoo Basin and the Paraná Basin, if there was any in the paleogeographic reconstruction, or if these were two completely separate basins.
I think the Paraná Basin is younger than the Karoo Basin, because the Paraná Etendeka lavas are 140 million years. The Karoo Basin ends by 180 million years. So the Paraná is actually a younger basin. There is a link with the Etendeka formation, which is in Namibia, but it's just in Namibia only. And the Etendeka lavas are only found in Namibia and not in South Africa, and they are 40 million years younger than the Karoo lavas.
São bacias separadas, né? Bom, agora a gente tem uma pergunta. Oi, que a gente tem uma pergunta de fora. Eu vou tentar privilegiar o pessoal que está fora, Felipe. Bom, tem uma pergunta que o Paulo, que eu acho de Brasília, mandou por e-mail. Eu estou sozinho aqui agora, Paulo, não estou conseguindo abrir e-mail ao mesmo tempo. De qualquer maneira, caso eu não consiga, a gente... Belo Horizonte, desculpa. A gente manda depois a resposta. Mas tem uma pergunta que veio do Douglas. O Douglas é de Teresina. E, de novo, tem a ver com os depósitos de molibdênio e urânio. Acerca dos depósitos de urânio e molibdênio de Beaufort, do grupo Beaufort, nos arenitos, é possível sugerir modelos de um sistema único de deposição dos dois elementos ao mesmo tempo, e também seria possível sistemas separados, um depois o outro. Além disso, qual seria a distribuição espacial desses elementos no depósito? Okay, so I have again a question related to the uranium moly deposits. So the question is, were the deposits, both elements, were they formed at the same time, or they were formed at different times? And the other question is, fica dançando aqui. And what is their special distribution in the area? Are they together, separate, or so?
For the first question, whether the uranium and the molybdenum were together or separate, it's not clear. As I said, we know a lot about how molybdenum is transported, but we know very little about how molybdenum is transported in low temperature fluids. So there are two possibilities as far as I can see. One is that both molybdenum and uranium are transported together, but in that case they both have to be transported in an organic rich fluid, as an organometallic complex, because you would need to transport the molybdenum as an organometallic complex. Another possibility is that the molybdenum is actually associated with hydrocarbons, as in some kind of organometallic complex, but that the hydrocarbons are sitting in the aquifers, in the sandstones, maybe derived from shale diagenesis or whatever, but the uranium then is coming in separately in another form, maybe in some other soluble form, but not necessarily an organometallic complex. It could be a chloride complex, for example, but then it gets reduced by encountering the organic matter that's in the sandstones, and it just so happens to have moly in it, so that the association then in the end is uranium and moly, but they may have separate origins. But there's not enough work that has been done to study this problem in the Karoo. All the exploration for these deposits was done in the 70s, and there have been no modern studies. Although there is a report that was published by Wiplinger and Cole on the uranium moly mineralization in the Karoo by the Council for Geoscience. There is a published publication. It gives the distribution and the sedimentological features and so on, but does not go into the geochemistry of how you form those deposits. So the second part of the question was, is there a special distribution of these deposits in the Beaufort group? And the answer is yes. The deposits are found only in the very southern part of the Karoo Basin, closest to the Cape Fold Belt. And it's only in those sandstones that you see the uranium. So again, it supports the idea that the fluids are coming from the Cape Fold Belt and moving northwards, and they are encountering reducing situations in these sandstones where the organic matter is. And then further north there are no fluids, and so there's no uranium mineralization.
Ok, então vamos lá. Eu vou tentar responder primeiro com relação à distribuição espacial. Eles estão todos concentrados na parte sul, muito próximos ao cinturão dobrado do Cabo, né? E com relação ao depósito, a formação conjunta ou separada, ele enfatizou que não há muitos trabalhos ainda sobre isso, mas que então as duas hipóteses podem ser aceitas. No caso deles serem depositados juntos, né, ele acredita que isso teria que envolver algum tipo de fluido associado a uma origem orgânica, né? Eles teriam que ser transportados juntos, né? Então se transporta o urânio e transporta o molibdênio também por fluidos com algum tipo de matéria orgânica associada. Outra possibilidade é que o urânio fosse transportado separadamente do molibdênio, talvez por alguma fase rica em cloro, uma fase fluida rica em cloro, e depois, quando passasse pelas camadas que são ricas em matéria orgânica, essa solução seria reduzida com a deposição do urânio, e aí talvez isso conseguisse envolver alguma deposição de molibdênio também, que estaria dentro dessas camadas que são mais ricas em matéria orgânica, tá? Tem uma outra pergunta também sobre isso, que é o tamanho dos depósitos, e essa pergunta vem do Marcelo Souza, que é de... O Marcelo é de Brasília. So we have another question regarding the uranium moly, and people seem to have liked it very much. So, and it comes from Marcelo from Brasília, and he wants to know about the size of these deposits. The size.
I couldn't help you on that score. I don't know. I haven't the slightest clue about the size, but all I can say is that it's economic because they are starting to mine. And a few years ago, before 2008, there was a bit of a mini boom in exploration, and a lot of very poor farmers made a lot of money by selling their farmhouses to mining companies to use as exploration headquarters. So there are quite a few deposits that were discovered originally in the 70s, and they have been put on ice. Basically, they were not economic, but now they are. So, but I can't tell you about the size or the grade. I don't know.
Infelizmente ele não conhece, ele não sabe sobre o tamanho dos depósitos, mas ele sabe que esses são depósitos economicamente viáveis. Houve um boom na década de 60, ele explicou durante a palestra, principalmente relacionado à necessidade de urânio para a produção, né, de artefatos nucleares. E aí ele comentou aqui que alguns fazendeiros até ficaram conseguindo fazer dinheiro porque se associaram a essas companhias mineradoras. Depois esses depósitos foram esquecidos e agora estão sendo retomados. Existem projetos que estão tendo início mais recentemente nessas áreas que estão mineralizadas em urânio e molibdênio. Então ele, apesar de não saber o tamanho dos depósitos, ele sabe que eles são economicamente viáveis. Eu tenho uma pergunta aqui do Paulo que eu vou... Espera aí. A pergunta do Paulo eu vou responder depois, Paulo, porque eu vou abrir um pouquinho aqui o espaço para o pessoal que está aqui, tá legal? Então vou fazer mais 2 perguntas só. Ok, tem uma outra pergunta dura aqui vamos lá. Essa vem do Edson, que é lá de BH. Aí depois eu passo para você, Felipe, tá? Aí a gente encerra para continuar até 1h. A pergunta que vem do Edson, da Sureg BH, ele gostaria de saber se há correlação cronológica entre os fósseis da Chapada do Araripe, no nordeste do Brasil, com os fósseis encontrados no Karoo. Okay, that's a tough one, okay? So we have a colleague in Belo Horizonte, and he wants to know if there is any sort of chronological correlation between the fossils that are found in northeast Brazil in the Araripe plateau and with those fossils found in Karoo. I'm not sure if you're aware of the fossils in the Araripe. So.
No, I'm sorry, I don't know about that.
I think I'm not a paleontologist,
Yes.
but I think they're mostly fish. I'm not sure if não sei se alguém aqui sabe. Tem dinossauros também, é claro.
No, I won't be able to answer that question because I know very little about Karoo fossils and even less about the correlations with other areas in the world. Okay. I'm not a paleontologist, sorry.
Okay. Então essa a gente vai ficar devendo pro Edson, tá bom? Vamos para a pergunta do Felipe. Fala. Ok. So is there any correlation that comes from Felipe? It's that any correlation between the coal fields in South Africa, Namibia, and in Mozambique?
Yes, in terms of the timing, they're all formed in the Eka group, which is immediately overlying the Dwaika glaciation. So you can actually follow them all the way through to Tanzania. It's more or less the same time period for the coal formation throughout the Karoo in the whole of southern and central Africa.
Existe sim uma correlação. A bacia do Karoo se estende, na verdade, né, por Moçambique, e esses depósitos de carvão estão associados, sim. Ana.
Só para saber se essas lavas da província Karoo são também recobertas por riolitos, como no Brasil e no Etendeca, não sei.
Okay. These Karoo lavas, they're mostly basaltic, but are they covered by felsic flows like rhyolites and rhyodicites as we have in Namibia and in Brazil, in Paraná as well?
In the main Karoo Basin, where we saw the final slide in the Drakensberg Mountains, there are only basaltic lava flows. But if we went to, let me see if I can find that first map. We find in the Libombo Basin, which is on the border between South Africa and Mozambique, we have very extensive rhyolites as well as mafic volcanic rocks. But it's only in this part here. This area here is the Libombo Mountains on the border with Mozambique, and there we find a lot of felsic volcanic rocks as well, rhyolites. But in the main Karoo Basin, these ones, the Drakensberg formation, we don't find any felsic volcanic rocks.
Então elas não são encontradas na bacia propriamente dita, dentro do supergrupo Karoo. Esses derrames do que ele chama aqui do grupo Drakensberg não tem as félsicas, mas quando a bacia se aproxima da fronteira com Moçambique, aí aparecem derrames de riolitos. Uma última pergunta do Carlos Eduardo e aí a gente encerra.
Sérgio, é sobre os carvões. Na realidade é uma curiosidade, eu queria saber a qualidade dos carvões e o teor de enxofre.
So the question is about the coal, okay? So the colleague wants to know about the quality of this coal and the amount of sulfur, for instance.
Well, there are many different factors to consider when you're looking at coal quality. One of them is the rank of the coal. Is it brown coal? Coking coal, anthracite. So it's all coking coal as far as the rank. So there's no brown coals. It's all been buried to high enough temperatures to have nice coking coal. But only in the very north of the Karoo Basin, close to the contact, in fact here, close to the contact with the lavas, in this northernmost part of the Karoo Basin, you find some anthracite, some higher grade coals. The main Karoo Basin coals are all coking coals, and they generally tend to have high sulfur. Actually, they're not that good quality coals, but we have no choice but to use them. But there are different variations within different coal seams, and also the ash content varies quite a lot. So we are mining the best quality, the thickest seams in the Karoo Basin. But obviously, as these are being depleted, we have to mine other seams which are less good quality. But of course, it also depends on what the final end product use is for the coals. In South Africa, we actually are world leaders in the technology of oil from coal. This was something developed during the days of apartheid, when there was a lot of sanctions, and South Africa, having no oil deposits of its own, was vulnerable to any sanctions. So they decided then to try to find some alternate energy source. And one of the things they did was pumped in a lot of research money into developing a method of producing oil from coal. And we have a state oil company, Sasol, which is a world leader in this whole technology. So in fact, we are now exporting that technology to places like China, where they have a lot of coal reserves as well. And so that requires a specific type of coal, whereas which has probably a higher quality than the thermal coal, which is used mainly for our power stations. So we use the lower quality coals for our thermal power stations, which account for 80% of our use. And we also export a lot of coal, which is higher grade, higher quality coals. But we also have to ensure that there is enough supply for our own use. And currently we are constructing 2 very large coal-fired thermal power stations, because the energy supply in South Africa is at a critical stage, and there have been huge blackouts and so on. So we have to have, within the next 10 years, new sources of thermal power. But so the coals do vary quite a lot in their quality, and there are many different coal seams, and there are some deeper coals. There's also a lot of potential for coal bed methane. That is just to get methane out, that is in a deeper coal seams, which are too sub-economic to mine. But I forgot to mention that the biggest debate going on right now in South Africa is about fracking of coal. That is to fracture the hydraulically fracture coal and get gas from that. There is currently no fracking going on in the country, but Shell oil applied for a license to do fracking in the southern Karoo Basin. And that stimulated a huge response from environmental groups who are totally opposed to this thing. But then it started a debate in scientific circles as well. The fact is that we have only 5 boreholes that go through the entire Karoo Basin in the southern part where it's deepest. And we have really no idea whether there is any economic potential. There are a few places where some oil has been found, gas, but at the current state of knowledge, all we can say is, well, because of the Cape orogeny and the fact that there's a deep basin there, it's possible that it could have generated hydrocarbons, and therefore there is a potential there. But we do not know whether there's going to be any real possibility of getting gas. However, the US Geological Survey, they did a study of worldwide hydrocarbon potential. And I've worked with them and I know how they work. But they published a report a few years ago in which it suggested that there's something like, 400 trillion cubic feet of gas potential for the southern Karoo Basin from fracking. And that has started this whole debate. Now, the South African state-owned parastatal organizations involved in petroleum exploration, Petro SA, they have done a study in which they reduced that USGS figure by 90%, but it's still a significant amount of potential. But it's still at this stage only potential, and but immediately after all these civil demonstrations against fracking, the South African government put a moratorium on fracking, and they stopped all licenses until they could get more information. And then now there are a lot of scientific studies underway. It spurred a lot of research in the universities in the Cape region. And what they've recently done is they've ended the moratorium and allowed there are 2 companies or 3 companies now that have applied for prospecting licenses, allowed them to go ahead with the work, because even if they find something, it'll be 10 or 15 years before there's any actual production. But they have to weigh the cost of environmental protection versus economic development. And the Southern Cape region is a very impoverished area with very poor communities and rich farmers. So the farmers don't want any fracking on their lands, but the communities are impoverished. The government has to do something and find a balance. But at this stage, actually nobody has any idea if there is any economic gas deposits there. But maybe in the future it will be.
Então vamos lá. Primeiro é basicamente carvão de coque, né? Tem alguns antracitos nos lugares onde a temperatura se elevou mais. O conteúdo de enxofre é alto, ok? Então basicamente o que eles fazem eles precisam muito, a África do Sul precisa muito de queimar esse carvão para gerar energia. Então eles consomem boa parte desse carvão, mas também exportam. E ele considera que o que é exportado, vamos dizer assim, é o carvão de melhor qualidade. A segunda coisa, eu estou resumindo um pouco, a segunda coisa é que no passado foi colocado muito dinheiro em pesquisa para produzir petróleo, óleo e gás a partir do carvão. Então é uma tecnologia que é dominada só pela África do Sul, e que ela hoje está exportando essa tecnologia também. Outra coisa que ele comentou é o fraturamento desses depósitos para aproveitamento de gás metano, né, que também tem sido feito. Com relação a isso, tem havido recentemente muitos problemas pelas organizações, né, de defesa de meio ambiente. Então, apesar de ter existido alguns anos atrás uma corrida, né, teve um relatório do Serviço Geológico dos Estados Unidos, por exemplo, que estimou em as reservas de hidrocarbonetos na bacia de Caru, estimou em números muito elevados. Depois houve uma reavaliação pelo governo sul-americano desses números, eles foram reduzidos em cerca de 90%, mas assim mesmo ainda existiria muito hidrocarboneto para ser explorado dentro da bacia do Caru. Mas existem 6 ou 7, meia dúzia apenas de poços que perfuraram a bacia, então o conhecimento geológico, a rigor, nesse momento é muito pequeno para se saber se algum tipo de exploração da bacia para hidrocarbonetos seria economicamente viável, né? Existem áreas, né, que são basicamente divididas entre grandes fazendeiros e populações bem pobres, e o governo de alguma maneira vai ter que encontrar uma maneira de balancear esses interesses, né? Porque especialmente com relação ao craqueamento, ao fraturamento das camadas dentro da bacia que poderiam conter gás, né? É o shale gas, né? Porque os fazendeiros não querem isso, os agricultores ricos não querem isso, mas obviamente toda a população pobre que ocupa basicamente a vizinhança, né? De alguma maneira estaria interessada em que isso acontecesse, porque isso gera, né, trabalho e renda. Ok, so we're closing for questions now. Vamos fechar para as perguntas agora. A Dayana voltou, que bom. E vou pedir para a Dayana de novo recolher as perguntas que a gente não conseguiu. Tem uma que veio do Paulo, de BH. Não, porque ele mandou pelo e-mail. Aí a gente vai compilar essa também para passar para o professor. Eu acho que sim, que foi a do urânio e molibdênio, não é isso? Essa foi respondida, tá bom? Então vamos lá, a gente respondeu do Douglas, eu acho que só ficou de fora a do Paulo que veio, que respondeu a do Edson também, a gente só faltou responder a do Paulo que veio por e-mail, tá bom? Aí a gente, até onde eu tô lembrado, tá bom? Ah, tá, o Paulo está dizendo aqui que essa é a mesma, então a gente já respondeu do Paulo também, porque o Paulo está dizendo que a do Edson é a mesma que ele mandou por e-mail, tá? Então não precisa, tá ótimo. Mas de qualquer maneira, se houver... Marcelo de Brasília, acho que respondemos. Qual é a pergunta que está aí no teu... Eu acho que respondemos sim, me diz mais ou menos qual é. É do ouro, a gente respondeu do ouro. Já respondemos essas também. Então a gente respondeu todas. Ok? Eu acho que sim, beleza. Estamos ficando eficientes demais, isso é ruim. São 12:12, então a gente vai até 1h agora. Vamos passar para 22, é isso? É a que está em tela agora. 20. Next lecture is this one here. Yeah. Vamos para 22 hoje. Agora, perdão, a gente almoça de umas 2, volta, aí na parte da tarde tem a 23 e a 24. We're going to have lecture 23 and 24 in the afternoon. And that's it. Is that correct? Okay. Just 2 more to go. Okay. Yes, this one we're going up to 1 o'clock, then we go for lunch, and but it's okay because... That's okay because we have plenty of time to ask questions. I will have actually some questions regarding this lecture 21, but I'll tell you what I'm going to do. I will leave it for the end of this lecture and then we can discuss this, okay? Eu tenho umas perguntas sobre essa aula 21, porque eu acho que o professor vem falando desde o início do curso, desde que ele começou a abordar o arqueano, sobre a relação entre a atmosfera, a biosfera e os processos litosféricos, né? E esse vulcanismo de Caru é um vulcanismo muito volumoso, então eu acho que seria interessante ele comentar algo sobre que efeitos esse vulcanismo pode ter tido sobre a biosfera e a atmosfera há cerca de 180 milhões de anos atrás. Mas eu vou deixar isso para perguntar no finalzinho dessa aula 22. Tá legal, turma? Beleza? Ok.
Okay, so let's continue. with lecture 22 on the breakup of Gondwana and particularly the Karoo and Paranaitendeka large igneous provinces. Now, what I want to do in this lecture is not give you the great details about all of these things, but just introduce again another controversy that is happening in the world of tectonics, or in terms of interpretation. So we have established how the Karoo Basin was formed, and we saw that the Karoo at the end had a huge outpouring of flood basalts, the Karoo lavas, which you see on this geological map is this purple unit here at the very top of the sort of almost layer cake stratigraphy that you see in the Karoo Basin. Now, you can see that the succeeding units are getting smaller and smaller, and that's because there is in fact a very elevated topography here. So it's actually like a big mountain chain, and you can see a little country here. This is Lesotho. The whole of Lesotho is completely surrounded by South Africa, because it's a last refuge for the Basotho people when they fled the Boers as they came in the 19th century, and the British who were in KwaZulu-Natal, and they kind of fled to the mountains and eventually sought help from the British to save their country, and it became a British protectorate until it became an independent country in 1968. So a large part of Lesotho is actually these Drakensberg Mountains, but we also have them along the Libombo chain that we see here, where you also find the rhyolites, and you can see further to the north there are some areas with Karoo flood basalts in the northern part of South Africa, also in Zimbabwe and in Botswana, and under the cover in the Kalahari there is also a lot of Karoo volcanics in Botswana and Namibia. So it's a very large igneous province that extends, as I will show you in the next few photographs. So here we saw this big this view of the amphitheater in the Drakensberg Mountains. So this is in fact the border between South Africa and Lesotho. So the border is right there on that face. So this side is South Africa, and when you get into the mountains, that's Lesotho over there. And here is a spectacular view of one of these mountain streams making its way down to the sea. It's a spectacular escarpment that you see, because it was formed and is retreating by scarp retreat through massive erosion, because it's also an area that gets very high rainfall coming in from the Indian Ocean side. It's only about 100 kilometers between the coast and these high mountains going up to 3,000 meters. And so it gets all the rainfall, and there's very high rain and very, very wet conditions, and it's causing very rapid erosion, and it's also producing the spectacular exposures. But all of this is just basaltic lava flows that make up the spectacular Karoo volcanic province. But if you look at the distribution of Karoo rocks and volcanic rocks in the whole of southern Africa, you can see it's extremely widespread. So what I showed you just now was the Drakensberg mountains, which are in Lesotho, and that is just these Karoo volcanic rocks here. But there are also the Libombo province, and there are Karoo volcanic rocks all over Botswana, Namibia, Zimbabwe, extending into this part of Mozambique and into southern Malawi, into Zambia, and and there are also, in fact, they are known in Angola. This is a big question mark, but we know that there are Karoo rocks in Angola as well. So it's a very, very large igneous province extending over the whole of southern Africa, extending for perhaps about 5,000 kilometers in a diameter circle, radius, 5,000 kilometer diameter circle. And aside from the lava flows, the lava flows has been identified as low titanium, high titanium lava flows. There's also the abundant sills that are shown schematically here, that are intrusive into the Karoo sedimentary rocks that are very widespread. And there are also a few dike swarms that emanate from this region here, which has been regarded as one of the classic triple junctions by Burke and Dewey back in the early 70s. and there is a dike swarm that extends in this direction called the Okavango dike swarm, and in fact has been found to extend all the way to the coast in Angola over here. So it extends through northern Namibia and has been found in geophysics there, and in fact outcrops along the coast in Angola. So very, very extensive dike swarm here, and then there is another group of Karoo lavas which extends in this direction in Mozambique, and there is a third one which is the Libombo, like that. So this appears to be a classic triple junction, and of course if you put a tight Gondwana reconstruction here, then Antarctica used to sit over here, and bits of Antarctica have drifted away. And if you look at this Mozambique coastal plain, there's been a lot of oil exploration there. There are a number of seismic lines we have through these Cenozoic post-Cretaceous sedimentary rocks, and they show very extended crust, but these volcanics dipping off to the east, and they are fairly extensive over here, these Libombo volcanics, but it's underlain by very extended continental crust, which means that Antarctica would have fitted in much more tightly if you reconstruct and remove the extended deformation that you see over here during extension. So it means that this is a classic rift triple junction, like you see in the Afar region in Ethiopia. And but it's the two arms of this rift actually produced an ocean basin, which is the Indian Ocean, as Antarctica rifted away. The third arm is a failed arm, which is represented by this major dike swarm, the Okavango dike swarm. But and then there's just a lot of volcanism that you see throughout the Karoo. Now, the big question about the Karoo volcanic rocks is: are they related to a plume? Are they related to several plumes? Is there just one plume feeding all of this magnetism? There are regional variations you can see in terms of the lava compositions. These are there are low titanium lava flows, high titanium lava flows, mixed lava flows. Are they all the result of the same source? Are there different sources or not? And this is actually not settled. It's not a question that has now been settled. It's a question that is being actively debated. So this is really what I want to talk about. Is there a single source or multiple sources? Here is a map that shows in great detail the distribution of the mapped dikes related to the Okavango dike swarm and the Tuli-Sabi sort of region in Namibia, the Nwanetsi igneous province, as well as dikes that have been mapped in the Kafar Craton in South Africa in relation to the volcanic rocks of the Libombo extending into southern Mozambique and this whole region. So it's a very, very extensive zone. It seems to all focus in on this sort of central Tuli region in where these three sort of rifts have a junction, but it's still highly debated. And the debates are about what actually triggers rifting. Is rifting caused by a plume coming up, or is there rifting generated by some other process like stresses in the crust, and that then induces volcanism from underneath by decompression melting? And it is not a debate that has been settled, but increasingly there are a lot more people who are skeptical of the traditional view put forward originally by Jason Morgan in 1972 about plumes. But the classic view can be summarized in this diagram, that basically you have a plume that comes up from deep in the Earth's interior, and it is the plume that causes uplift, and that uplift then causes failure and tensional stretching of the crust and outpouring of lavas and sedimentation in these rifts, which eventually open up to form an ocean basin, and and that's how it works. Now, and what is the evidence for a deep origin of plumes? Well, there is not much seismic evidence, because we don't have the resolution in seismic imagery to image something as small as a plume with any accuracy, especially further down you go into the Earth's mantle. But the geochemical arguments based on the composition of volcanic rocks, and one of the important things is the presence of helium. Helium, when we look at helium, there's helium-4, which is the common form of helium, but there is helium-3, which is primordial helium. Helium-4 is radiogenic and can be produced by decay of uranium in the crust, but helium-3 is one of the primordial elements. It's not radiogenic, and helium-3 is an index of how primitive it is. It would have been a component of the original chondritic material that made up the Earth, but most of the helium throughout Earth history has been lost by degassing into outer space. And so if you find, so there is no helium-3 in the present atmosphere, but if you find volcanic rocks that have got helium-3, that's telling you that there's some primordial component in there, which can't be through the convecting upper mantle. It's got to be some deep source, and so people have suggested that there is some deep hidden source in the lower mantle that would be providing a source for helium-3. And so, but there's always been a kind of a, well, let's say a rivalry or some disagreement between geophysicists on the one hand and geochemists on the other hand. Geophysicists have their own models of what the Earth's interior looks like based on seismic properties of the Earth's mantle and core, whereas geochemists have a totally different view based on trying to reconcile what they see in terms of elements versus the chondritic model for the original Earth's composition. And one of the big problems is whether plumes come from the core mantle boundary or whether they are coming from a much shallower mantle. Plumes, the existence of plumes is not in doubt because there is a lot of volcanism that is focused in one place, and it forms radiating dike swarms and so on, like I've just shown you. So that it's not difficult to imagine that there is some centralized source from which these things could be spreading. But there is this big debate, and that debate is very much going on in the literature today. Now, I'll just show you, say, some kind of a classic view. This is from our book, which was published in 2005, about, say, this is the position of this Nuanetsi plume, and that produces a rift that eventually causes the breakup of Antarctica. So Antarctica breaks away, and there are these volcanic rocks that you see here in Mozambique that are formed as Antarctica rifts. And the Libombo then has to be a transform margin to allow for this kind of rifting to take place. So there is some kind of a transform fault system going on like this, and the Okavango dike swarm occupies this failed rift, the failed arm of this triple junction. And then this rifting sort of continues, and then a new strike slip faulting system starts to operate from here, so that the Falkland Plateau, which was adjacent to South Africa, then rifts away in a strike slip motion like this. So the entire Falkland Plateau then slides away as the South Atlantic also starts opening up. So there is, rifting that is orthogonal to the mid-ocean ridges, but also strike slip faulting, which are breaking away and slicing away pieces of crust in this direction. So the continental margin that is left behind in South Africa is a faulted strike slip margin on this side. It gives us a very narrow continental shelf in the south where most of our oil exploration is concentrated. But notice that we have a faulted margin in KwaZulu-Natal, and it's a very, very deep drop. Just from the continent straight down into abyssal plains, we'd have almost no continental margin there. It's a strike slip margin that we see on the east coast of South Africa. And that's because of this strike slip, dextral strike slip fault system that basically sliced away the Falklands Plateau from its position adjacent to the southeastern part of South Africa. Okay, so this is more or less the way that we have viewed plate tectonics in this way. This is the kind of reconstructions that are done from looking at magnetic anomalies on the sea floor by rotating continental fragments and so on. This is the stuff that Colin Reeves has done a great deal of work on, and if I can find it, I will try to show his presentation of his animation of Gondwana rifting. But the big question is whether the plumes that might be responsible for this kind of breakup, where do they come from? Are they deep or are they shallow? So here we see an extensive area of magmatism. We see the Karoo volcanic province, we see the Etendeka and the Parana volcanic provinces, and the Farrar dolerites in Antarctica are in fact extensive and across the Antarctic mountains. So, and then, well, there are other flood basalt provinces which we won't worry about, like the Deccan in India, which is much different age, 65 million years. So the big controversy that I just want to say a few words about is this controversy about plumes versus plates. What is it really that causes continental breakup? Is it the plumes that are coming from the deep mantle in the form of deep mantle plumes rising from the core mantle boundary and producing this kind of uplift that leads to rifting and then breakup? Or is it from that means a bottom-up view, a view that is coming from the bottom? So if we have this view of the Earth's mantle and core, we have the solid inner core, the liquid outer core, and then we have a source of deep plumes coming up. Slabs are sinking, and then there are areas of plumes that are coming up from the core mantle boundary and going up through the whole mantle and then rising up. Now I will just come back to this diagram, but I want to just show you the sort of classic models that people have used to explain rifting being generated by plumes. So the classic model is that a plume is coming up. A plume causes doming, it causes thinning of the lithosphere and stretching of the crust that leads to rifting, volcanism, sedimentation, and depending on the situation, it may either open up into a new ocean basin, or it remains as a failed kind of rift with a huge dike swarm running down the center, like we see with the Okavango dike swarm. So the problem is what is the actual cause of rifting? Is it a plume that comes up and then is formed at the base of the lithosphere, causes doming and then stretching? Or is it the other way around? Do we find stretching first for some other reason, which then induces the mantle to rise up and causes decompression, melting of the mantle, which then occupies the space created by faulting? So the rifting would be have a source in terms of stresses in the lithosphere for some plate tectonic reason, something to do with the movement of the lithospheric plates that produces interplate stresses and for at some point, whether there's some pre-existing weakness or whatever, it causes rifting apart, and that induces a magmatic event? Or is it the other way around, that a magmatic event caused by a plume coming up from the core mantle boundary or somewhere else in the mantle, is it the plume that's rising that is causing this? So this is a debate that is very much going on in the recent literature. And I will just tell you about a paper that was published last year by Frankie, who is from the GFZ in Potsdam in Germany, and the Germans have been doing a lot of work in the South Atlantic Ocean, looking at rifting processes, and what he's concerned with is this whole South Atlantic region and the rifting that is going on here. So they've done a lot of studies in this area and looking at the geophysics and looking at the drilling and comparing the sedimentary successions, looking at all the unconformities, trying to correlate the unconformities, and then trying to work out a tectonic model that can explain the timing of rifting in relation to the timing of magmatism. And his paper was published last year in, I think I've got the wrong version, because I'm sure I had a version in which I did actually put down the reference, but I seem to have lost it. But his paper was published in Marine and Petroleum Geology last year in 2013, and there is a website which I give here, the mantleplumes.org, which is a very good website to do with anything to do with mantle plumes and these large igneous provinces and the dike swarms and so on. It's the best place because it's a very active website that is always putting in a new data, new papers, and discussing them, writing discussion articles. It has a large igneous province of the month in which a lot of things are written up and so on. So I urge you to follow this website for the current status of these debates. But the argument put forward by Frankie in his paper is that he does not believe that the plumes have initiated the rifting, and the reason for that is if the plumes initiated the rifting, then the sequence of events should be first doming and perhaps unconformities related to an uplift over there, and then followed by igneous intrusion. And he sees things the other way around. Also, what he sees, and he had a diagram which I've had in another version. I'm sorry. He shows that if you had a plume coming up due to some effect coming from the mantle, the plume would be causing uplift, and if there is any magmatism associated with the plume, it should be there should be a maximum of magmatism close to the plume, and it should be dying away as you go away from the plume. So there should be a kind of a wedge where near the plume there is more rifting and more magmatism, and should be dying out along strike northwards and southwards from the plume. And what they find in their work is just the opposite. It's getting, if you see where the plume might be centered, it's actually getting wider away. There's more magmatism as you go away from what is supposed to be the plume center, because in this particular case, the rifting in the South Atlantic was related to the Tristan plume, the Tristan da Cunha plume, and they do not see this relationship. They see magmatism actually increasing as you go away from the Tristan plume. And the conclusion that they reach in this paper, and this is a big review paper about this whole story. He's got two different areas in the world, which he also discusses in this paper, about the relationship between the timing of plume activity versus rifting. And his conclusion is that he sees in all three cases, he sees evidence that there's rifting that precedes the arrival of a plume, therefore the plume can't be responsible for rifting. It's the other way around. So this is a strong indication that things are controlled from the top down rather than from the bottom up. And I urge you to read the papers, particularly of Don Anderson at Caltech. Anderson, for the last 10-15 years, has been a major critic of the whole plume model, saying that the plumes originate from the core mantle boundary. He does not like this story at all. Now I'll just go back to this one as well. But Anderson says this idea that the plumes come from the core mantle boundary is driven by geochemists who want to explain helium anomalies in volcanic rocks. So when you find ocean island basalts, they would be explained by a plume. So the classic plume model will apply to Hawaii to explain the younging of volcanism in the Hawaiian chain. So the plume is like a flame coming from the mantle, and the overlying plate, it's simply just riding over it, and it's producing this volcanic chain, getting older and older as you move away from the source of the plume. And it is in these ocean island basalts that the geochemists find these helium-3 anomalies. But a helium-3 anomaly is anomalously high helium-3 to helium-4 ratios. And he says everybody explains these anomalies in terms of an excess of helium-3, but you can form exactly the same anomaly by having less helium-4. So he has a completely alternative model to explain all of these features that people have argued are caused by deep mantle plumes. And he has been a strong critic of that. And he says, if you look at the original ideas of mantle plumes put forward by someone like Jason Morgan, then people started arguing on the basis of that model. But then other people came up with alternative evidence to show that model couldn't really work to explain certain other things. Then the believers in that model would modify the model to accommodate those exceptions, and the model becomes more complicated, but it can accommodate that. And then this has been going on for so long that he says now there is he calls this an immunization. It's like against some disease. So when you change your model to explain the criticism of your critics, you are immunizing your model against all controversy, and then the model grows in complexity until it can explain everything, including people who are talking about the upside down drainage model, where you have plumes coming from a particular spot, and then it hits the lithosphere and is deflected by the lithospheric mountains, if you like, in upside down drainage, and they end up about 1,000 kilometers away from where the center of the plume is supposed to be. So you can use a plume to explain anything you want using that model. So nothing can ever be disproved by having this kind of a model. Now what Don Anderson argues is that this is not science, because the scientific method, when you have an hypothesis in the scientific method, it has to be testable. And one of the main tests of any scientific hypothesis is the falsifiability of that hypothesis. You need to be able to find some evidence that falsifies an hypothesis. It's very difficult to find evidence to prove an hypothesis, because it only supports an hypothesis, does not prove it. Because a hypothesis postulates a number of things that would have happened, and the data that you get can be consistent with it, but it does not prove it. But if you find some piece of evidence that completely contradicts what this model supposes, then the model has to be wrong. The model is falsified by that model. Now, what Anderson has been arguing is that what's been happening in the literature over the last 3 or 4 decades about plumes is that the model has become immunized to all exceptions, and it incorporates those exceptions until the model can never be falsified. Because you come up with something and says this doesn't work, they will come up with an explanation that will make it work, under certain circumstances. So that is actually the problem. And I think similar criticisms have been leveled against the snowball Earth model as well. The snowball Earth model has now been growing in complexity to accommodate data that says there was a hydrological cycle operating. Okay, so we have a little refuge here that was open to water, but so your rocks were deposited in that one, everybody else's rocks were different. So this is a problem in geology. It's a general problem, I think, and we have to think seriously about what we do in geology and whether it's really scientific or not. So the plume controversy is a very, very big one. But it's not. It's definitely not over, because there is the latest tweak in the plume controversy is actually extremely exciting. It is the discovery of these large, low-velocity S-wave provinces sitting right on the core mantle boundary. That is, these areas that are shown here in orange, and they've been found from seismic work. Obviously, there's no other technique that'll look back that far down into the Earth's mantle. And there is a whole series of papers now by Trond Thorsvik, Kevin Burke, Bernard Steinberger, and others involved in this to explain these provinces. They are abbreviated as LLSVP. That's Large Low S Velocity Province. That's what it stands for. And it's because it is in the S velocity, in the seismic waves, where they see a low S velocity, so they have to explain it somehow. Now, whenever you have to explain changes in seismic velocities, there are two things that really change impedance in rocks. One of them is composition, the other one is temperature. And you cannot resolve that just by looking at the seismic data. You need to have some independent source of data, and for this, we don't really have an independent source of data, but it can't really be a thermal anomaly because it couldn't have lasted that long. And I will show you in a future lecture this afternoon when I talk about diamonds that this is very much alive, this whole idea about these large low velocity provinces, but it's also very, very exciting. So this is a paper from Kevin Burke in 2011 in Annual Reviews of Earth and Planetary Sciences, and in which he talks about the origin of these things, and he also says there is this affects the geoid, the shape of the Earth's sort of globe, and he thinks that we have evidence from Mars that there is something similar in Mars. In Mars, they don't call it the geoid, they call it the areoid, from Ares, from Mars. And Mars also has something similar, which is sort of fossil frozen above its core, which is something, a Martian equivalent of these low velocity provinces we see on Earth. Now, the basic idea behind these large low velocity provinces is that somehow they are very long-lived features on the core mantle boundary that have been there at least since the Paleozoic, but according to Kevin Burke, they could have been there since the moon forming event. That means since the Earth was formed. And on the margins of these things is what he calls the plume generation zone, the PGZ, and this is where you have, if you look at the plates, in terms of plate tectonics, we now have good evidence, even seismic evidence, that plates do not just end up in the upper mantle, but they cross the transition zone from 660 kilometers, and the plates can sink way down to the bottom of the mantle, right to the core mantle boundary. So, and we've known this for a long time, in fact since 1989, when people like Adam Jivonsky at Harvard showed the first seismic imaging results that showed the deep structure of the mantle. So this idea that subducted lithosphere actually ends up right at the core mantle boundary and then sort of piles up there where it forms a mass which then flows along this core mantle boundary until it hits one of these stationary low velocity zones and undergoes melting and generates new plumes that only rise up along these plume generation zones. So this is a new model. This is not the old model where the Earth is just generating plumes randomly from the core mantle boundary. This model says plumes are only generated at very specific places on the core mantle boundary, and that is on the edge of these large low velocity zones at these so-called plume generation zones. So this is a completely new model, but the model has been tested and published in numerous papers now by Torsvik, who is a paleomagneticist in Norway, and Kevin Burke, who is Mr. Earth. Kevin Burke knows everything. So I'm going to show you in the next paper, when we talk about diamonds, how they've used this model to explain the distribution and timing of kimberlites, which is very, very interesting. But I just wanted to highlight that there is a big debate going on about the timing of rifting, the source of plumes, and whether plumes generate rifts or do rifts initiate volcanism, but rifting caused by crustal processes rather than mantle processes. Okay, so we'll stop there now.
Thank you very much, Sharad. Nós temos uma pergunta já do Rafael Araújo. Ele é de Manaus e ele gostaria de saber como os mares internos do Gondwana foram afetados durante a formação do Pangeia no final do Paleozoico. So we have a question from Rafael coming from Manaus. And he wants to know how the internal seas were affected. I'm not sure what he means by affected, but maybe were rearranged maybe during the formation of Pangaea at the end of Paleozoic.
I'm not sure that I totally understand the question. Which internal seas is he referring to? Oh, okay. All right. Okay.
Eu também não entendi a pergunta, sinceramente. Eu não entendi como os mares internos foram afetados. Mas agora o Rafael também não está mais lá e o professor também não entendeu bem a pergunta. Eu ainda tentei traduzir o afetados por... Isso. Ok. Eu vou fazer alguns comentários. A gente tem 10 minutinhos. Tem alguém que quer fazer alguma pergunta aqui? Não? Bom, então enquanto não chega a pergunta de fora, eu vou fazer alguns comentários sobre essa... Oi? Ele ficou online? Pede para ele refazer a pergunta, talvez de uma maneira um pouquinho mais específica, mais clara, aí a gente pode... Oi? Radu, tá bom, só um minutinho, por favor. Tem nesse site mentalplumes.org, que é realmente muito bom, tem uma seção que é dedicada à definição de plumas, né? Então tem uma do Mark Jensen, de março de 2004, que é o seguinte: pluma é um termo que remete a um lixo semântico que não faz absolutamente nada para clarear as ideias, nem do autor, nem do leitor. O debate é forte. Now, there is this quote by Mark Jensen in mentalplumes.org, which is, plume is a term that amounts to a semantic garbage disposal that does nothing to clarify the thoughts of either the author or the reader. Well, it's a great debate, actually. Yeah. Ok, outra coisa é o seguinte, o paper que o professor falou, o paper do Dieter Frank, tá no Marine Geology, é o volume 43 do Marine Geology, volume 43, Dieter Frank, 2013. E o paper é Rifting, Lithosphere Breakup and Volcanism, Comparison of Magma Poor and Volcanic Rifted Margin. That's the one, isn't it? Páginas 63 e 87. Eu baixei o PDF aqui, mas qualquer um pode baixar porque o PDF é de livre acesso no Marine Geology, ok? Esse foi o paper que o professor falou nos últimos slides dele aí, tá? Bom, vamos fazer então, vamos passar aqui a pergunta do Carlos Eduardo.
A pergunta é o seguinte, até em paralelo com a evolução do rift Atlântico, eu quero saber se dentro desse magmatismo não ocorreu nenhum tipo de manifestação de magmatismo alcalino, tá? E se esses basaltos eles são predominantemente doleíticos.
Mas aonde? Caru? No Caru. Ok. So again, related to Caru, our colleague wants to know that if it's exclusively tholeiitic basalt magmatism, or if there is any sort of alkaline magmatism associated.
I don't know if any alkaline magmatism associated with the Karoo rocks there, but it's not only basalt, of course, there's also rhyolite. And in the Nwanetsi province, where the triple junction is, where the three, over here in this region of Zimbabwe, we actually see a whole lot of ring complexes, or granitic ring complexes, and some that are quite evolved, and they even have mineralization associated with them. There are breccia pipes in those ring complexes with molybdenite, and there's also tungsten, scheelite, and fluorite bearing little prospects which are sort of associated with those, and some of them are actually intruding the mafic lava, the late ring complexes in there. But in the rest of the Karoo province, it's mainly tholeiitic lavas. Yeah.
Que ele conheça não, existem algumas ocorrências próximas da junção tríplice que ele mostrou no slide, que são basicamente estruturas anelares com algumas rochas graníticas que estão mineralizadas, inclusive em scheelita e it's scheelita, what else? Sorry. Scheelite, sorry. Fluorite, fluorita, scheelita e tal. Tá, talvez eles estejam de afinidade alcalina, mas ele não tem certeza. Fala, Diana. Fala, por favor. Para o quê? Para o núcleo terrestre, é isso? So this comes from Manaus, and the question is, what do you think about the models for the Earth's core? Models that are pointing to a graphite-rich core for the Earth. É essa? It's about the outer core.
The outer core.
Yeah, there seems to be some models that are related to the graphite-rich outer core composition. I'm not sure if you're aware of that.
Yeah, no, I'm not aware of that. I I'm aware of experimental work that on very high pressure physics, looking at what the core might be, the solid core might be made of. And I know that they would have in those models a little bit of carbon, perhaps with the iron, and even things like oxygen. There might be a little bit in there, but I'm just trying to think. There was a girl called G. Lee who was doing a PhD on this at Harvard back in the 1990s. But I'm really not aware of any new data that suggests there might be a lot of carbon in the outer core.
Ele não conhece nenhum tipo de modelo que envolva um enriquecimento em grafita do núcleo externo. Então ele simplesmente não consegue responder. Tem mais alguma de fora? Mas ele basicamente repetiu a pergunta. Então, assim, vamos ver se depois o professor, então, porque ele não entendeu a pergunta nenhuma, na verdade. Então a gente pede para os colegas esperarem um pouquinho, entenderem que a gente vai responder isso, o professor, a gente vai passar isso para o professor, ele vai responder por escrito depois. Existem várias questões que estão sendo repassadas para ele, para que ele possa responder. Ele vai responder, mandar para a Dayana, e a Dayana vai passar para todos que estão no mailing list, tá? Bom, mais 2 minutinhos, eu vou fazer se ninguém mais quiser fazer perguntas, eu tenho uma pergunta para o professor, que é o seguinte: desde o início, como eu falei, desde o início do curso ele vem falando das interações entre atmosfera, biosfera e litosfera, do Arqueano para cá, e eu acho que esse foi um dos motivos principais da escolha do nome dele para dar esse curso. A capacidade, basicamente, que ele tem de integrar todos esses processos e apresentá-los como uma espécie de sistema, o sistema Terra. Eu acho que o Nevaldo, quando a gente teve a oportunidade de conversar, ele enfatizou muito que eu me lembro, ele enfatizou bastante a vontade dele de exatamente passar essa filosofia para os geólogos do serviço geológico, principalmente os recém-contratados, a necessidade de associar processos geológicos com processos biológicos e da atmosfera também. So I think that the main reason for you to be chosen as a lecturer here is that one thing you do quite well is to integrate the biosphere, the atmosphere, and the lithosphere processes, a sort of holistic or in a sort of system. So we had you talking about this process from Archean to the Proterozoic, to now we are at the Mesozoic, Jurassic, and Cretaceous, with this large amount of magma production and lava outpouring. So what sort of impacts would you expect from this amount of lava being being extruded on Earth's surface? What sort of effects would you expect this to have onto the biosphere, onto the atmosphere and Mesozoic times?
Oh, that's a whole subject of a whole lecture in itself. Yes. Look, this is a whole other debate about what causes mass extinctions. And we know that the two largest mass extinctions in the Phanerozoic, the Permo-Triassic boundary, which I talked about, and the Cretaceous Paleogene boundary, there's been a lot of debate in the last 2-3 decades about the causes of those, especially after the discovery of the iridium anomaly at the KT boundary and the whole impact model for that mass extinction. The alternative model that is now probably becoming the orthodoxy is that mass extinctions are actually caused by large volcanic provinces, large igneous provinces. And this is now getting strong support from the very good geochronology that is being done by people like Vincent Courtillot and his group in Paris, who are going around systematically to all the large igneous provinces and trying to get systematic dating of the timing of those large igneous provinces. And then trying to compare that with the ages of mass extinctions, and also there is another group at the University of London which has been looking at the timing of all the largest Phanerozoic impact structures and trying to do the same. So trying to look at, is there a correlation between the ages of impact structures and the ages of mass extinctions or the ages of large igneous provinces? And what comes out from that analysis, and they've done Monte Carlo simulations and statistical sort of analyses of all the existing data for both large igneous provinces as well as meteorite impacts, is that there is only one major mass extinction in the Phanerozoic, and we have at least 5 big ones and a few smaller ones. There's only one mass extinction which exactly coincides with a meteorite, and that is the Cretaceous Paleogene boundary. But all of the other mass extinctions coincide with large igneous provinces. So the conclusion is inescapable, according to Courtillot, that it is in fact large mass extinctions that are caused by volcanic eruptions or large igneous provinces that are the main culprit in most mass extinctions. And if you look at the Cretaceous Paleogene boundary, it also has a large igneous province coinciding with that big meteorite impact in Mexico, and that is the Deccan Traps. The Deccan Traps exactly are in the same time interval. So what Courtillot would say, and he has said that because he came to our university and he gave a lecture on this, he says, even if Chicxulub never happened, there would still have been a mass extinction at the KT boundary caused by the Deccan large igneous province. So, and Courtillot and his group are the ones that have been most involved in this question of the environmental effects of large volcanic eruptions. Now, the problem is that not all large volcanic provinces result in mass extinctions that are large. There may be localized things, but they're not of global impact. For example, and one of them is this one. The Karoo large igneous province does not produce a big mass extinction in the record in years. There's just only a localized sort of, a couple of things that die out, but it's no large mass extinction. So then you have to ask the reason why. Why do some large igneous provinces like the Siberian traps or the Deccan traps, why do some of them produce huge mass extinctions and others very small? And the answer, at least as far as the Permo-Triassic boundary is concerned, which is the largest of all the Phanerozoic mass extinctions, is the nature of the rocks into which through which the Siberian traps have come through. The Siberian traps, dated at about 251 million years, have come through a thick sequence of Paleozoic rocks which contain massive amounts of evaporites and also coal seams. So they have had massive amounts of interaction with organic matter and probably gave off huge amounts of methane. And methane, aside from being a powerful greenhouse gas, can also have many other environmental effects. And according to their modeling, also the sulfur that is coming out of there as a sulfur dioxide will have had major environmental effects in terms of acid rain and all of that. So perhaps it's the nature of what these things have come through. In the case of the Karoo, you're looking at just siliciclastic sediments. Interaction of magmas and siliciclastics not going to do very much. And it's come through a little bit of cold seams, but nothing massive. No huge marine evaporites or no huge black shale sequences or something like that. So that may be what is the big difference. What is causing the big environmental effects is the effects of the intrusions on the rocks through which they're coming through, and what that is spewing out into the atmosphere. Now, another thing that if you want to know on a small scale what environmental effects large volcanic eruptions can have, Coutinho quotes the example of the 1786 eruption of Lucky, which is a fissure eruption in Iceland. In Iceland, we have the largest fissure eruption, the largest eruption actually witnessed in historical times. I mean, we had in the 19th century Krakatoa, and we had Toba in 1815, but they were explosive eruptions, but the volume of magma in Iceland in 1786 was larger. And 1786, the eruptions lasted for about 6 months into about 1787 and produced about a cubic kilometer, maybe actually less than that, but that's the total volume of magma that was actually extruded. But that is the largest volume that has actually been seen by humans to be erupted. It's in human history. So all other eruptions, which are much larger, were prehistoric eruptions. But this one, we have a very good record of the actual conditions that were in Iceland at that time. There is a priest who kept a journal which has been published now and also translated from Icelandic, and he shows devastation completely. Firstly, Iceland had a very small population. To start with, today it's about 200,000. Back in the 18th century, it would have been much less. And most of the population suffered drastically. I mean, we have seen the eruptions of Eyjafjallajökull about 2-3 years ago, and causing major disruption of aviation in Europe, but also having environmental effects in Iceland itself, on the cattle and on the people. But this 1786 eruption, not only did it affect Iceland, it affected the whole of Europe. It produced a huge sulfur-rich, SO2-rich cloud, which produced a haze that spread over the whole of Europe. And Coutinho and his group have actually modeled this to see how much atmospheric SO2 would be given off in that eruption, and how long it would have lasted, and so on. It's very interesting. I've actually done some historical research myself, influenced by Coutinho's research. He showed, firstly, Benjamin Franklin, the American scientist and president, he actually was the American ambassador to France at that time, and he made some observations. He noticed that there was all this these days when there was all this haze, and in that winter of 1786, there was great mortality. And Franklin noted that the hospitals were full of people with respiratory diseases, and the mortalities had risen. And he was one of the first persons to link what is going on in France with the ongoing eruptions in Iceland. I've done my own historical research and found that the same thing happened in Scotland in terms of mortalities. You look at the figures of people in the hospitals, then after 1786 there was a huge rise in mortalities and so on. So, and I've even found evidence for atmospheric electricity. There is a famous meteor that was seen across the whole of England. There were paintings about it, and there's a whole book written about it. And it is supposed to be the great meteor of 1786. And I have my doubts that it was a meteorite from outer space. I think it was an atmospheric electrical phenomenon, because I've now heard talks by people who say this is very possible. The atmosphere is quite electric. There are all kinds of things, but the fact is that the so-called meteor was if you read the eyewitness accounts, and they're all published in the Philosophical Transactions, they show that people could sense the air was thick, and it was just like, SO2 rich atmosphere. And it is in this thing that you had it's probably an electrical discharge of some sort that produced this so-called meteor. So, and this is a tiny eruption of less than a cubic kilometer. Now, if you think of a large volcanic province, Kevin Burke says rule of thumb is large volcanic province is 1 million cubic kilometers, 1 million square kilometers in area, and it takes 1 million years to erupt. So that's a rule of thumb. It's very simple. And if you do that, then it's a cubic kilometer per year for 1 million years. So the kind of environmental disruption that happened through one little volcano in Iceland, imagine that continuing for 1 million years. That will be the cumulative effect of a large igneous province in terms of its effect on the environment. So it's really huge, and so now it's no surprise that most mass extinctions are found to coincide with these large provinces.
I could see you were quite excited with this. So, eu não vou traduzir por causa do adiantado da hora, claro, ficou muito longa a resposta, isso vai aparecer traduzido nas aulas depois, já são 1h15, eu não vou atrasar mais o almoço. Mas o professor falou basicamente que o tema é tão interessante que daria um curso inteiro, né? E só o tema daria um curso inteiro. Mas muitas extinções em massa estão deixando de ser diretamente relacionadas a crateras de impacto, e principalmente depois dos trabalhos do professor Cortilhot na França, com datações de grandes províncias basálticas continentais, essas extinções em massa estão sendo mais relacionadas ao surgimento dessas grandes províncias basálticas continentais. Especialmente, existem algumas províncias basálticas que não estão relacionadas à extinção em massa, então parece que a relação da existência da província com a extinção em massa tem a ver com o tipo de rocha que é atravessado pelo magma até ele chegar à superfície e extravasar. Então, no caso da grande extensão do Permiano, que está associada aos derrames siberianos, né? Esses derrames estão associados a sequências de rochas como evaporitos e camadas de carvão também, e a interação do magma com essas camadas pode ter resultado numa condução de uma quantidade muito grande, por exemplo, de metano para a atmosfera, que além de causar um tremendo efeito estufa, né? É um gás causador de efeito estufa tão ou mais poderoso que o gás carbônico. Também causa outros efeitos colaterais, como por exemplo chuva ácida, porque não é só o metano que sai, mas sai também enxofre dentro dessas sequências, porque estão cheios de sulfatos e tal. Então parece que a relação hoje, principalmente após os trabalhos do professor Cortilhot, na França o pessoal tem mudado um pouco o eixo da relação de extinção em massas com impactos de meteoritos, que era o modelo mais aceito, principalmente por o limite KT, né, por causa do encontro dessa camada de irídio, e agora o eixo está sendo mais voltado para relacionar esses processos com essas grandes províncias basálticas continentais. Ele falou muito mais do que isso, mas a gente vai deixar para traduzir depois junto com as aulas, tá bom? Então agradeço a todos, agradeço os colegas que estão nas outras unidades regionais, viu? Aprendi, Dayana. E a gente vai sair para o almoço agora e vamos voltar cerca de 2h15, tá bom? 2h15, 2h20 a gente retorna para as duas aulas finais. Obrigado a todos. Thank you very much, Sharat.
Plumes, kimberlites, lithospheric structure, and diamonds. So this is a big topic to cover in a lecture, but it's got a sparkle at the end of it, which is of course diamonds. So we want to understand more about the occurrence of diamonds. We all know that they come from kimberlites, but we want to understand what controls kimberlites, and where do diamonds come from, and all the rest of it. So diamonds, as we all know, stand for all these things, because somehow the custom started a long time ago of giving engagement rings. So you associate the gift of diamonds with love and purity and joy. And De Beers came up with the slogan, "A diamond is forever." So diamonds have always been associated with wealth and with privilege and something else. So it's a romantic story about diamonds. But the scientific story about diamonds is even far more interesting than the story about diamonds as a gemstone. And here you see some of the largest diamonds ever found. In the center is a model of the Cullinan diamond, which is the largest gem diamond ever found, because I think the Sergio in Brazil was a carbonado, but it was bigger, but it is of course not a gem diamond. This is the Cullinan diamond, which was found almost 100 years ago in 1905, 3,106 carats. And flawless. So that's the kind of things that people would like to find more of. This is the largest uncut yellow diamond, octahedral diamond in the world. It's called the 616 diamond, and it belongs to De Beers, and it happens to be their P.O. box number, the post office number of De Beers in Kimberley is also 616. It happens to be 616 carats, so they thought, what a coincidence, let's name the diamond after that. So this is something you can see at the Kimberley Diamond Museum. And here is just a selection of fabulous diamonds from South Africa, uncut, and the one in the middle, at the top, which is a cut diamonds. So diamonds have quite a natural range, a variety of different colors and crystal forms and so on. But we generally tend to see in the jewelry stores only the final cut product. But natural diamonds themselves are quite beautiful and have a range of different colors. While we're on the subject of colors, I can tell you that there was a lot of excitement in South Africa about a month ago, when in one of the alluvial diggings they found a blue diamond, which was about 25 carats or something like that. It was one of the largest really deep blue diamonds, and that color of diamonds is extremely rare. And they estimated that the diamond is worth about $20 million. Just one diamond. I don't know who would pay $20 million, but there are people who would. Here is an old photograph showing what the types of the types of rough diamonds that were recovered from the mines in Kimberley. Okay, so we know after the discovery of this rock kimberlite back in the late 19th century, the diamonds actually have a primary source, which is brought up. They're formed deep down in the Earth's mantle, and they're brought up by kimberlites, and the kimberlites erupt, and then kimberlites are eroded, and then diamonds make their way in rivers and to the sea. And you can find primary diamond deposits in kimberlites and secondary deposits in gravels and also in the sea. In Brazil, I know that you have lots of diamonds, but most of them are the secondary diamonds. You have no diamond mines apparently in kimberlites, except for some small workings. And you also don't, as far as I know, don't have any marine diamonds. In South Africa, we have all three. So I will show you a little bit about some of that. So, but let us look at this host rock in which diamond was discovered. Because diamonds were discovered in Brazil a long time ago in the 18th century, whereas in South Africa they were discovered in 1866. So in 2016 it will be 150 years since the discovery of diamonds. It's a significant anniversary, and there will be a big diamond conference in South Africa at that time, or in Botswana. The Kimberlite conference is going to be there. So kimberlite turns out to be the host rock from which primary diamonds occur. But kimberlite itself is an extremely strange rock. It's a hybrid rock, and it comprises both what you call components that are sort of primary igneous components, and it also has a whole lot of other components which are accidental components. There are xenoliths and xenocrysts, which are accidental crystals that are formed from the disintegration of xenoliths. And so you have, it's a kind of an ultramafic rock, a high temperature peridotite, but it's got fragments of peridotites and eclogites as xenoliths, and it's got megacrysts, which are big crystals, and which has reacted with this low temperature volatile rich matrix during and after intrusion. And there are also sort of many different fascies that are recognized in kimberlites, the diatreme fascies where you've got solid massive kimberlite, but as it's erupting, it sort of explodes, and you get a tuff, a kimberlitic tuff, which is formed in the crater sort of fascies and so on. And there are also other xenoliths in there of wall rocks, so you get both mantle xenoliths in kimberlites as well as crustal xenoliths, which are accidentally incorporated in the kimberlite during its ascent. So the mineralogy of kimberlites, they contain a whole bunch of minerals. Olivine is the most common mineral, so it's a kind of a peridotite, but it's got garnet, it's got ilmenite, pyroxene, mostly clinopyroxene, and it has a lot of hydrated minerals as well. It's got phlogopite, and then it has things like serpentine, spinels, perovskite, monticellite, apatite. There are carbonates, mostly calcite, a variety of clay minerals. So some of these are all alteration minerals, secondary minerals, and so on. You have sulfides in there, millerite, pyrrhotite, pentlandite, chalcopyrite. There's zircon, which is very useful for dating if you can find zircon, or rutile, titanite, pectolite, etc. So there's a whole range of different minerals, some of which are primary, others are secondary due to secondary hydration processes or due to weathering. And there are lots of minor minerals, including PGEs that have been found, graphite, silver, native copper, but the most precious one, of course, is diamond. So diamonds are found as inclusions in kimberlites, and for a long time, diamonds were thought to be things that crystallized out of kimberlites, because kimberlites are carbon rich. They've got other carbonate minerals like calcite and so on. And at one time, diamonds were thought to have crystallized out of a kimberlitic magma. But that all ended with the work of Jan Kramers, who was at that time at Wits University in Johannesburg in the 1970s, at the time when I was an undergraduate student there. And Jan Kramers was the first person to date diamonds directly by looking at sulfide inclusions in the diamonds. That included things like galena, and he was able to date the sulfide inclusions using lead isotopes. And what he found is that the diamonds were very, very much older than the host kimberlites. We've known the age of the kimberlites in southern Africa are sort of Jurassic to Cretaceous in age, whereas the diamonds that Kramers dated were about 2 billion years old. So we realized from that time on, in the late 70s, that diamonds are actually xenocrysts. They do not belong to the kimberlite magma, but they are simply carried by the magma. They're formed somewhere else, and they are accidental xenolith or xenocrysts in the magma. And then companies like De Beers, which have been mining diamonds since the early days of Kimberley, they discovered that the xenoliths that you find within kimberlites, things like the peridotites and the eclogites, can actually contain diamonds in them. And so it turns out that that is where the diamonds are formed. The diamonds are formed in the mantle, where you find the peridotites and the eclogites forming, and all that the kimberlite magma does is to intrude through that piece of mantle, picks up pieces of that mantle and brings it up to surface. And in that process it may actually dissolve some of those xenoliths to liberate the diamonds as free diamonds. And you can see from the diamond morphologies in kimberlites that sometimes they show resorption surfaces, so the diamonds themselves start to get dissolved in the kimberlitic magma after they've been liberated from their host xenoliths. So here's a variety of textures taken in thin section, showing you what a kimberlite looks like. It's a very complicated looking rock because of all these this mixture of olivine. Here you see a fresh good euhedral looking olivines with a fine grained, very altered matrix in which you'll find all kinds of spinels and garnets and other things, and phlogopite and so on. So but in addition to that, you get big megacrysts, big crystals of things like phlogopite and other minerals which have been liberated from the dissolution of these the xenoliths, the mantle xenoliths that you find in the kimberlite pipes. And among the rare things that you find, of course, are diamonds. Diamonds are extremely rare. If you look at a kimberlitic diamond mine in South Africa, a typical mine, it would be running at a grade of a few carats per 100 tons. Maybe if it was a rich mine, it might be running at a few tens of carats per 100 tons. So a carat is 0.5 grams, and to have that sort of grade per 100 tons, you're looking at an in situ grade of something like 1 part per billion of that order of magnitude. And to try to find 1 out of a billion, it's almost impossible. So I remember very, very clearly my first visit to a kimberlite pipe, an operating mine in a kimberlite pipe many years ago. It was a De Beers operated mine, and we were told that people have worked for their entire careers in this mine, in this open pit, and they have never seen a diamond because it's 1 part per billion. We got off the bus that De Beers had supplied because we were in our own bus. We had to get off our bus, get into the De Beers bus, and then go down into the open pit. And everybody got off the bus, and I was one of the last people to get off. And then the last person to get off the bus, he got off and he bent down and he picked up the first rock he could find outside the bus, and it had a 5-carat diamond sitting on it in matrix. So immediately he called our attention to it, and everybody came and we took photographs. And the geologist told us this is the first time he had seen a diamond in the open pit. And very shortly afterwards, 2 very hefty security guards came came up to this place, and they got a strong box and a receipt book, and they got this man to sign a receipt. He got the receipt, and they took the diamond, locked it up, and took it away. And at the end of our visit, everybody was searched. It was the old days when we had old cameras. We had to wind up our phone, open the cameras, show them there was nothing inside. They took photographs of us and they let us go. What are the chances that you find 2 diamonds? So anyway, so it just shows you how rare diamonds are. And so you could be mining tons and tons of rock, but your monthly production would be what you have seen in this previous photographs. This might be a monthly production out of a big diamond mine. So out of this, you've got your make all your money, but all your costs go into the mining of that stuff. Here is a famous a photograph of it's actually I think it might be a painting of a diamond, an octahedral diamond in the kimberlitic matrix. You know, in South Africa it is illegal to own an uncut diamond. It is because it was a law that was passed a long time ago to prevent diamond smuggling and so on. So you cannot legally possess an uncut diamond unless you have a certificate, you know, to show that you are a legitimate educational institution or a collector or something like that. But so in fact we don't have any such specimens in our major museums. You want to see a diamond in matrix like this, you have to go to the American Museum of Natural History in New York. They have a wonderful large octahedral diamond in matrix from South Africa, which they got through some means they don't want to tell us. Okay, so where do diamonds or diamondiferous kimberlites occur in the world? And this is an interesting story. You look at the distribution of kimberlites, and they are usually found associated with cratons, and especially the diamondiferous ones. This one shows all kimberlites, not just diamondiferous ones. This is the De Beers database. De Beers used to have the best research laboratory of any mining company in the world. In the 70s, they must have had over 100 people working for them. They had their own mass spectrometers, they had their own scanning electron microscopes, and they developed the whole technology and methodology for kimberlite prospecting. They still have a laboratory, but they have gotten rid of their dating laboratory and they've donated it to other to universities and so on. They've disbanded their whole big research laboratories. So, but during those years, they systematically prospected for kimberlites all over the world, and they also dated them. They had their own dating laboratory doing argon dating, and they systematically dated phlogopites out of kimberlites, and they've got a whole huge database for the whole world. And this is a paper written by Hilke Jelsma, who is the chief consulting geologist for De Beers currently, and they allowed him to publish this as part of the database. Of course, not the exact localities and so on, but it shows you the distribution of cratonic rocks, old cratons, and you can see that there is a strong correlation between where kimberlites are found and where cratons are. There are just a few examples of a few kimberlites that have been found in mobile belts away from these kinds of cratons. And without any exception, all the diamondiferous kimberlites are definitely restricted to cratons, and the oldest cratons, the Archean cratons, are the ones that are the most likely to have diamondiferous kimberlites. So I will come to why in a minute. So this is the real answer to why you need a thick craton in order to form a diamondiferous kimberlite. This is a well-known sort of diagram, and it shows the thickness of the lithosphere. So at the top here, this is the surface, and this would be the crust, and we're taking an average crustal thickness of 45 kilometers here. And then we look at the lithosphere, and the lithospheric thickness can be just under 100 kilometers to perhaps 200 kilometers, such as under an Archean craton like the Kaapvaal craton in South Africa. In fact, the Kaapvaal lithosphere extends almost to 250 kilometers. It's got a very deep mantle root. So what is the difference between the lithospheric mantle and the asthenospheric mantle? Well, the asthenosphere is where the mantle is convecting and undergoing convection either in the upper mantle or the whole mantle, whatever you think convection is doing in the mantle. Whereas the lithosphere, the lithospheric mantle, especially the stuff that is underneath the continental crust, the so-called subcontinental lithospheric mantle, this mantle is more refractory because this is mantle which has already lost some components through partial melting in the past, which has then risen up to form volcanic or intrusions or volcanic rocks in the crust above, which has left behind more refractory material. Because if mantle undergoes partial melting, then the material that melts first at the lowest temperatures is going to rise up first, and that leaves behind a residue which is more refractory, which melts at a higher temperature. So basically what you're looking at is the remains of what happens when you melt mantle peridotite and you partially melt it and remove melts. Now when you remove partial melts, then certain elements are going to partition preferentially into the melt, things like silica, potassium, but also uranium and so on. So through partial melting events, you're going to deplete that mantle in things like uranium and potassium, which as we know are radioactive elements. So you are going to lose your heat producing elements in the lithospheric mantle throughout geological history if it undergoes partial melting processes, and in the end that lithospheric mantle is cooler than the surrounding asthenospheric mantle because it has less heat producing elements. So if you look at what happens to the geotherms, you look at the geotherms like the 900 degrees centigrade geotherm or the 1200 degrees centigrade geotherm. The geotherms are depressed in this area of thick lithosphere because of the lower heat flow. So because of the lower heat flow, the geotherms do this. So you have thicker crust and it's still cool. It's at 1200 degrees at 150 degrees centigrade, whereas when you go away from the craton, it will be a much higher temperature at the same depth. So you have to think of this lithospheric keel as being old and cold. And that is the key to how diamonds would form. Because another key component of this diagram is this line over here, which shows the diamond stability field. And it shows the conditions in terms of depth or temperature at which diamonds are stable versus graphite. So diamonds have a strange behavior in terms of their stability, which I can show you in this next diagram. Diamonds are stable. Diamonds are a high pressure form of carbon. Graphite is a low pressure form of carbon, and of course also low temperatures. But this line, instead of being the other way, which is what happens in most cases, this line has this funny slope, which means that diamond is stable at high pressures but at low temperatures. If you have a diamond and you keep it at this pressure at which diamond is stable, but if you increase the temperature, it will convert to graphite, even at high pressures. So the diamond is only stable at high pressures, but relatively low temperatures. So here are the temperatures given in degrees centigrade. So you can see that if you have a particular depth at which diamonds might be stable, it depends on the temperature as well, whether you're going to form diamond or not. And that is what explains the curve in this particular graph. This graph does not go as a straight line. It's not just a function of pressure where you go from graphite to diamond. It's a function of pressure plus temperature. And in that case, you can see that the temperatures underneath in this area where you've got thick lithosphere, at the same depth, the temperatures are basically, because of the geothermal gradients are doing that, the geothermal gradients are depressed. So at the same depth away from the craton versus what is in the under the cratonic keel, the temperatures are quite different. The temperatures are lower here than they would be away from this cratonic keel. So that is why the shape of this graphite to diamond transition has a curve rather than being a straight line. Now, so if you are in this lithosphere and you are below this line, this is where diamond is stable. So diamond is stable and is found in the lithospheric mantle underneath a craton, at these sort of depths, about 150, just about 150 kilometers to 200 kilometers depth. If you have a subcratonic lithospheric mantle with a deep root that goes down from 150 to 200 kilometers, that is actually where you will find diamonds. You will not find diamonds in the asthenospheric mantle because it is too hot. So in the asthenospheric mantle, you will always only find graphite. The only place where you will find diamonds, where the proper stability conditions are found, is in the lower keel of one of these old and cold cratons in the lithospheric mantle. So if you know that this is the only place where diamonds are found, then this is what you have to look for. You have to find an old craton and find where the deepest and thickest lithospheric root is under that craton, and that is the primary source of diamonds. Then you have to find kimberlites which have punched their way through that particular piece of lithosphere to the surface, and then they could have had a chance to bring up kimberlites to surface. So if you look on this diagram, there are several kimberlites that are shown here, K1, K11, K. So if you have these particular kimberlites, they are coming up through this diamond sort of window, and therefore they are able to pick up diamonds and be diamondiferous. And here is, say, a lamprophire which could do the same. It comes up through the diamond window and it can actually pick up diamonds. But if you had one that was on the edge of this keel or somewhere through a mobile belt, it will have no chance to pick up any diamonds. It will only have graphite. So this is the key to finding diamond deposits. It's been known about for a very long time, but then the problem comes out to how do you find an old craton, and where in this craton is the deepest part, and so on. And there's also the other problem of old cratons that have lost the lithospheric keel, that have become decratonized. So there you may have had kimberlites that had brought up diamonds at the time when the keel was still present, and then the keel was removed, so today it's no longer a craton or no longer has a thick lithosphere, and you would sort of rule it out in terms of prospecting, and yet it may still have diamondiferous kimberlites. A good example of that would be the North China Craton. The North China Craton has Archean and Proterozoic rocks. It was clearly a craton. It behaved rigidly as a craton, but in the Mesozoic it lost its cratonic root, had a massive granitic injection of granitic melts. It's got a lot of gold mineralization associated with those granites, but it also has lost its lithospheric root and became decratonized. But if there were kimberlites there prior to the Mesozoic, they could clearly have been diamondiferous. So it is still prospective for diamondiferous kimberlites if you know that there are kimberlites there and they are of the right age. Okay, so let's look at the distribution of kimberlites in southern Africa. And here we see whole clusters of kimberlites. Kimberlites don't occur as just individual kimberlites. They usually occur in clusters. And literally, you get hundreds of kimberlites that can be found in a particular craton. And I know that De Beers did a lot of prospecting all over the world. They found literally thousands of kimberlites. In fact, there is a rule of thumb, if you like, in exploration for kimberlites. Because there are lots of kimberlites, but there are very few kimberlite mines, diamond mines. So the rule of thumb is 1 in 1,000 kimberlites is going to be diamondiferous. 1 in 1,000. And 1 in 1,000, not 1 in 1,000, 1 in 100. I'm sorry, I will repeat that. 1 in 100 kimberlites is diamondiferous. And 1 in 100 of diamondiferous kimberlites is economic. Which means that maybe 1 in 10,000 kimberlites is going to be a diamond mine. So that's a number of mines you'd have to find, a number of kimberlites you'll have to find globally to find a few diamond mines. And if you count the number of kimberlite diamond mines there are in the world, there are very few. There's about 5 in Angola, about the same number in South Africa, and about 3 in Botswana, or 3 or 4, and 1 or 2 in Zimbabwe, and a few in the Congo, and that's it in Africa. Then you have some in Australia, you have the lamproites in Argyle and so on, and you've got a few now operating in Canada, and there's some in Russia. Those are the only kimberlitic diamond mines in the world. The rest of the world's diamonds are alluvial diamonds, or marine diamonds. So, but there are thousands and thousands of kimberlites that have been found. So, I will come back to this distribution of kimberlites in South Africa, but the ages have been known for a long time. We basically have about 4 clusters of ages of kimberlites. So we have kimberlites that are, most of our kimberlites that we see here, most of these ones are sort of late Jurassic to Cretaceous in age. They range in age from about 160 to 80 million years. Then we have a small group of kimberlites up here at Venetia, which is in fact our largest diamond mine. It's very close to the Zimbabwe border. And there's also a few kimberlites in Zimbabwe, one of which is the mine as well. And this cluster of kimberlites in the north is actually 500 million years, or 510 or 12 million years, about Cambrian age. And then just north of Pretoria, so here, this premier kimberlite, it's the only one that we know of in the whole of South Africa that has this age, but it's a very important kimberlite. This is the one where the world's largest diamond was found, the size of my fist. So, and it's still operating today, and that kimberlite is 1200 million years, Mesoproterozoic in age. And finally, we have a cluster of kimberlites in the Northern Cape region here, the Kuruman cluster, which turns out to be 1649 million years, and is non-diamondiferous. So all the other ones are diamondiferous, this one here is not. And then I mentioned when I talked about the Witwatersrand Basin that we actually have diamonds as paleoplaces in the Witwatersrand conglomerates. So that must indicate that there were even older than 2.8 billion year diamonds on kimberlites, diamondiferous kimberlites on the Kappa Craton, which have never been discovered up to now. Nobody knows where they are, but they must have been there. And if you look at the dating of the diamonds, inclusions have been dated in them. We have diamonds formed at 1150 million years, and diamonds formed at 33.3 billion years at Finch and at Kimberley. And there are also other diamond ages like the eclogites from one of the mines, which give about a 2 billion year age. So the diamonds, as I said, are much older than the hosting kimberlites. They were formed a long time ago and simply picked up by these younger intrusions as xenoliths or xenocrysts. So here is a map by Jelsma in which he looks at the distribution of kimberlites in relation to lithospheric structure or crustal structure here. So you see here the cratons, the Kappa Craton, the Limpopo Belt, and the Zimbabwe Craton. This is all very, very old lithosphere here, and this is where you find the bulk of the kimberlites. Then we also have the Mesoproterozoic mobile belt over here, and we find quite a lot of kimberlites here, all of which are barren. There's no diamondiferous kimberlites here in this cluster over here. And again, we have in northern Angola the Angolan shield, and most of these, this one here is actually Proterozoic in age. The Angolan shield is about 2 billion years, and it's got a lot of kimberlites, but very few of them are diamondiferous, whereas the ones in the northeast of Angola, the Kasai Craton, has got a whole lot of very, very good diamond mines, very diamondiferous kimberlite, one of the most prospective places in the world, because just in this little area they've got 5 kimberlitic diamond mines. And across the border into Congo, in the Bujimai area, there's also another few kimberlitic pipes which are being mined. So this is very prospective, this old Kasai craton, and it's really Archean in age. In fact, the oldest rocks dated from this region are about 3.5 billion years, ranging to about 3.2 billion years in Kasai. And then the other diamondiferous kimberlites, there are kimberlites known in Tanzania, in the Tanzanian Craton. About 1,000 kimberlites have been found by De Beers, and there is only one operating kimberlite diamond mine in Tanzania, the Mwadui mine, which is one of the largest in the world. So here is the same sort of thing, except here now you see the different ages given of kimberlites in this legend. The youngest Jurassic to Cretaceous kimberlites are found here in the Kappa Craton. They are the old 500 million year kimberlites which are found in this sort of area in northern part of Skapar Craton and Zimbabwe Craton. And then there are other ages like the old ages coming from this region. Now, in the same paper, De Beers geologists have long believed that what controls kimberlite emplacement are regional structures, and they've done a lot of lineament analysis and a lot of detailed structural analysis to show that this is the case. And here is a map from Mielsma's paper which shows the linear distribution of kimberlite in clusters which occur along major crustal lineaments. So here's a big linear feature that runs through from Namibia through Zambia into Tanzania. It's in fact a very well-known sort of a lineament zone separating the Congo Craton from the Kalahari Craton, and it has been reactivated a few times, and it seems like this is one major control on kimberlites emplacement, but these ones are all within a mobile belt, and they're all barren kimberlites here. The more interesting lineament is this one in Angola, which has been known since the 1960s, because aside from kimberlites, there's also alkaline intrusions in Angola, which are following the same trend, and it's a big lineament trend following some major fault structures. And these kimberlites here in the Kasai Craton, the Archean Craton, are diamondiferous. The ones in the Proterozoic Craton are not. Okay, so let's go to, we've seen what sort of controls the crustal distribution of kimberlite pipes. They're related to particular large-scale structures in the Earth's crust. Let's look in more detail at the different parts of a kimberlite. And this is a model that was developed by De Beers geologists. Barry Hawthorne was the chief geologist of De Beers in 1975, the chief consulting geologist. And this is based on a study of many different kimberlite pipes at different erosion levels. So they put together a model of what a kimberlite pipe would look like in 3 dimensions at the time of extrusion and intrusion. So you have a root zone of a kimberlite where kimberlite actually assumes more a dike-like form, and then it may actually be eroding by erupting along an intersection of say two lineaments or something, and as it comes up through the crust it assumes a more circular form, and it's shaped like a champagne glass. It starts to flare out as it comes near the surface until it explodes violently, and most kimberlitic explosions are thought to be extremely violent and very fast explosions with very, very gas-rich magma, very volatile-rich magma, which fragments, and during that explosion process you form a tuficitic kimberlite, which can form tuff rings in the kimberlitic crater, just like you find around Mar craters around explosive volcanic vents. And you may find in a well-preserved kimberlite like the one at Orapa in Botswana, where you have this uppermost sediments preserved, you actually can form a crater lake above the eruption and sedimentation of lacustrine sedimentation within this crater facies. So you have these explosive volcanic sort of rocks that are related to this extrusive phase and the crater phase. And then you have diatreme facies where it is a very frothy kimberlite full of vesicles and may have lots of xenoliths that have come in from the surrounding wall rocks that have collapsed into this particular facies. It may have material that is dropped down from the wall rocks, as well as things that's carried up from a greater depth. And then as you go deep down in the kimberlite, you get what is called the main diatreme facies, getting down into the root zone where it becomes a dike. And you have kimberlite dikes exposed at very deep erosion levels, and they are actually dikes. So this is the generalized model for kimberlites. And here is a diagram that illustrates how the morphology of the kimberlites may change with depth. So it ends up as these kinds of kimberlitic dikes. You may have multiple intrusions along the same dike. Sometimes you get two nested pipes next to each other, as you find at some of the diamond mines. So De Beers in the last few years have been supporting a lot of research into the mechanisms of volcanic eruptions of kimberlites. They've supported studies on the brecciation mechanism, because they're also interested in what does it do to diamonds. Does it destroy diamonds? Does it enhance diamonds in any way? Because sometimes they find a big difference in diamond grades between the different facies of the kimberlite, between the diatreme facies and the deep down here. There's quite a difference, and also what you find here in the tooth rings. Okay, so this is a painting that was done by De Beers, which they commissioned, to show how a violent eruption occurs of a kimberlite pipe. Now, there was a very important paper that was published 2 years ago, which allow us to get a handle on why kimberlitic eruptions are so violent and so rapid. Some people looked at kimberlitic magmas, and they estimated that perhaps the eruption velocities could even be supersonic. It was so fast and so violent, and that is why there's a huge amount of volatiles released very suddenly, and therefore produces an extremely violent explosion which disrupts the magma and fragments it. Now, this paper by James Russell, who is from the University of British Columbia in Canada, and Don Dingwall, who is in Munich, they found a clue to how kimberlites are actually formed and why they ascend so rapidly and so explosively. And this is a very, very interesting study. So they did an experimental study looking at from kimberlite petrography, where you can find things like this. These are xenoliths in the kimberlites, and you can see that they've been eaten away by the kimberlitic magma. The kimberlite magma is actually actively eroding into the xenoliths, because those xenoliths are basically being digested and dissolving in that kimberlite magma. So you can see here a peridotite xenolith, which is being, and orthopyroxenes, which are being basically corroded and dissolving away in the kimberlitic magma. So what Russell et al. Did was they suggest that in fact kimberlites are just a strange form of carbonatite. They start off as carbonatitic melts of carbonatitic composition, and they evolve during this intrusion process. So you start off with a melt which is actually a carbonate melt, a carbonatite with a carbonatitic composition. And as we know, carbonatites, because they are mainly carbonate, should have huge amounts of CO2 in that melt. Now, according to this model, if you start adding mantle rocks into and start dissolving mantle rocks in a carbonatite, you start to assimilate and to digest these xenoliths. You start to dissolve pyroxene out of the xenoliths, and that drives up the silica content of the carbonatite. So the carbonatite melt starts to evolve in its composition from a pure carbonate melt to something that is increasing in its silica content. And what this diagram shows, this bottom one here, unfortunately it's not going to focus any better than that. This is a diagram that shows silica versus the solubility of carbon, of CO2. And it shows that as you increase the silica content of a carbonatitic magma, the solubility of CO2 decreases. So as you have more and more silica in the magma, there is less and less CO2 that can stay dissolved in that magma. And so what they're simply saying is that this is a model that involves clinopyroxene assimilation by melting of the xenoliths in that magma. And this is very rapid because the magmas are quite different composition of the CPX, and the CPX is simply eaten away very rapidly by the magma, and the magma then changes its composition, and as it changes its composition, it has to exsolve the CO2 that can no longer be dissolved in the magma. It comes out of the magma and comes bubbling out. But what the effect of doing that, the effect of adding silica is to actually increase the viscosity of a magma. But by adding a mixture of bubbles and silica, you're actually vastly decreasing the actual viscosity of the magma. So the magma is buoyant and with a very low viscosity, so it is extremely buoyant, and therefore it will shoot up very, very fast from great depths. So as long as you've got a structure that it's following, which would be these lineaments, you've got some kind of a structure that going all the way through to the top of the crust, these melts are going to ascend very, very rapidly. And the more they're going up, the more they are dissolving these clinopyroxene xenoliths, and they're basically just generating bubbles, and they're simply shooting up through the crust with no problem at all at very high buoyancy rates, very fast intrusion rates, and very low densities. So this is what basically aids the superfast intrusion process, and that is what can explain not only the eruption mechanism of kimberlitic magmas, but also the origin. We know that carbonatites, we know very well how carbonatites form from experimental petrological work that has been done over the years. And we can take a piece of metasomatized mantle, and you will partially melt that, and you generate a carbonatite at a particular under particular pressure and temperature conditions. So carbonatites are far more common, and we can generate. We see huge carbonatite complexes on surface associated with drift zones and so on. But now we have a mechanism for generating kimberlites out of the same kinds of magmas if they assimilate a lot of mantle material. And there is work that has been done recently, and it's now just been published very recently in Lithos by a group from Germany, which show that there is a strong link between kimberlitic magmatism and carbonatite magmatism. In all the provinces where you find kimberlites, you also find abundant carbonatites. And there are many such examples. So let's look at the big hole in Kimberley. This is the type kimberlite. Kimberlite as a rock type gets its name from the town of Kimberley, which was a mine originally discovered in about 1869 or something. And by about 1870, they had discovered this yellow rock that they were mining turned into a blue rock when they went further down. You can see the big difference in the color between the deeper parts of this and the near surface where it's yellowish, and that is the weathered kimberlite. And this is at that time it was the biggest man-made hole in the world. And and the mine actually closed down in 1914. So there was quite a lot of of diamonds produced there. 14.5 million carats of diamonds came out of this hole. So this is what you see today. Today there's a very good museum and a diamond museum next door to this big hole in Kimberley. So South Africa is a big producer, and currently its largest producer is the Venetia mine in the Limpopo province, which produced 8.5 million carats in 2005, at an average grade of 133 carats per 100 tons. And this is more than half of South Africa's total production. So South Africa historically has had many diamond mines, but now it's come down to one big one, which is the only big mine that De Beers still owns in South Africa. De Beers, which is a company that started in South Africa and Kimberley, does not own any mines anymore in Kimberley. It sold all its assets over there, and is concentrating more on the one big diamond mine in South Africa, as well as the big diamond mines in Botswana and Namibia. The world's biggest diamond producer is Botswana, which has got 3 big or 2 very large and 1 or 2 smaller kimberlitic diamond mines, and they are owned in a joint venture between De Beers and the Botswana government. And in Namibia you have the highest quality secondary diamond deposits in the world, which are the marine diamonds along the coastline, which are a very, very high percentage of gem diamonds, and that's also owned by De Beers in a joint venture with the Namibian government. Okay, so kimberlites have in most other kimberlite pipes, aside from this Venetia, which is very rich at 133 carats per 100 tons, and the average value of the diamonds was, back in 2005, $55 per carat. So you can multiply 8.5 million by $55 to get the value of the actual production out of that particular mine. But other kimberlite pipes, usually which are diamondiferous, have usually a lower grade, just a few tens of carats per 100 tons. And when you look at alluvial diamonds in South Africa that's mined out of the rivers, the grades are very much lower. You're looking at only about 1 carat per 100 ton or less for the alluvial diamond operations, which I will talk about in the next lecture. I want to show you a very interesting diamond mine. This is not in South Africa, but in Lesotho, that country that is completely surrounded by South Africa, where these diamonds are actually intruding through the Drakensberg lavas. And this particular mine is sitting at an elevation of 3,000 meters above sea level. It is the highest diamond mine in the world, and it is so high and so cold in winter that it snows in this area. The open pit has to be closed down sometimes because of snow, but they also have their own ski slopes for the employees of the mine. They can go skiing in winter. So, and here is one of the 2 pipes that you find at this mine. It's a big kimberlite pipe. This big one was mined out some years ago, and there is another active pipe, which is this one. What is interesting is that this original pipe was discovered in about the early 1960s or so, and it was developed by De Beers, and it was an active mine in the 1970s when De Beers was mining. Then De Beers mined this particular pipe out, and then they sold the operations to some other companies and they walked out. They basically said the grades were too low. It was sub-economic. The pipe next door, which De Beers left behind, turns out to have the best diamonds in the world, the largest diamonds in the world, which there have been quite a few diamonds that have come out of here which are 400 carats, and they are the best, purest quality diamonds, and there are quite a few over 100 carats. And in one weekend in about 2007 they found 2 diamonds more than 100 carats, including one that was about 400 carats, which was eventually sold for about $40 million, something like that. So very, very large. And also, unlike any De Beers mine, they allow you inside their sorting room, where they have the entire month's production of diamonds laid out in front of you. This is all diamonds. it's spelling out Letseng in diamonds. And here is a big, that's me. I'm holding a diamond that is this big. That's about 30 carats or 50 carats diamonds. And there are some pretty big diamonds that have been found. They are such a good quality that, you know, they sell for 10, 20, 30 million dollars. So the big difference here and what they did with De Beers is how fine do you crush your ore before you send it to the mill. Because these big diamonds are very rare, but they are extremely valuable. So it costs you more money to, if you want to, you know, you lose a lot of diamonds if you only crush up to a certain level. If you crush finer, you will liberate more diamonds. But then you will break the big ones. So you have to find a statistical balance between getting more diamonds out or getting fewer diamonds but with the bigger ones. And I think nowadays there is such a premium price paid for the biggest diamonds that it's well worth your while to throw half your diamonds away if you can find a few big ones. A few 400 carat, a few 100 carat diamonds will make up for the loss of half your production. So this is what this particular diamond company that's mining here, Petra Diamonds, is doing in Lesotho. Okay, now having looked at kimberlites and all of the you know, the diamonds and so on, I want to end this lecture by telling you about a very new, exciting development in kimberlite geology. And I'll come back to this diagram which I talked about in the last lecture, which is the new view of the interior of the Earth that's coming out from the work that's being done by seismologists, but in conjunction with people like Kevin Burke and Trond Torsvik, who's a paleomagneticist. So this new view of the Earth is that there are these two very large low velocity zones on the core mantle boundary. So the core mantle boundary is almost 2000 degrees centigrade. It's very, very hot. And sitting above this boundary is this large low velocity province, which may be, I don't know, about 100 kilometers, not quite 100 kilometers, but it could be, say, 50 kilometers in thickness, but extending for quite large distances around the Earth. So there is one that is underneath Africa, that is this one here, and there is another one underneath the Pacific Ocean, which is this one. And they have been given names. They've been called Tuzo and Jason, after J. Tuzo Wilson of the Wilson cycle and Jason Morgan, who was the first person to come up with the idea of mantle plumes. So, and of course Kevin Burke knew these people personally, and he's named these things after them. And the idea is that subducted slabs sink way down into the bottom of the mantle until they rest on this core mantle boundary, and where it's very hot and they undergo melting, and this basically spreads out until it hits the plume generation zones, and from there these things rise up to form plumes. And this is the only place where plumes actually go up, on the edges of these large low velocity provinces. Now, what is the observational data on which this was based? What they did, I'm sorry I don't have the diagrams to show that, but what Torsvik and Burke did was to take the 25 of the largest large igneous provinces that were formed in the Phanerozoic. They chose the Phanerozoic ones because then we know more or less where the continents were at the time of eruption. Once we go into the Precambrian, then, you know, it starts getting much more dodgy because we don't have that well constrained paleo positions. But for the Phanerozoic, and especially up to about the Ordovician, we have very well constrained paleogeographies in terms of seafloor spreading and the paleolatitudinal positions, and even the paleolongitudinal positions of the continents. So we can tell exactly where over the three-dimensional Earth a particular large igneous province was when the plume that formed it erupted. We can tell the longitude and the latitude. We can plot it on a world map and say, this is the point where a large igneous province erupted. Subsequently, the continent on which that large igneous province is formed may have moved due to plate tectonics. But we want to go back, because all of these large igneous provinces have been dated and we have the positions. So now we do paleocontinental reconstructions using paleomagnetics, and we work out the exact position on Earth where it was erupted, when it was erupted. And so you can draw up a global map showing where all these 25 large igneous provinces were in relation to the Earth and in relation to the Earth's interior. It turns out that when you do that, there is a remarkable coincidence between where these plumes were erupted and the edges of these two large low velocity provinces on the core mantle boundary. 23 out of 25 of these plumes coincide with the edges of these large low velocity provinces. If you take these provinces and you project their boundaries onto the surface of the Earth, then 23 out of 25 of these large igneous provinces, their positions coincide with the edges. And these things have got very irregular sort of plan views if you plot a map of these large low velocity provinces, but they are formed, the plumes are found coinciding with the edges of these low velocity provinces. So this is the point. And here is the map. This is a map showing the one underneath Africa. This would be Africa here, and what you see in red over here is the large low S velocity province, that is the one under Africa, which is this one here called Tuzo. So so in the next diagram you are seeing a map view with Tuzo, the outline of Tuzo projected onto the surface of the Earth. So here it is. Here is the map of the world with Africa. You can see Africa over here like that, and this red blob here is an outline of Tuzo projected onto the surface of the Earth. And in green is the positions of these 25 large igneous provinces of Phanerozoic age. Where did they erupt? And you can see that quite a number of these provinces have erupted all around the edge of Tuzo, which is quite remarkable. And you look at the other large igneous province, which is adjacent, the one over under the Pacific. When you project its outline to the Pacific Ocean and you plot other large igneous provinces, they also plot very close to this boundary of that large igneous province. There's only this one over here, this as a large igneous province, which doesn't plot close to these boundaries. So this was the basis on which Trond Torsvik, whom you see over here, a giant of a man, a Norwegian giant, a Viking if you like, and Kevin Burke, who is a giant of a man just in terms of his mind. They actually came together at my university. They were both visiting professors and both working with Lou Ashwell, who is a co-author on this paper over here, who is again another remarkable geologist. And so somehow they sort of gelled in terms of chemistry. Their ideas fitted in so well that they decided to become new collaborators, and they've been working over the last several years now on developing this model of plumes being generated from these plume generation zones on the edges of these large low S velocity provinces. Now, after this particular diagram was published and they decided, let's look at the problem of kimberlites. And so they thought, well, we have this big De Beers database of kimberlites and their ages. And so they got hold of the De Beers kimberlite database and started plotting different kimberlites of different ages. And since we know where the paleogeography was, they wanted to see if there's any relation to these large low velocity provinces. So they started to do that with kimberlites of different ages. So they divided up the De Beers kimberlite database into age provinces and then plotted them and see where they plot in relation to these Jason and Tuzo. So here is a kimberlite, some kimberlite pipes here of 505 million years. And here you can see them. These are the 500 million year kimberlites in southern Africa, the ones in southern Zimbabwe and Venetia over here. And this is where they plot in relation to this red line. Now this red line is the edge of Tuzo, and the other one is the edge of Jason, right? Now how they define the edge is in terms of the intensity, the 1% contour line of the slope of the change in intensity of that curve. They can do it completely blindly, just get a computer to plot that, because it is not like you deciding subjectively where is the outline of that low velocity province. It's simply done by taking the 1% change in the slope. So it's done automatically, generated by a computer. So there is no subjectivity involved in that in the calculation of where this red line is that surrounds this province. And so here it is projected onto the surface, and you see here that these kimberlites cluster on the edge of Tuzo. And they did the same with kimberlites of different ages. So here we see the 160 million year ones, and all the 160 million year kimberlites cluster on the edge of Tuzo. And they did the same with kimberlites of other ages. So, but look at this, there's a remarkable clustering of the kimberlites around the edge of this computer-generated projection of the low velocity province. And so, they conclude that there is a link between kimberlite magmatism and plumes that are generated from the core mantle boundary on the edges of these large low velocity provinces. And so this is a very provocative paper, very interesting in terms of kimberlite petrogenesis, and it was published about 3 years ago, 2010 actually, and it's out there waiting to be tested or refuted. But it gives you lots of food for thought now about where to prospect for kimberlites. You need to know the ages of magmatic provinces. Maybe you know about carbonatites, and you've got a carbonatite province, then you know that carbonatites now can change into kimberlites. If you've got any relationship between carbonatite magmatism and some plumes, then perhaps that is the way to go in terms of prospecting. But this paper has provided lots of food for thought for diamond explorers. So I'm going to stop there and give you some of these key references.
Okay, thank you, Sharad. A gente está aguardando as perguntas. Tem uma pergunta aqui do Francisco. Tem duas, tem o...
A maior produção mundial de diamantes vem de Argyle, na Austrália, né, que está relacionado com uma faixa móvel. A minha pergunta é o seguinte: ou seja, com lamproítos, com rocha lamproítica que, bom, diferente um pouco dos kimberlitos. A minha pergunta é se teria algum prospecto, teria alguma ocorrência em lamproítos também similar a, não do mesmo tamanho, mas geologicamente falando, similar em faixa móveis do sul da África. My question is about comparing Argyle is the biggest diamond production in the world. It comes from lamproites in the mobile belt. Do you have something similar, or not the deposit, but the prospect to have a similar fashion lamproite bearing diamond rocks?
We don't find many lamproites in southern Africa. I don't know of any that are, well, I should rephrase that, because actually when we look at the kimberlites in South Africa, we have two different types of kimberlites, type 1 and type 2 kimberlites, and there are differences between them, but one of those, and I can't remember which one it is, has more similarities with lamproites, because lamproites, again, it depends on how you define them, and because now that we know how kimberlites can form, they're forming by assimilation and starting with a carbonatitic melt. So maybe lamproites are just part of the same clan of kimberlites, of ultramafic rocks, which are coming from the mantle through, and very carbonate rich, which are somehow undergoing either assimilation or some other process. So I think that it will turn out that the differences between the different types of kimberlites and lamproites will just depend on its particular history, but they may all have ultimately a similar origin. In South Africa, we don't have a lot of lamproites. The only ones I really know of are the ones in the Luangwa Valley in central Zambia. And in Zambia, there we have an association of lamproites and carbonatites. There are in fact extrusive carbonatites in the Karoo, in the Luangwa Trough. They have extruded and formed carbonatitic lavas. So just like Aldonio Lengai, these ones are actually calcitic carbonatite or dolomitic carbonatites, so they haven't dissolved away like Aldonio Lengai, which is soluble. But there is an association between lamproites and these carbonatites. So it may be part of the same clan, and I don't know enough about kimberlite and lamproite petrology to tell you what exactly is the difference. But I would just imagine that they should be similar in terms of their origins. Because they seem to form by, at least the kimberlites now we see from the experimental work, form by assimilation.
Ok, então ele iniciou dizendo que não existiam lamproitos reconhecidos no sul da África. Ele voltou à frase dizendo que na verdade existem dois tipos de kimberlitos, são os dois tipos clássicos da literatura, são os kimberlitos tipo 1 e tipo 2, e um desses kimberlitos, que ele não lembra exatamente qual, é normalmente associado com lamproitos. Ele acha que agora que a gente conhece o mecanismo de formação dos kimberlitos, que é esse mecanismo que ele demonstrou de origem no manto e depois ascensão, assimilando, né, as rochas em seu movimento até a superfície, lamproitos podem, no final, pertencer ao mesmo tipo de família, mesmo clã, foi essa a palavra que ele usou, e compartilhar a mesma origem com os kimberlitos. Ele sabe da ocorrência de lamproitos the lamproites, carbonatites, you know it's in Zambia, it said. Yes, na Zâmbia Central, lamproitos associados com carbonatitos, né? E como modelo de origem de kimberlitos agora, né, começa o offset, como ele mostrou, né? Começa com uma origem carbonatítica, então ele vê como uma possibilidade de lamproitos e kimberlitos estarem talvez associados a uma mesma origem. Felipe, quer fazer pergunta? Tá legal, Francisco? Tá? Uhum. Não, uma de cada vez, senão eu piro. Então vamos lá, vamos ver se eu entendi. Apenas 1% dos kimberlitos são realmente férteis e um dos mecanismos de se conhecer essa fertilidade é através do estudo das granadas. Se ele conhece algum outro método de... Ok. Well, it's well known that about 1% of the kimberlites are actually fertile, and one of the ways of prospecting it is using garnets. And would you know of any other method of prospecting them apart from the garnet method?
Well, the best way to find kimberlites is actually geophysics, especially in countries where there's either deep weathering like here, or where they're covered by younger rocks like in Botswana, where it's covered. And a lot of kimberlite pipes have been found just using geophysics, and De Beers spent a lot of money doing geophysical exploration for kimberlites, because it's the easiest way to find them, and then you just drill and so on. But then of course the other method is, once you found the kimberlites, then you want to find the diamondiferous ones, and it was also an in-house developed technique by De Beers of the G9, G10 garnets, to find the type of garnets that are associated with diamonds. So I don't think there's any difference in terms of the actual prospecting. You have to find those diamonds and perhaps the other indicator minerals that are associated. Well, the indicator minerals just tell you kimberlite, but you want to find the particular composition of your garnets to tell you diamondiferous kimberlite. In terms of valuation, even if you find the diamondiferous kimberlite, as I said, maybe 1 in 100 diamondiferous kimberlites is going to be actually economic. That is actually the biggest problem. The most difficult problem is to determine if a diamondiferous kimberlite is actually economic. And the economics can vary quite a lot depending on the diamond size distribution. Like you saw at the Letseng mine in Lesotho, the very rarest, smallest, the largest stones, which are extremely rare, also extremely valuable. So you want to find those ones. But how do you sample a kimberlite for that? Because you may mine for several months, mining thousands of tons of material, hundreds of thousands of tons, before you find one big diamond. So how do you know that your kimberlite actually has diamonds of that size, unless you actually mine? It's like, they do bulk samples. Once you found a prospective kimberlite that is diamondiferous, you know that it's got micro diamonds in there, then you want to find the size distribution of your diamonds. That's the next problem, is to find the size distribution and to see how rare it is, and that will determine the economics. So this is a very difficult problem. It requires specialists, statisticians involved in working out the optimal size that you need to mine, and that will allow you to pick up the biggest stones with the biggest value. You need to know what is the quality of your average stone, which is what is the average dollar price you're going to get per carat, and that also varies quite a lot depending on where you are. Some mines may contain rare colors like deep blues or pinks, like in Argyle, which are very valuable stones, much more valuable than your normal white colors, and others will have very, very large stones like Letseng. So those are the real problems. It's even after you've gone through your 1,000 or 10,000 kimberlites and you found the one that is really nice and diamondiferous, you still need to evaluate that. De Beers has done, they've done trial mining of some of these kimberlites just for a couple of years, just to really get a good handle on what sort of grades you're going to get. And that's the sort of thing you have to do. You need really big bulk samples when you're looking for something that's in parts per billion range in your rock. And that might be valuable, and you have to be able to crush the ore without destroying it. And so those are the kinds of problems that you have. So one of the things that De Beers is doing is trying to save time in trying to find micro diamonds, for example, or big stones. If you find a kimberlite pipe and you're drilling a kimberlite pipe for evaluation, you don't want to destroy any kimberlites, right? Any diamonds. So you use as big a drill core size as you can find. So you get a big size core and you drill down into your kimberlite, and then you're going to sample that to find the diamond distribution. But even in that sampling process, if you crush that, you may accidentally crush diamonds. Then you're not going to get the right size distribution. So you want to be able to liberate diamonds from your sample kimberlite without destroying them. So they found a way of doing it by using microfocus X-ray technology. This is now, apparently Siemens has just come out with a desktop model, which is only going to cost a few $1,000s. But these models that we're talking about cost millions of dollars, and they use X-rays to do like a CAT scan, but of rocks instead of human bodies, which you find in a hospital. Siemens is the company in Germany that has developed this technology. We actually have a machine like that now for our paleontology department. We can take a rock that contains a fossil, and instead of spending 2 years chipping away the rock to expose the fossil, you can now get it in about 2 hours. You can scan the entire rock and get any slice you want in any direction you want, and it's got millions of slices through there at a 40 micron resolution. So this is what De Beers has been doing now for some years. They were the first people in South Africa, just like in the old days. They got themselves the latest technology and they got an X-ray scanner. So now they pass all the core through there, and they can pick out the diamonds in this core. They just can fine tune it until they can pick out the right density and the right contrast with the matrix. And they can actually work out a 3D distribution model of the diamonds, and they don't miss anything. So then it will be automatically computed the size distribution of the diamonds, and then you will know what is in situ. Even if you crushed it, you will still have to do all of that. They can now do this automated. So they can now pass a lot of drill core at a very fast rate through the machines to evaluate what are the small diamonds doing, and then hopefully they can extrapolate that curve up to the rarer and bigger diamonds. But it's helping them a lot in evaluating kimberlites. But this is the kind of things you have to do. You have to use the best technology available in order to evaluate kimberlites correctly, because it's a very difficult thing to evaluate kimberlites for diamonds.
Ok, então encontrar os férteis. Então tem todos a granada como indicadores, que é um método que se usa normalmente, mas ele ressaltou a necessidade de estudos geofísicos. Ele chegou a mostrar aqui na palestra que especialmente onde os cráteres estão muito erodidos, né, o levantamento geofísico é importante, e as chances são de acaba tendo mais chances de encontrar os kimberlitos com diamantes onde a quilha, né, está mais profunda. Ele chegou a comentar isso aqui. Bom, então a De Beers, por exemplo, gastou zilhões de dinheiros fazendo levantamentos geofísicos e utiliza isso como um método prospectivo importante, mas continua utilizando os minerais indicadores como os dois tipos de granada. Bom, além disso, mais recentemente, aí depois ele comentou que o problema não é tanto encontrar o kimberlito diamantífero, mas saber se esse kimberlito vai ser economicamente viável. Isso vai depender de vários fatores: tamanho dos diamantes, distribuição. Então ele citou que existem vários trabalhos, inclusive trabalhos estatísticos, que tem que ser feito para se conhecer a distribuição dos diamantes, a granulometria deles dentro do kimberlito hospedeiro. E o maior problema é realmente quando você vai furar e você corre o risco de perder os diamantes, né? Você tem um diamante grande, pode furar e destrói esses diamantes grandes. Então a De Beers também desenvolve técnicas, né, em que eles tentam recuperar os microdiamantes junto com os diamantes grandes, mas assim mesmo eles têm que furar. Então, mais recentemente, o que eles têm feito é um escaneamento por raio-x. Então eles fazem o escaneamento por raio-x, descobrem onde estão os diamantes que são mais importantes, continuam a construir curvas estatísticas a partir dessa distribuição, e eles têm feito isso de maneira totalmente automatizada. Basicamente, os testemunhos passam por uma linha automatizada que vai sendo escaneada por raio-x. Eles conseguem fazer uma reconstituição 3D do que está passando pelo raio-x, como se fosse mesmo uma tomografia, uma radiografia, e aí localizam os diamantes, as zonas, né, que estão com os diamantes que interessam mais para serem prospectados. Então, a partir disso é que eles planejam como vão continuar a lavra. Mas, basicamente, é muito difícil você saber se um kimberlito vai ser economicamente viável ou não sem começar a furar, né? A outra pergunta é? Uhum. Uhum. Okay. Is there any sort of relationship between the different types of diamonds with the faces of the kimberlites you showed?
I'm not sure about. I think that most of the shapes that you find of the diamonds in a kimberlite are generated way down where the diamonds actually formed. There's not that much modification in the kimberlitic magma. It rather reflects the conditions under which the diamonds were actually formed. And you can see that when you see diamonds that have got crystalline rims around them. You find a gem diamond with a funny rim around it, and so on. And these all relate to crystallization conditions in the mantle when the diamonds are generated. That's another whole question of how do you form diamonds in the first place? Where does the carbon come from, and under what conditions are diamonds, formed? Some people think they're formed out of a fluid phase, which infiltrates into the mantle and then crystallizes under certain conditions. Also, we get there's a lot of studies done on the different colors of diamonds, which are a result of the nitrogen content in the diamonds, and which affects the ordering of the crystal lattice in the diamonds. So, at least some of the colors are due to nitrogen. There are other reasons as well, which all relate to the crystallization conditions in the formation of the diamonds, rather than conditions in the kimberlites. The kimberlites are coming up so fast, and because now we can see that in fact diamonds are found in xenoliths. So that's where the variations, morphologies come from. There may be some things like a resorption of diamonds in the kimberlite magma that might change from an octahedron to a dodecahedron, for example, where the diamonds become smaller and they change in terms of the morphology as they're being resorbed in the kimberlite magma itself. But those are just changes in size, but not related to the facies itself. The facies might relate to the sorting of diamonds through some process, including the eruption process, where things go up in the sky. So diamonds can actually go up into the sky and then fall down again. And so that sorting process would be sedimentological, the way you find in pyroclastic rocks. But that would be the only difference that I could see. There are, however, kimberlite pipes, and including the Argyle diamonds in Australia, in the lamproites, where there is a big difference in the grade between the diatreme facies and the crater facies. So there may be either an early phase which was more diamond rich, or something of that sort. But there can be a difference in the grade, but I'm not so sure about the morphology.
Não existe uma relação que ele conheça entre os tipos de diamantes, né, as mesmas cores, com as faces dos pipes, porque basicamente essas características parecem ser adquiridas durante a formação dos diamantes. E eles não são formados dentro do magma kimberlítico, né? Eles são formados em algum outro local, dentro do manto, e os kimberlitos acabam trazendo eles até aqui em cima. A gente sabe disso hoje porque os diamantes são encontrados inclusive dentro de nódulos mantélicos, né, que são trazidos pelos próprios kimberlitos, né? O transporte pode de alguma maneira mudar o tamanho, basicamente o tamanho de alguns diamantes durante a ascensão do pipe kimberlítico, mas assim mesmo não há uma relação direta entre as faces, né, dos diatremas ou dos pipes com as formas ou os tamanhos e tal. Existe uma relação com a cor. Se descobriu que algumas cores dos diamantes, né, estão relacionadas a nitrogênio, que acaba mudando algumas das características cristalográficas do diamante, e assim eles acabam adquirindo a cor. Mas isso também estaria relacionado aos seus locais de formação e não ao transporte pelo magma kimberlítico, ok? Beleza. Diana, tem alguma pergunta? São 4. Beleza, eu vou explicar por quê. A Diana está certa, são 4h15, então a gente não vai fazer o coffee break agora. Em atenção a alguns colegas de outras unidades que estão indo para o campo, nós vamos continuar com essa lecture, a última agora, e a gente faz, no final de tudo, a gente sai pro coffee break, tá legal? Então não vai ser um coffee break, vai ser um end coffee, sei lá como é que a gente chamaria isso, não tem break, né? É o happy hour com café. Então a gente vai responder só uma perguntinha, e as outras 2 perguntas a gente de novo assegura que vão ser passadas ao professor e remetidas aos colegas posteriormente. Qual é a pergunta? De onde vem? Carbonatítico. Ok. Okay. So I have this question from Brasilia, and taking the Russell's model for the origin of kimberlite, starting with the carbonatitic magmas and then assimilating the silica-rich rocks. So you have all these diamonds in kimberlite. So because of this association with the carbonatic magmas, would it be possible for us to find diamonds in carbonatites, and since the origin of the kimberlites would be associated with carbonatites, or not? A última parte da pergunta tem uma outra. And if you know of any carbonatites that would be with diamonds.
You see, the thing is that the diamonds are not crystallizing out of the magma. The diamonds are actually picked up accidentally in the xenoliths of mantle material from that lithospheric keel where the diamonds are found. So you may have a carbonatitic magma that is coming through that keel, but then it has to pick up xenoliths of peridotite or eclogite and start dissolving them. It's like a Coca-Cola, and you put aspirin in Coca-Cola, it's going to it's going to shoot out. So you need to have that. You need to put the diamonds in the carbonatite. Okay. So the diamonds are actually the inclusions in your aspirin that you put in your Coke. So that's what you need. And if you don't have that, you're not going to get diamonds. And a carbonatite that has reacted with diamond-bearing lithosphere is called a kimberlite. So that's what it is.
Bom, na verdade, o que é necessário é que haja essa reação do magma carbonatítico para que os kimberlitos se formem, então eles possam sample, né, eles possam coletar os diamantes das suas áreas fontes no seu processo de ascensão até a superfície. Então, basicamente, se você tem um magma carbonatítico que consegue fazer isso, ele mesmo se torna um magma kimberlítico, né? And you are not aware of any occurrence of diamonds in carbonatite. Se não há ele não conhece nenhuma ocorrência de diamantes em carbonatitos, ok? Então, agora a gente encerra as perguntas, pode ser? E vamos para a última aula dele e no final, então, a gente passa para o happy hour, tá? Com café. We're not going to have the coffee break today because we have our colleagues somewhere else and they are going to a field trip tomorrow. And so they asked us to carry on so we could finish about 5 o'clock and then we in Rio we can go for the coffee, okay? Okay, thanks.
Our final lecture of this course on the Cenozoic evolution and metallurgy of Southern Africa, heavy mineral sands and diamonds. So, since we already started talking about diamonds in the previous lecture, and we saw that the diamonds appear as in the primary rock, which we call kimberlite, and I mentioned all the secondary diamond deposits, the alluvial diamonds and the marine diamonds. So this is what happens next in the diamond cycle. So we have secondary diamonds, alluvial diamonds which are found in river basins that drain the kimberlitic source area and adjacent to modern river channels, as well as in ancient river channels such as in terraces where the drainage is subsequently shifted. So these diamonds are all derived from the erosion of kimberlites, and diamonds are very stable in the surface environment and very hard. So once they've been released from the parent rocks, they can travel for great distances. And diamonds can actually reach the sea where they will form marine diamonds. They can be, they can enter the sea and then be modified by various processes, by beach activity, and be incorporated in conglomerates along the shoreline, or they may be trapped on the sea floor in little traps, sedimentological traps on the sea floor. And in the case of Southern Africa, we have had, we've got the world's most extensive marine diamond mining operations in Namibia and offshore South Africa, and it is possible that this may also be profitable in other parts of the world where you have the right conditions. So let's once again look at the sort of diamond deposits that are found in South Africa. This time we are not looking just at the kimberlite pipes. We're actually looking at primary and secondary diamond deposits. So you can see there's quite a lot of different diamond deposits, and I'm just pointing out here the big primary kimberlite pipes. This is Kimberley with a whole cluster of kimberlite mines around here. The Premier diamond mine where the largest diamond came from, and the Venetia mine, which is our largest diamond producer in South Africa. So the secondary diamond mines are actually also found mainly in this area where the primary diamond kimberlites are found, which is not surprising at all. And they end up in the drainage basins or the paleo drainage basins, which eventually end up being transported by the Orange River to the sea. And there's also other drainage systems which also contain alluvial diamonds. And then notice that this is the whole Karoo Basin here, which is older than most of the kimberlite pipes, because these are Cretaceous, Jurassic to Cretaceous kimberlite pipes. So the Karoo Basin is actually older and therefore does not have any and plus most of the Karoo Basin is sitting on Proterozoic lithosphere, which is a mobile belt, and therefore does not have diamondiferous kimberlites. So in the southern part of the country, there are no diamonds. Most of the diamonds are found, including the Kafar craton in the kimberlite pipes, and all the secondary deposits are on the Kafar craton or in rivers draining from the craton going towards the sea. What you don't see is the same number of alluvial diamonds found in the Limpopo River, but there must be some potential here because there are some big, very large kimberlite pipes here in this drainage basin of the Limpopo. And if one looked in Mozambique at the paleo drainage of the Limpopo, perhaps one could find big diamond deposits just like you do along the Orange River, which is draining the rest of the Kafar craton. So I would say there is potential there for alluvial diamonds. Now the marine diamonds are very interesting. This is the area offshore South Africa where we are mining marine diamonds. And it also continues in Namibia, because in this is only showing the deposits in South Africa, but the richest marine diamond deposits in the world are on this coastal stretch of Namibia, extending from the Orange River mouth northwards for about 100 kilometers or so. This is the so-called Sperrgebiet. That's a German name for this region where nobody else, aside from the mining companies, were allowed in for a very, very long time. And this is the place where you find marine diamonds that are mined on shore and also still underwater and being mined by ships. So the general idea is that these diamonds have moved from their source in the kimberlites to the coast in paleo drainage systems and also in the modern river systems. So the way that alluvial diamonds are mined, there's usually very small scale operations. This is the place and a space for small scale workers, because it's not, none of these operations are very rich or big enough for big mining companies to be involved in. They want to find a kimberlite mine where they can mine for many years and mine millions of carats per year. They're not interested in these small workings. So traditionally in South Africa, the alluvial diamond mining has been done by small scale workers, and I will show you what the operations look like. So they usually have to remove any overburden using small bulldozers and so on to expose the diamond bearing gravels in the terraces around the modern rivers, because there has been major changes in the land surface, which has been uplifted. So the rivers have cut down and they've left behind high level gravel terraces which contain these alluvial diamonds. And then they recover the diamonds by means of rotary pans and gravity sort of concentrators, and then they use various processes which I'll show you, like grease tables, to separate the diamonds. So we have a lot of alluvial diamonds in the lower Vaal River basin, and it's been mined for more than 100 years in this area. And most of them are mining recent river deposits, but in terraces which are above the current levels of the active river systems. And sometimes very large diamonds can be found. One of the largest was a 511 carat diamond, which was found from one of these small scale operations. So this is a typical small scale operation with a rotary pan, where they're mining gravels just on the banks of one of these small rivers. A slightly larger scale operation will be mining, and it will have a mine dump like this with a conveyor belt, and from that they will have a feed going into a mine. There may be a small sorting plant to size grade the intake to remove the large pebbles. Basically, they will have, because there's a mixture of large pebbles and smaller gravel, and most of the stones that come out of here are very, very small. So they first screen all the stuff to remove all the big, large pebbles, because and the screens are big enough to let through even what could be large diamonds. So you would have such operations, and there were some sort of medium scale mining companies which have got fairly large operations, and what they are mining here, which you can see, is the paleo channel, a paleo sort of a meander of one of these rivers, like the Vaal River, which is still an active river today, but it had an abandoned channel in the past, which has now been filled in with sediment. So now they can go back to these paleo channels, remove the overburden, get to the gravels, which are diamondiferous, and mine them. So once they've got the gravels and they go to the sorting plant, this is the way it's treated. So this is now much reduced in size after you've removed the large size of pebbles, and this is the conveyor belt feed going into the separation plant. And nowadays they have got machines that can detect the diamonds on the conveyor belt. So diamonds actually fluoresce under ultraviolet lights. So they have a machine that can pick up diamonds by passing through this machine, which then picks up the fluorescence, and they've got small little air jets which basically pick up a fluorescing diamond and shoot it into a different stream. And they do this several times, so they don't miss anything. A diamond might be hidden under something else, so they will run a circuit, and they'll do it a few times until they're able to shoot diamonds off into a separate circuit, which will then go onto a grease table. And a grease table depends on the property of diamonds, that the surface of a diamond is attached to grease, and is actually very hydrophobic. So it will actually repel water, but will be attracted to grease, whereas other kinds of silicate pebbles will not be attracted to the grease, only the diamonds. So these tables have got grease on them, very fatty sort of grease, and it's a kind of conveyor belt which goes back around and comes back. So all the rocks that do not stick, they simply drop off the table. The diamonds that stick to this carry on, and they actually get embedded in this grease layer. And then they remove the grease, and then they take diamonds out of that. Now, and then out of that stream that is selected by these machines that detect the fluorescence, they eventually end up putting them on a jig. This is a grease table, by the way, and it's vibrating, so the water is jumping up and down, and the rocks that do not stick to the grease get bounced off, and the diamonds that do remain behind. And then the final product they get is a bunch of stones that have been collected, and out of that they hand pick with somebody who's trained to look at them, and you can find like a nice diamond over there, or there's another one or two in the background like that. So these are fairly small stones, not very big, but they would keep a small operation going, and they might get a few 100 carats a month or something like that. And it also depends on the value of the stones. And occasionally, every now and then, they might find a big stone, which will be as a bonanza. So South Africa used to produce a lot of the world's diamond production. Initially, when diamonds were discovered in 1867, there were only two producing countries in the world, Brazil and India, where diamonds were the main source for most of human history. The only source of diamonds were the alluvial gravels at Golconda in India, until diamonds were discovered in Brazil. But then when the primary source of diamonds was discovered in South Africa, in Kimberley, this was a massive diamond rush, and then South Africa's production climbed very, very rapidly, and South Africa then had the monopoly on the diamond market for a very long time, and until other countries and other diamond fields were opened up in the 20th century. In the early 20th century, they found rich diamond mines in Congo, and then the ones in Namibia, and so on. So South Africa's share has basically fallen, while world production has been climbing due to the discoveries elsewhere in the world, in Russia, in the Second World War, and afterwards, and then more recent discoveries in Australia and Canada. So that's the state of play of the world sort of diamond market. Diamond production in South Africa, well, in 2001 there were 15 kimberlite mines, 17 alluvial mines, 17 marine diamond mines producing 11 million carats. But this has shrunk quite a lot. Many of the kimberlite mines have closed down or sold by De Beers, and all they are doing in some of those mines is just retreating the old dumps. They had stockpiles of xenoliths, for example, in one of the old mines, and they let them just kept them outside for a couple of decades until they start to decay by weathering, and then it's easier to remove the diamonds from those mantle xenoliths. Okay, let's look at the marine processing of diamonds. These are recovered from the seabed by modified sea vessels or floating mines that are equipped with all the tools that are needed, including pumps to pump out all the sediment from the sea floor, and then they've got screens and media separation plants and recovery plants, and there are smaller operations that simply vacuum up the sediment and sort it on shore. But the biggest of these is the De Beers marine vessel, and you can see this is a very well supported ship with a helicopter landing pad, and this is how they are mining on the sea floor off the west coast of South Africa and of Namibia. These ships, they have huge dredges, and they basically vacuum up they are given a concession area, and they do very detailed mapping with sonar of that seafloor to find exactly the topography of that seafloor, and they target particular potholes on the seafloor where diamonds might be trapped, and then they just vacuum up everything from there, and they sort them out and get recover diamonds from there. Okay, so this was sort of a snapshot view of the diamond industry in South Africa, both the kimberlites and the alluvial and the marine diamonds. Now I want to concentrate on the other economically important mineral deposits that are found in Cenozoic rocks in South Africa. What is quite interesting though, is we do not have that many alluvial gold deposits. I must actually rephrase that. That's what I just said. If we go back to that original map which showed the diamond mines and diamond occurrences in South Africa, and the fact that rivers have been carrying diamonds to the sea, those same rivers are draining things like the gold fields in the greenstone belts and so on. The thing is that the Witwatersrand gold is very, very fine grained, so you don't find any gold in the rivers. If you pan the rivers in the Witwatersrand, you don't find alluvial gold. Even the world's greatest gold field, because you don't get big nuggets there, you don't find gold in the rivers. But you do find that kind of gold in Barberton and other greenstone belts, and they would have been eroded at the same time as the kimberlites. And so the rivers that carry diamonds to the sea also carry gold. So in fact, a few years ago, Anglo-American Corporation in South Africa signed a deal with De Beers to mine gold out of the same seabed where they were getting diamonds. Now, because a company gets a license to mine a particular commodity only, De Beers only has a license to mine diamonds. And if they find gold, they're not allowed to keep it because they're not legally allowed to own it. But if they sign a joint venture with Anglo-American, then Anglo-American now has a license to mine gold in the sea floor, and they're in a JV with De Beers. So De Beers sucks everything up of the ground, and they keep the diamonds and give the gold to Anglo-American. So there is actually a lot of money to be made from this, from seabed mining of both diamonds and gold. Now, I know that in places like West Africa, There are alluvial diggings where the small-scale workers, the garimpeiros, actually find both diamonds and gold from the same diggings. But this is being done on an industrial scale offshore South Africa. Okay, so in South Africa we don't have small-scale workings for alluvial gold, but in Zimbabwe, where we go to the north, most of the gold production in Zimbabwe comes out of Archean greenstone belts, and there's a lot of gold in the rivers. And they've been mining this for more than 1,000 years, and it is still going on. There are people you'll find still making a living by panning gold out of the rivers in the greenstone belts in Zimbabwe. So let's look at the other important commodities that are coming out of our Cenozoic sediments in South Africa, and the most important one is heavy mineral sands with titanium and zirconium in the form of rutile, ilmenite, and zircon. So this is a very important topic because there are quite a few such deposits in the world, on the mainly all around the coast, for titanium and zirconium. There are, all the ones shown in red on this map are mineral sand deposits, secondary deposits that are concentrated in beach sands, whereas there are only a few hard rock mines for titanium or zirconium, like Allard Lake in Canada, which is a major titanium mine, and places in Norway, Panjihua in China. Very few sort of ilmenite deposits that are being mined. Elsewhere in the world, we have these marine concentrations of heavy minerals in heavy mineral sand deposits. And there is a big concentration of these heavy mineral sand deposits on the east coast of Africa. In fact, extending from South Africa all the way, in fact, to Somalia, there are known heavy mineral sand deposits. I don't know why there are so few in Brazil. There may be more that are not on this map, but apparently Brazil does not have that many compared to what is found on the African coastline. So maybe it has something to do with a tectonic or uplift history of where these minerals come from. So what is in the heavy mineral sand? Well, aside from quartz, which would be the common thing in these sands, the heavy minerals might be pyroxenes, magnetite, garnets, aluminosilicates, but the ones of economic interest are ilmenite, rutile, and zircon. And these are the ones that are actually mined economically from these heavy mineral sands. These are heavy minerals which may vary in their percentage from 1 to 15% of the actual of the sand itself, whereas all the heavy minerals together may constitute up to 20% of the sand. But the valuable heavy minerals are ilmenite and rutile and zircon. Now these figures are a bit outdated, they're about a few years old. I don't know what the current figures are, but a few years ago ilmenite was selling at about $100 a ton, and if it was treated into a titanium rich slag, it fetched $600 a ton. And from that you could also produce pig iron from smelting of ilmenite. It's iron titanium oxide. So you could fetch $250 per ton for pig iron and $600 per ton for slag. So this was a way to provide value to ilmenite producing these products, which you sell at a much higher value. Rutile was fetching about $500 per ton, and zircon fetches $900 per ton. So these are things that you really want in terms of economic mineral deposits. Now, there are a lot of deposits that are known in Africa. There are some in West Africa, in Senegal and Sierra Leone, but the main ones are on the east coast of southern and East Africa. There are also some on the west coast of South Africa here, Namakwa Sands, and then we've got a whole range of deposits from South Africa, Mozambique, into Tanzania and Kenya, and into southern Somalia as well, and also some in Madagascar. So there are quite a lot of these deposits. So why are there so many in Africa? Well, it may depend on having a source, firstly of rocks in which you'll find zircon and ilmenite and rutile. And we know that the whole east coast of Africa is a big orogenic belt, the Mozambique belt, which has a lot of zircon and possibly a lot of rutile. And we also have the Karoo volcanic rocks, which are found in Lesotho and along the Libombo Mountains in South Africa and in Mozambique, which are a major source of ilmenite. So we have a mixture of different rock types which will provide this mix of rutile, zircon and ilmenite. But there is another factor at play here. Why is Southern Africa so endowed in these heavy mineral deposits? And that has to do with the uplift history of Southern Africa. And if you look at Africa as a whole, we see, well, this kind of shows you the vegetation belts in the equatorial regions. But in the north of Africa is the Sahara, which is like places like West Africa over here. It's a very flat terrain, except for a few isolated mountain ranges in there. But Southern and East Africa, by contrast, have got very elevated topography. And you can see that here in this map, which shows the topography of Southern Africa. And what you see in Southern Africa, which you don't find in North Africa or in other continents, is an extremely elevated interior plateau. So if you go from the coast, you rapidly go upwards in elevation until you hit this plateau, and then it's very flat in the interior. So the interior of South Africa is an elevated plateau at an average elevation of about 1,000 meters above sea level. And that is by contrast to the average elevations of North Africa or Europe or the continental interior of the Americas, which is about 400 meters above sea level. So there is something very peculiar about this region in Southern Africa as well as East Africa, which makes it elevated. And what seems to be responsible for this is what has been called by Andy Nyblad the African super swell. There is a region of anomalously hot mantle in Southern Africa, above Tuzo, by the way, and that stretches from the core mantle boundary towards East Africa as a big region of anomalous mantle in terms of seismic velocities. And it's interpreted as something with anomalously hot mantle, which is more buoyant and has lifted up this whole Southern African region, at least for the last 30 million years, when it has been stationary over the same part of the mantle. Because Africa was drifting until 30 million years ago, when it started colliding with Europe, and then it got pinned in that position and has been sitting over the same part of the mantle for the last 30 million years. And that's allowed shallow mantle convection to establish a basin and swell topography in North Africa, but the super plume has buoyantly risen up over Southern and Eastern Africa and has given us an anomalously high elevation. This is dynamically supported topography that we see in Southern Africa. And this elevation is what you see responsible for the major escarpment that you see on the Drakensberg Mountains, which I showed earlier when I showed the Karoo Igneous Province, which has this very, very prominent scarp with these mountains going up to 3,000 meters. And that is a very recent elevation of the whole subcontinent. And this recent elevation of the subcontinent has resulted in massive amounts of erosion. And that erosion has eroded things like the several kilometers thick, at least 2 kilometer thick Drakensberg lavas, which all contain ilmenite. So there's huge amounts of ilmenite entering the coastline of South Africa from the erosion of these volcanics. And the uplift is also exposed Precambrian basement, which is rich in zircons and in rutile. So this is one of the reasons why we have such rich heavy mineral deposits in Southern Africa, and maybe why you don't find them in Brazil. So this continental uplift has happened in a very recent times, 20 million years, 5 to 5 million years. So you see this major uplift over here that's produced the Lesotho highlands, and there's been rapid erosion along that front, and that is deposited as Cenozoic coastal sediments over here, in which you have the concentration of heavy minerals on the east coast of South Africa, but also to a more limited extent on the west coast of South Africa. And so we find on both sides of the coastline heavy mineral deposits. So this is what is responsible for the huge amounts of ilmenite, this rapid uplift and erosion of the Karoo volcanic province in the last 5 million years, and producing these spectacular scarps through retreat by erosion, has dumped a whole lot of sediment into the oceans, where it is being reworked as these heavy mineral deposits. So how do you form these mineral sand deposits? It's simple. From the source rocks which are being eroded, the rivers carry these heavy minerals as bed load until they enter the sea, and where they enter the sea, they are redistributed by longshore currents in the ocean. So they spread out, and they are spread out along the beaches by these longshore drift process. So we end up with the distribution of these heavy minerals along the coastline, and then when they are exposed at high tide, the winds which are onshore in this area, they actually blow the sand containing heavy minerals to form sand dunes, which form an entire corridor along the whole coastline. The entire coastline of the east coast of Africa has got a line of sand dunes, aeolian dunes, that extend all the way to Somalia. So it's thousands of kilometers of these dunes, and they are rich in heavy minerals. So this is the process, and you can see here a map of the northern KwaZulu-Natal coastline, the eastern province of South Africa, and there are modern dunes that you see here stretching all the way towards Mozambique, and these are being mined by Richards Bay Minerals at Richards Bay. This is our biggest heavy mineral sand deposit and one of the largest in the world. But also what people have been who have been thinking about this, there are also paleo dunes related to different changes in the coastline, because in the past, when the sea level was higher, the coastline was further inland, and it was producing the same kinds of dunes with the same process. So there are paleo dunes, and here's a line of paleo dunes along a paleo coastline, but these dunes were older because the sea level was there in the past, and that may have been a few million years ago. So there's been that much more time for diagenesis to take place. And if you remember what I had to say about the formation of red beds form from the alteration diagenetically of these labile minerals due to diagenetic fluids, oxidized fluids moving through them. So that's what happens in these paleo dunes. The paleo dunes have had more time and more fluids going through over that time period to oxidize the heavy minerals like the ilmenite and produce lots of clay and lots of secondary iron oxide. So those paleo dunes are red in color and much more clay rich, and it's more difficult to extract the heavy minerals than it is from the recent dunes, which are very white and have very fresh minerals in them. So if you go to Richards Bay along the coastline, this is a view from Google Earth of the operations, and what you see is the current coastline where the beaches are, and then this line of vegetation, which is the vegetated sand dunes, where the beach sand is blown by onshore winds to pile up the sand in these aeolian dunes, which with time get vegetated by and stabilized by vegetation. So what Richards Bay Minerals are doing is they are mining these dunes. Now that is an environmentally destructive process because they are removing the indigenous vegetation. So it's been very controversial, and they've been forced by environmental legislation to rehabilitate the dunes and plant the same indigenous vegetation after they've reconstructed the dunes but removed the heavy minerals from there. So you can see what they're doing in their operations is simple. They build a little dam behind the dunes, and so it's filled with water, and they have a barge with high pressure jets because these dunes are actually unconsolidated. They are Pleistocene to Holocene dunes, which are mainly unconsolidated. They just need a high pressure hose, which you'll see somewhere here. You can see these dunes are full of heavy mineral layers. These black layers here are all heavy mineral sand. So they're running at a few percent, maybe 10, 15% of heavy minerals, very, very rich in heavy minerals. But there is the vegetation on top. The vegetation needs to be stripped out, and then they just take, look at these heavy mineral layers, very, very rich, but in unconsolidated sands. So they just have to take this, and all our beaches are like that. I mean, this is taken in the Eastern Cape, about a few hundred kilometers from the Richards Bay, and you walk on the beach, and this photograph is in focus. This rock is in focus, but this looks like it's blurred. But that's just the way the wind blows the sand in ripples. The finer quartz particles blow away, and it leaves behind this on the surface the remnants of this black sand. So there's lots of this in all the beaches, and in Richards Bay in particular there's a very high concentration of these black minerals. And here's another example, this time in Sipingo. Again, when the wind blows and the water and the sediment is wet, it's kind of it blows away all the lighter stuff and leaves behind this lag of black sand. So what they do at Richards Bay is they have these dredges and a very high pressure hose which breaks up the sand, and then they simply pump it into a heavy mineral separation plant and extract it that way. And then they have to rehabilitate the dunes once they removed it. And you can see in this photograph here, this is the original dune. They've now stripped the vegetation and they are mining this dune, and you can see the color is dark gray because it's full of heavy minerals. Once they've extracted this from the plant, they dump the quartz sand back, and you can see that this is much whiter in color because all the heavy minerals have been removed. And then they plant the indigenous vegetation again. They build up the dune and try to rehabilitate behind them. So they're basically mining along the dune, rehabilitating behind and mining in front. So that's what they're doing here at Richards Bay. And this is one of the largest heavy mineral mines in the world. There's another big one like this in Western Australia, but this is certainly one of the biggest titanium and zircon producers in the world. So, and it's very simple mining, just high pressure hose. Now the other mine is Hillendale, which is the one that's in the older dunes inland, and you can see the color is very different. The color is red, and this red color is from the diagenesis of those heavy mineral sands to produce clay minerals from the breakdown of pyroxene and also iron oxide from the breakdown of ilmenite to form hematite. But so here this is a little bit more difficult. It's still easy to break open with hydraulic hoses, but they have to treat, they have to flocculate the clays in order to settle the clays and get rid of the iron oxides to get a concentrate of the heavy minerals. And I'll end by looking at the Namakwa Sands operation on the west coast of South Africa. This is Cape Town down here, and we have Saldanha Bay here, which is a big port. And along the west coast in this area here, there are these heavy mineral deposits that are being mined by a company called Namakwa Sands. And what they do is they produce a concentrate of ilmenite, rutile zircon, and then they send it down to a smelter which they have here at Saldanha Bay. So they produce a higher quality product of pig iron and a slag which is rich in titanium, and then they export it from the port in Saldanha Bay. So this is their plant, the metallurgical plant, the smelter at near Saldanha Bay, and this shows the entire operation. And the final products that they get are zircon and rutile concentrate, and then from the ilmenite they produce a titanium slag which sells for $600 instead of $100 per ton, and they have a pig iron plant which also fetches about $200 or $300 per ton, and so they've added value to their product and are making more money out of it. So this is the sort of production of titanium that we had in South Africa in 2001. I don't have more recent figures for this, but you can see that the number one production in the world is from Australia. South Africa is number 2 in the world in terms of the entire world production of about just under 5 million tons of titanium oxide. And you know that titanium is used, it's got many different uses in steel, in the steel industry and so on, but it's also used for paint. And another thing that it's used for is paper. The white color of paper is from titanium dioxide. So it's in very wide use throughout the industrial world in many different processes. So there's a huge demand for titanium. Okay, so we have basically in this course gone from the origin of the universe and the origin of the solar system to the origin of the earth, and then the evolution of the oldest rocks, and we have gone through steadily in this history of South Africa. So you can see that South Africa has got a phenomenal geological history spanning a large part of Earth history from 3.6 billion years, where the oldest rocks are found in southern Africa, all the way through to the recent, and we have got mineral resources in rocks of all ages, from the Barberton Greenstone Belt with its gold and iron ore and asbestos, through the Transvaal supergroup with its massive iron manganese deposits, and we saw the Witwatersrand with its biggest gold deposits, the Bushveld complex with its titanium and chrome and so on, all the way through to the kimberlites in the diamonds, as well as concentrations of kimberlites, of diamonds in young rivers systems in the modern day ocean floor, as well as these heavy mineral sands coming up from the uplift history. So South Africa has a lot to show any geologist. And I was mentioning during lunchtime that in 2016 we are going to host the International Geological Congress, so in Cape Town, and in order to bid for this at the IUGS, we went to the IGC in Oslo in 2008, and we showed a small video in which Professor Martin de Wit was standing I think in front of either Table Mountain or the Barberton Mountain land, and said, every geologist in the world has to see the geology of South Africa before they die. So I would first like to thank all these people and say muito obrigado to Professor Onildo Marini, whose brilliant idea it was to establish this whole course of instruction for the geologists at CPRM. Thank you very much. I'd like to thank Novaldo Teixeira for thinking of inviting me to this course, because he's heard me talk before when he was in Southern Africa. I thank Gustavo Melo, who unfortunately is not here, but he helped very much to set up the course and to help me over the last week. I thank very much Professor Sergio Valente, who has been fantastic in translating and helping with this course. And I want to thank Diana from CPRM here, the Rio de Janeiro office, for all the help that I've got from her as well. And of course, to all the participants in the course all over Brazil who are listening in on this, thank you very much for your attention over these last 5 days. It's been a pleasure for me, and I hope it has also been a pleasure for you. And finally, I want to invite you all to Cape Town and come and see all of this fantastic geology in 2016. Start saving now. Now, I do want to leave behind some presents, because I think it was Novaldo who suggested that I should present this course based on the book that we published in our geology department, Wits University, and it's available in all the bookshops in South Africa. But because it's probably not yet available in all the bookshops in Brazil, I would like to present my copy to the CPRM for their fantastic library over here, so that maximum use can be made of this book. So I would like to present this. Maybe Diana, would you like to come and accept this? You represent them for sure. Well, thank you very much, but don't go away. I have something else too, you know. Find it. Give me 1 second.
O livro vai ficar disponível na biblioteca da gente. Lógico. Não vai ficar. Não vou levar para casa, infelizmente. Quê? Não tem tempo. Infelizmente não tem tempo de ler tudo isso.
Well, I'd like to thank you for all the work that you've done for this course. Okay, thank you very much. And Sergio,
Yep.
you have done a splendid job. And I'd like to present you with what looks like a Brazilian T-shirt, but it is not. No, it looks like a Brazilian football T-shirt, but in fact,
Thank you very much. Thank you very much.
Okay.
Thank you. It was a
So-
pleasure.
it will remind you of South Africa.
Oh, yeah. Okay, thank you. Muito bem, pessoal. Eu gostaria, em nome dos organizadores, agradecer também a todos os participantes aqui do Rio de Janeiro e também das outras unidades por toda a colaboração ao longo dessa semana, que para a gente foi de trabalho duro, embora a gente saiba que no final eu acho que o resultado foi muito bom. Aqui no Rio, pelo menos, a gente recebeu vários comentários de que o curso foi proveitoso. A gente tem recebido também comentários de colegas de outras unidades. But we won't leave you before you answer just a few questions. It's almost done. Tem alguma pergunta vindo do pessoal de fora? Ok. Então, vamos responder essas duas perguntinhas dos colegas. Tem alguém aqui que quer fazer alguma pergunta? Presente aqui no Rio? Não, então a gente responde essas duas e aí eu... Professor. Pergunta do Marcelo, de BH, Brasília. Zita. Ok, boa, Marcelo, eu ia perguntar isso também, legal. Well, the people in Belo Horizonte want to thank you very much, and we have a question from Brasilia. Is there any monazite associated with these black sands?
I think there probably is a small amount, but it's not enough to be economically, concentrated and separated as a separate stream. Because when they extract the heavy minerals, they have to, end up with a concentrate of rutile, a concentrate of ilmenite, concentrate of zircon. So if they had also to extract some of the other heavy minerals, they'd have another stream, but there is not enough, at least on the East Coast. Maybe on the West Coast, because we have some very rich monazite deposits that are going to be mined. There is a place called Steenkampskraal in Namaqualand in South Africa, near the West Coast, which is a primary deposit with rich in monazite, and it's going to be mined as a rare earth deposit. Right? And so because of that, maybe there's a greater potential for heavy mineral deposits on the West Coast, but there's been less uplift on the West Coast than there was on the East Coast. So there is Namakwa sands, but I don't know if there is a potential. You really need to have the right source rocks to produce a rich monazite deposit. So there's not enough monazite to be economic. Oh, by the way, I have to say that I really enjoyed giving this course to everybody who is listening out there, and I would actually enjoy getting your feedback. So you all have my email. And please send me 1 or 2 lines in Portuguese. If you it will improve my Portuguese. You've been learning English all this time, but if because I can read a little bit of Portuguese, it's not too different from French. And it would be nice to hear from you and to hear your comments and any suggestions for improving this, my presentations, or anything for the future. I'd like to hear from you. Thank you.
Muito bem, o professor agradece a todos, pede que mantenham contato, todos têm um e-mail dele, podem escrever em português, ele lê francês, então ele acha que também pode entender o português e, quem sabe, até mandar algumas respostas também em português. Com relação à monazita, não há monazita, pelo menos em quantidade que seja economicamente viável, principalmente na parte leste na costa leste da África. Na costa oeste da África existe um projeto de exploração de terras raras em monazitas, mas é em monazita primária, não é monazita em placer, né? Mas na costa leste não, isso não há. Tem uma outra pergunta. Obrigado. Tem uma outra pergunta do Marcel Besser, lá de Fortaleza. E a pergunta é... Não, segura, pode deixar. Não, meu amor, segura. Esse suerguimento expôs... Esse suerguimento expôs as bacias margem passiva dos oceanos Atlânticos e Índicos, desculpa. Por quê? Obrigado. Qual o tamanho desse suerguimento? Ok. We have this question coming from Marcel and from Fortaleza, and that's the last one. This uplift exposed the passive margin basins of the Indian and Atlantic Oceans, and if yes, why? And if it is the case, how high was this uplift? No, sorry. He wants to know how high was this uplift anyway? But he also wants to know if this uplift exposed the passive margin basins of the Indian and Atlantic Oceans. I think
yeah. Okay. So this would be the diagram that is of interest. If you plot on here the Dwika tillites, which at the time of the glaciation in the base of the Karoo Basin was a flat surface, right? The continental interior had undergone a billion years of erosion and weathering, so there'd been a lot of weathering, and it was basically eroded quite flat. And when the glaciers came in from the northern highlands, they were basically almost at sea level. They were entering the sea, and we know we've got glacial marine sedimentation. So we can take the base of the Dwika as a kind of a datum point and say that was close to sea level at the time of the Dwika glaciation, which was 300 million years ago. Now, today we can go to the east coast of South Africa in Durban, and in Durban we can see the base of the Dwika. There are striated pavements there, and it's very close to sea level. So it's still very close to sea level right now on the coast, and the same with the west coast. But the interior of the continent, the same has been uplifted, so you can follow that unconformity, and instead of being a horizontal unconformity, it is bowed up, so that you can go to the interior of the Vredefort Dome, which is now sitting at about 1,600 meters above sea level, and you still see the striated pavements from the Dwika, which are now uplifted that much. So it shows that the uplift is sort of, the continent has been bowed up like that, and it's not like a from the margin where the whole thing has been lifted up. It's kind of just bulged up like that, and the unconformity itself is now curved, and it's going from 0 to 1,600 meters and down again. So and that amount of uplift has happened since rifting, since the opening of the oceans, since the Cretaceous, and you can see what it's eroding is the Jurassic Karoo lavas, which have been massively eroded. They used to cover probably a much larger area, and now with this recent, in the last 20 million years, this rapid uplift has left behind just the remnant of this Drakensberg, but everything else on the east coast has all been eroded away, all of this area, and is now sitting down here in the coastal basins.
Ok, bom, o surgimento principal, na verdade, não foi nas margens continentais, mas sim na parte mais central do sul do continente, né? Existe um pavimento estriado sobre o qual há uma discordância que pode ser acompanhada, né, desde a costa até as partes centrais, indicando que as áreas que estavam no nível do mar e que são marcadas por esse pavimento estriado, associado a uma glaciação, eles hoje estão, essa discordância pode ser encontrada até 1.600 metros de altitude. Então o surgimento na parte central pode ter chegado a essa magnitude, né? Mas todo o surgimento está, na verdade, eles chamam de bulge, é como se fosse um domeamento localizado na parte central e que não movimentou muito a parte costeira, nem a oeste, nem a leste também. Então as margens não foram muito soerguidas, embora a parte central tenha sido tremendamente soerguida e se consiga ver essa discordância saindo próximo do nível do mar, chegando a 1.600 metros no interior do continente. E esse soerguimento foi tamanho que erodiu uma quantidade enorme das vulcânicas do Karoo. Esse surgimento, ele acha que ele vem ocorrendo desde o Cretáceo e foi responsável pela erosão de uma quantidade grande das vulcânicas do Karoo e que deveriam antes cobrir uma área muito maior, antes do surgimento cobrir uma área muito maior no sul da África. Eu acho que é isso. Tá bom, então? Okay, we have all people outside Rio thanking you very much, and again, the name of the Geological Survey, we'd like to thank you for this incredible course. I think it's going to be of real importance for all the geologists in Brazil, and we hope to see you in 2016 in Cape Town to see all this wonderful geology and in the field, and who knows, together and get our hammers and destroy part of your beautiful geology. Bring some samples from South Africa to Brazil. Obrigado a todos novamente e a gente agradece os colegas das outras unidades regionais mais uma vez e a gente vai continuar nesse esforço de fazer com que esse programa de formação continue a melhorar cada vez mais. Obrigado ao Noevaldo Teixeira também por dividir, por me deixar, por me convidar para participar desse programa, e eu espero também que tenha sido de alguma ajuda para todos vocês, ok? Então, até mais, muito obrigado.